All right, well, it is 9:20, so it looks like we made that work just in time. We'll go ahead and get started with our first presenter. Are you able to share your screen, Shuan?
We're sec.
While you get ready, I'll say each presenter has been given 20 minutes. I'll do my best to keep us on track. I'll keep an eye about 2 minutes before. I'll turn my camera on if need be, and if at the 20-minute mark you're still talking, I may interrupt you so that we can keep on time here. Our first session has 4 speakers in it, and once our presenter is ready, and it looks like the screen is starting to come through there. We'll go ahead and turn over to you for your machine learning talk.
Okay, can you see my screen now?
Sure can, and hear you loud and clear.
Okay, thank you. Thanks for having me. My name is Son Huang from the Ohio State University. Today I will talk about the machine learning-based force models for irregular shaped particles in gas-solid flows. Okay, so this study is about the gas-solid flows, and then you can see on the left side of this slide, it is showing the chemical looping system. We're using iron oxide particle with the air and then circulate from the combustor to the cyclone to separate them. And then the particles will go back to in the combustor through the moving bed reducer. And then this is the system we can produce the syngas. And what I'm trying to say about this figure is even within this one system, you can see there are a lot of different flow patterns because they have different configurations and flow conditions. So to understand this type of system, we need to understand the interaction forces between the gas and solid, and then we can apply the high resolution CFD methods to obtain the exact flow pattern around the particles. But this method is computationally heavy, especially for multi-particle systems. So practically, we apply the experiments. So for example, we can apply the 2D fluidized bed, and we can observe the bed to see the bulk behavior of the gas-solid flows, and we can establish the semi-empirical force model and then apply the model into the larger scale CFD method. And recently, several researchers started applying the machine learning method, and the bottom right corner figure shows one of the good examples applying machine methods. So this study is about to obtain the individual drag force for single spherical particle, multi-particle systems. And then you can see there are different colors. Even though they're using the same shape of the particles, the drag force is different because of the neighboring particle effect. So this is the output they want to predict, and then they collect the data by applying the high resolution CFD method. And then in the study, inputs are Reynolds number, solid volume fraction, and neighboring particle effects and neighboring particle positions. And they apply this deep neural network, and then the machine learning method usually is known to behave as a whole black box, but they apply the intermediate variables obtained from the DNS method, which are the pressure field and the velocity fields. So rather than applying this machine learning method as a black box, they actually put the intermediate parameters to behave as a physical information to improve the overall accuracy of this model. And in this study, we want to apply the neural network-based force models to predict the behavior of the non-spherical particles in gas-solid flows. The non-spherical particles are difficult to define their geometrical factors, so usually we apply the regular shape equations such as the super-ellipsoidal equation, and then once we define the particle shapes, we can develop the force model, and then we can apply it into the large-scale CFD method. But the problem is, even with this simplification, especially the collision force modeling is heavy to compute, and then due to the simplification, the force model cannot be accurate. So we want to apply the machine learning-based and neural network-based force model to improve the computation efficiency and the accuracy for a diversity of non-spherical particles. So to generate the irregular shaped particles, we applied the spherical harmonic method. The left equation shows how we use this method, and basically this method contains some random number and to define a single parameter to define the roughness of the particles, which is called spherical descriptor D here. And then this is the proportional to the roughness, and then it varies from 0 to 1. But in this study, we set the maximum value as 0.5. And then other than this roughness parameters, we define the elongation and flatness indexes to generate the particles having the aspect ratio other than 1. So it varies from 1 to 2 in this study. So you can see the irregular shape particles here generated from this spherical harmonic methods. And then, as I told you, it contains some random numbers. So that means even we're using the same shape factors, the output can be different. So that is, we apply the variation autoencoder model, machine learning method, to distinguish them, to define the shape factors. So after applying this spherical harmonic method, we can obtain the Lagrange endpoint, and then we apply them into the in-house CFD model we developed by using the direct forcing scheme. We also applied the gas kinetic scheme with a simplified sphere function for incompressible flows, and we also applied the adaptive mesh refinement to improve the computational efficiency to collect the data for the following machine learning models. Okay. And then the neural network is basically the regression method to connect each layer of the data. And then if we have a 2 or 3D data, we can apply the convolutional neural networks. And for the one-dimensional multi-components data, we can connect them using the multi-layer perceptrons. And then the procedure is basically to update the parameters to make the better prediction. And then right figure shows one of the example we applied, the variation autoencoder model I explained. So from the spherical harmonic method, as I told you, the shape factors, even with the same shape factors, the detailed particle shapes can be different. So we applied this method to regenerate the original particle shapes. And then after the training, we can, so if the model can reproduce the original particle shape, that means the interpreted parameters can represent the particle shape. So we have the latent vector in the middle, and then we use this latent vector as an input for the following machine learning methods with the Reynolds number of the flow. Okay, so the first step of this study is about the interaction force model for single particles. So the center figure shows the overall scheme. So once we define the shape factors, which are the roughness, elongation, flatness, and the orientation of the particle, we can apply the spherical harmonic method to generate the irregular shape particles. And then we can apply the particle resolve the DNS method to obtain the actual force coefficients. So this is the way how we collect the data, and then this is the path we want to avoid because it is computationally heavy. So after applying the VAE method, we can obtain the latent vector which can represent the particle shapes, and then with the Reynolds number, we correlate them with the force coefficients from the CFD method by applying the multi-layer perceptron. So once we train this model, we can bypass the CFD method to obtain the accurate force coefficients. So right figure shows the data we collected from the DNS method, and the left figure shows the evaluation process. We change the instance angle of the flow, and then we can compare the results from the DNS and the results from this machine learning method. And then it shows, you can see when we increase the roughness of the particles, it shows the off-trend behavior for the drag, lifting force, and torque coefficients. And then this neural network can predict this pretty well with the high accuracy. You can see the mean square error shows pretty low values for this study. Okay, and then we wanted to expand the scope of the study for multi-particle systems. So once we apply the VA method, we can obtain the latent vector, and then by applying the multi-layer perceptrons, we can obtain the individual drag force. We focus on the drag force for this multi-particle system study. And then we added the transposed convolutional neural networks, which is the red boxes here. And then after the training, because when we collect the data through the DNS method, we were able to collect the data for the flow fields as well. So by using those data, we trained this TCNN model to predict the velocity and the pressure fields for single particles. So if we have two different particles, we can apply this method to predict the flow fields around the particle, and then we assume the linear superposition, and then we can combine them to predict what would be the flow fields with the two particles here. And then the bottom equation describes how we can modify the drag force by using this superposition. And for example, if you see the right figures, if you have three different particles, and if you want to obtain the drag force of the third particle, then we can apply the TCNN method to predict the flow fields for the first and second particles. And then we can add them linearly, and then we can calculate what would be the effective velocity at the position of the third particle, the surface average value, and then this value can be used into the bracket, the term in the bracket in this equation here. And then we tested this method for 100 different particles, having the concentration just up to 0.5%. And then the right bottom corner figure shows the accuracy can be improved by applying this superposition method, which is called pairwise interaction extended point particle model. And then the reason we applied this study just for the low concentration system is just because if you see this equation here, the first term is the average drag force, which is influenced by not just by the Reynolds number, but also by the solid volume fraction effect, because due to the self-perturbation, I mean, the average drag force is affected by the solid volume fraction. So to ignore this effect, we just tested this method for low concentration systems. Okay, and then recently we're focusing on to expand the previous study into, toward a higher concentration systems. And then to do that, as I explained, we need to have the equations to calculate the average drag force. So by assuming just a simple parameter which is influenced by the Reynolds number, solid volume fraction, and then particle shapes, we collected some data from the DNS multi-particle systems, and then we established these equations, and then we are testing this method for the higher concentration systems, and then we did for two different systems, one whole dispersed system having the concentration 6%, and one of these first systems having the concentration of 5%. And you can see on the right figures, it shows pretty good prediction in terms of the percentage adder, and then it shows the moderate ARCTUS scores as well. The reason we were able to do this is because it seems, if you see the data here, this solid volume fraction effect factor is influenced by mainly the solid volume fraction, not the particle shapes. But that is the assumption we apply this method in this study. But the particle shape itself does not affect much on this solid volume fraction effect, but it seems the overall orientation matters. So when high aspect ratio particles align in the same direction, that it is showing higher F factor here. So that is the thing we're working on recently. Okay, and then this is the last one. So we're working on the development of the interaction force model, but even we have the accurate interaction force models, we need to have the contact models to apply this model into the CFD-DM method. So if you just assume the spherical particles for the contact model, then the overall accuracy for the final application cannot be accurate. And then the problem is if we use the non-spherical particles for the DM method, calculating the contact probabilities are pretty heavy, because that requires to input additional loop inside of the DEM loop calculation. So the idea here is, why don't we just make the model for the contact probabilities calculation outside of the loop, and then apply them to the following the DEM calculation. So we generated 8 different particles, including regular and irregular shape. And then by putting the first particle in the center, and then we put the second particles randomly, random position and random orientations, and then do the iteration to calculate the contact probabilities, which are the mean contact point, normal direction, and the interpenetration depth. And then the inputs will be a relative displacement and orientation. And we also put the vertices of the second particles to include the shape factors as well. And then we applied the multi-layer perceptrons. You can see in this figure here. And then the outputs are the contact detection and then contact property calculations. And then after finishing this training, then it shows pretty not super accurate, but you can see the parity plot on the right here, and then we can use this method because after this training, we can evaluate the thousands of the particles, the contact properties within a second. That means the computational efficiency basically is equivalent to the spherical particles assumption calculations. So this shows pretty significant improvement of the computational efficiency for contact model. Okay, so this is the conclusion. The study provides the machine learning based force models for irregular shaped particles, which can be practical. And then one of the main point of this study is because by applying the superposition model at the end, we were able to make the model which mainly requires the data for single particles. That means we don't need to collect the multi-particles data sets to train the model, because that is the most heaviest part for fully dispersed systems for machine learning studies. And also this study provides the computational efficient collision force model, which can be applied, we hope, which can be applied to a CFD-DM method. Okay, this is it. Do you have any questions? Thanks for listening.
Thank you for the presentation. We have about 4 minutes for questions, if there's any. I don't see anything. Oh, there we have one. See the question in the chat there from Dinesh Tafti. What is the maximum Reynolds number you've tested at?
Oh, the range of the Reynolds number is between 0.1 and 100. And after, above the 100, because we're using the regular shaped particles, it shows unsteady flows then. So we think we need to have the separate machine learning approaches to evaluate the unsteady flows.
I guess I'll ask a question as well. So for the contact model, do you see any risk in, say, a machine learned model kind of missing collisions? Because CFD-DEM is well known to be extremely sensitive to we'll say missed collisions, and that you can get fairly unphysical behavior pretty rapidly if collisions are missed. Do you foresee that being a problem with these type of ML trained data sets?
Yeah, that would be the future study for this model, because we just apply the machine learning method and then try to calculate the accuracy, and then we compare the accuracy with the case just using the spherical particles for non-spherical particles. But to see like the problem you mentioned, we need to apply this method for the full DM studies, and we'll do that yet. So that would be the future study to see what will actually happen if we apply this method to the DM method.
Okay, great. Any other questions from the crowd?
Jordan, I do see a follow-up from Danish about the previous question. Does the accuracy deteriorate as Reynolds number increases from 1 to 100?
So what was the question again? Let me see, chat.
Does the accuracy deteriorate as Reynolds number increases from 1 to 100?
No, I mean, we didn't see any like changes according to the Reynolds numbers.
All right, and with that, we'll thank our speaker, and please keep an eye on the chat to see if you see any questions come through pertaining to your talk, and we'll go ahead and move to the next presenter. Roberto, if you'd like to share your screen and make sure your audio is working.
Yes, can you hear me?
Yes, we can.
Perfect. I'm in the process of sharing my screen, and
we got it.
Okay, let me go full screen. Which screen do you see? The presenter mode or the...
We see the presentation as expected.
Perfect. Thank you very much.
Thank you.
Okay, so good morning, everyone, and thank you for attending my talk. My name is Roberto Torelli. I'm a senior research scientist at Argonne National Lab in the Transportation and Power Systems Division. Today, let me turn my laser on because I'm going to need that. Today, first of all, I want to acknowledge a few people, aside from myself, but there's a few people that contributed to this project, in particular, Dr. Bethany Lush, Dr. Gina Magnodi, and Dr. Shudip Mondal, and especially the latter is the main contributor. So the work you're going to see today is the result of the research that he performed while at Argonne as a postdoc. I'd like also to acknowledge our computing facilities as well as Convergent Science for providing the licenses to the software Converge that we used for the simulations performed in this work. So I want to introduce the problem that we are interested in solving here, and I'm going to populate these slides because I'm going to talk about a few things that are pretty much everywhere on the slide. So in propulsion systems, in internal combustion engines, we have injectors. These injectors are delivering the fuel. And when it comes to simulating the effect that the internal flow to the injector has on the spray formation, on the mixing, evaporation, combustion, most of the time we rely on very simplified approaches that completely disregard what happens inside the injector. So we assign a rate of injection, a mass flow rate, a total injected mass. We impose a cone angle in which we are distributing the Lagrangian parcels that are describing our spray. But we are definitely not considering most of the physics that are happening within the injector, which will affect how the spray evolves downstream. The problem, though, is that the simulations of the internal flow are characterized by much smaller timescales and length scales, which are usually not compatible with the timescales and length scales of the reactive flow simulation of the spray and the combustion that we are simulating in the engine. So it's really, really a complicated problem to do the coupling of the two parts online. There are examples in the literature, but there's still a demonstration of what could be done. But from a computational efficiency standpoint, from an industry perspective, these type of problems are commonly not resolved in a way that couples the flow internal to the injector to the spray. So our idea is to use a typical static coupling approach where we are decoupling the problem at the exit of the orifice. And we are basically using that information at the exit to initialize the Lagrangian spray with more information than if we did a typical rate of injection approach. However, to do that, we need to run the internal flow. That's expensive. So what we're trying to do here is we're trying to develop and design an emulator that is data trained and that can emulate the internal flow behavior at the exit of the orifice without having to run the actual simulation. In order to do that, we need to run, of course, a lot of cases. We need to characterize the data sets so that we can build an emulator and then get the information we want easily. So in this case, we are looking at a single hole injector. So this is a research injector. Usually automotive injectors are multi-hole. And I will go through the details of what this injector looks like and what kind of information we're trying to extract. But in order to build these maps that we use to initialize the spray, we will be looking at gaseous volume fraction, velocity components, and liquid mass. And all of that allows us to characterize the flow downstream. And I should have included temperature as well here because, of course, there are spatiotemporal fluctuations of temperature at the exit of the orifice. So introducing now the emulator framework. We will go through each phase of this. So for now, we focus on the first part, is the training data generation. So we are collecting 81 snapshots for each CFD case that we will be running. We will extract them at the orifice exit during a time duration of 20 to 40 microseconds in which we reach the steady state flow condition. And these are simulations in which the needle valve, which is this blue component here, it's actually fixed at a specified needle lift. In reality, that needle moves, and it moves to allow the flow to go through the injector. We will see how to account for that later in the presentation, but for now, we're focusing on static needle lift. And each snapshot of the 81 snapshot contains 4,214 grid points. This gives an idea that it's a high-dimensional problem that we're trying to solve. Okay, now we designed a design of experiments. We focused only on a few parameters to simplify the problem, but ideally this can be extended to as many parameters as we need. This, of course, means that we need to collect more data, but for this particular application, we fixed a certain amount of cases with a needle lift between 15 and 400 micron. We also played with fuel viscosity and with level of dissolved gases. Again, these are just 3 of many parameters that could be of interest, but this is more for a demonstration of the approach. This allowed us to design a DOE with 60 samples in total in this 3-dimensional design parameter space using a Latin hypercube sampling. So you see the blue dots represent the operating condition that we see during training, while the red dots correspond to the operating condition that we used for the test cases. Let's move into the reduced order modeling. So now we want to compress the data to a latent space, and we do that through an autoencoder. For those that are not familiar with autoencoders, we are basically using a deep neural network to compress the information of the 4,200 points down to a latent space of 8 points. And then we are redecoding that to go back into the original space, which is the one of the particular quantity that we're looking at. So for each of the quantities that I listed earlier, volume fraction, velocity, and so on, we are actually using different autoencoders that have been optimized for that specific parameter. So the idea is that with the encoder, we now can deal with a much smaller amount of data, 8 points, and use that to characterize through this neural network each single snapshot that we are taking from the internal flow simulations. There are some details here. We can go through that if there are questions, or they are well documented in the literature. Just a note, we also consider other dimensionality reduction techniques like POD, but we found that the autoencoders are better representing the non-linearities that we experienced in these flow fields. So here there is just a test of making sure that the autoencoder is working as expected. So we have the truth up here, the reconstructed flow fields in time, and here you can see how the latent space changes for each time step. So this tells us that based on the errors that we measured on this reconstruction, that the autoencoder is actually able to encode and decode the information going into the latent space and back into the original space. Moving forward, we want to apply now regression modeling because we have those 3 parameters, needle lift, viscosity, non-condensable gases. We want to link them to the actual output without having to go through a simulation again. So the idea is that we are now using a neural network to connect the 3 initial parameters plus time to the latent space directly. So this allows us to skip the use of data, of course, now that the model has been trained. And then through the use, through the use of the pre-trained decoder part of the autoencoder, we can now reconstruct the flow field. So that basically means that we are linking the original parameters through this regression model and the decoder directly to the flow field of interest. So this allows us to connect directly how the parameters are influencing the emulated flow field of interest. So here you can see the predictions of these time average flow fields. So you can see the truth up here, and then in the middle you have the time average truth. So we took those 20 microseconds of 81 snapshot, and we averaged them. We did an ensemble average, and here on the bottom you can see the emulated flow field for a test case that was not seen during training. And we can see that although there might be some room for improvements on certain particular flow fields, like for example the V component of the velocity or the void fraction, the volume fraction alpha, the error is acceptable to tell us that this approach works, and it works with the amount of data that we used for the training. We now are able to generate those maps. I'm not going to spend too much time here. We used Converge for the combustion, spray combustion simulations. There are a bunch of details here. I'm happy to go through that. But what we're looking basically at is an endodecane spray with a 1500 bar injection pressure into a chamber temperature of 900 Kelvin and 22.8 density. These are typical conditions of the so-called engine combustion network spray A. So we use this type of condition to test how the reacting spray is behaving. And here you can see how the spray originating from the emulated maps and the combustion that is ensuing to the mixing and evaporation of the spray is qualitatively non-recognizable between the truth and the emulator. So that tells us, at least from a qualitative standpoint, the emulator is definitely predicting a reasonable behavior of the spray and the combustion. This approach when it comes to the single case that you're looking at, after, of course, all the training, it is 2 million times less expensive. So this number should be seen as the ability to generate a new case that we haven't not run in the internal flow with a turnaround time that is 2 million times less expensive if we had to go through the entire process through only CFD. Here we have some also quantitative comparison between the true CFD case and the emulated case. And you can see that, for example, parameters like liquid and vapor penetration, maximum temperature, the heat release rate, they all pretty much coincide between the two cases, giving us even more confidence that this approach works. However, that was for fixed lift. How does this work when we want to move into moving needle lift? Now, keep in mind that an typical injection in an engine lasts a few milliseconds. We were only looking at 20 microseconds. So the internal flow simulation turnaround time for a typical moving needle lift simulation is about of the order of weeks, as opposed to days and most that usually engine simulation would take. So this is definitely a big bottleneck for this type of applications. So we need to accelerate the internal flow so that we have comparable turnaround time with the engine simulations. But we also need to deal to the fact that data are scarce because these simulations take too long, and even generating an enough amount of data, it's going to take a lot of time. So what we did, we wanted to use an approach where we are transfer learning from the static needle simulation to the moving needle. In order to do that, we are basically taking the original neural network, freezing a certain amount of layers, and retraining only the final layers that go into the latent space of the moving needle simulations. So this is the design of experiment for this particular case. So the parameters that we are investigating are now the same. However, the needle lift is actually linked directly to time through this needle lift profile. And we are looking at 11 samples where the red dots are training, the triangles are validation, and then we have one test case. Again, we are using the autoencoder, which start from the weights and biases of the original autoencoder framework that we did for the static needle autoencoder. So here we have the performance of the for the reconstruction error, and you can see that when we use transfer learning as opposed to not using transfer learning, we are consistently improving the lowering the error that we commit at every single time step, where, as you can see from the red line here, as opposed to the black line. So the transfer learning in general results in a better reconstruction performance, which is 5% reduction of this L2 norm error that we have across the entire duration of the simulation. So going back on to the original framework, this is the one we use for the fixed needle. Again, we go from the parameters through a neural network directly into the latent space. We use the decoder and we obtain our flow fields. What we're doing now, we are trying to link the new, there's a change in the input space because the lift is actually linked to time. So we are linking that to the original regression model, but we're freezing, as I mentioned, a few initial hidden layers, and we're retraining the last few hidden layers with transient simulation data. And we are now using the decoder from the transient needle emulator, which is different than the original one for the static needle emulator, to obtain the emulated transient needle flow fields. So here you can see how this allows us to improve almost over the entire range of time and needle lifts the error for the emulation of a case that has not been seen before. And we have a peak reduction of 20% in the emulation error before the end of the ramp-up phase. We do see some peaks over in the last portion of the injection that we need to address, but overall, it seems like the transfer learning is delivering while also allowing us to deal with a much smaller amount of data than we would need if we didn't have transfer learning. So looking now at the effect that has on a spray combustion case, we can see again from a qualitative standpoint, the flame looks pretty similar. The spray evolution looks pretty similar. But then also if we look at the liquid vapor penetration, maximum temperature, heat release rate, we are indeed looking at very good agreement between the emulated flow fields and the truth from the CFD case. And this results in a 38 million times less expensive generation on new case, just because the bottleneck again is in the moving needle simulations, which can take up to a few weeks to complete. So I think this is my last slide. With this, I would like to thank you. I think I'm perfectly on time, and I would be happy to take any questions.
Thank you very much. I'll let Deepak take over for managing the questions in the chat.
Yeah, sure. So the first one is from Danish. Are you predicting time-dependent BCs or steady state? If time-dependent, are they time-correlated frames?
So yes, we are predicting time-dependent boundary conditions for the maps that we are using for the Lagrangian spray in the decoupled simulation of the spray combustion. So those are time-dependent because the needle lift is actually also a boundary condition that is time-dependent, right? We are assuming a triangular profile. In reality, those profiles are much more complex, but in general, the response that we have at the exit of the orifice is the result of that time-dependent boundary condition that we are imposing on the needle. Now, there is no direct accounting of correlation from time to time in the snapshots, but given the way the autoencoders are framed, they will account for those nonlinearities, and the autoencoder is the same for all the time steps. So it's kind of inbuilt the ability to capture certain effects that are time dependent, because that autoencoder needs to satisfy the entire evolution of the flow fields in time. I don't know if that addresses the question.
Thank you. Yeah, Danish, please let us know in the chat if you have any follow-up for that. Okay, so essentially you treat each time step as a static case. Is that right?
From the emulator perspective, yes. They are treated as independence of the other time steps. But they intrinsically account for that history just because they're the result of the previous time step.
Thanks. And one more question is, what exactly do you mean by transfer learning? Is it the fact that you start with weights and biases of the static needle?
Yeah, that will be one good way to interpret it. Yes, because we don't have a lot of data due to the cost of generating those data for the moving needle simulations. We are starting from the assumption that the timescales of the flow through time, which is usually for these injection pressures and velocities, is a few microseconds. It's almost possible to assume that the flow field at the exit is the result of the exact position of the needle at that moment. There are, of course, effects connected to history, especially if there are non-uniform distributions of the flow fields. But it's not a too wrong assumption to say that at that time the needle is imparting the way the flow looks like at the exit. So by using those weights that we had in the autoencoders in the regression model and tweaking only a few layers, we are at least starting from a starting point that makes sense. And then modifying those later layers, we are able to tweak the autoencoder, to tweak the regression model in order to predict the effect of the moving needle valve on the flow fields.
Great. Thanks, Roberto.
Yeah, thank you very much. And we'll go ahead and with that and move on to our next presenter. Please keep an eye on the chat to see if there's any more questions that roll in about your talk. And with that, we'll go ahead and turn over to our next presentation, which will focus on the material point method and its application to multi-phase flows. I believe our presenter was, yeah. Are you able to share your screen, Shrith? Here we go.
Sorry, can you hear me now?
Yep, we hear you now. Okay. But we lost your screen.
Yeah, I can share it. So can you see my screen now?
Yep, we see PowerPoint.
Okay. Okay. So talks about neural networks and machine learning, and this talk is going to be old school. Good morning, everyone. My name is Srijit. I'm a researcher at the National Renewable Energy Lab at Colorado. And today I'm going to talk about a numerical analysis of regular material point method and its application to multiphase flows. Okay, so just to give a brief background, so with the growing computational power at our disposal, researchers today are interested in performing simulations of complex real-world phenomena. These simulations often involve multiple scales and need to incorporate multiple physical aspects too. This gets even more complicated when there are complex geometries of the computational domain involved. For example, on the top left of the presentation, I'm showing a simulation of a rolling snowball. These animations were used in the movie Frozen as well. So on the right-hand side, I'm showing compaction of concrete, which has been simulated, and pouring candies from a tube. So these pictures are taken from a publication from Wang et al. And at the bottom, I'm also showing simulations of a toothpaste applied on a toothbrush and simulations of ice cream being spread on a conveyor belt. Incidentally, all these simulations are performed using material point method, and the details of which I'll be giving in the coming slides. So material point method is basically a hybrid Euler and Lagrangian method. It's an extension of the particle in cell method used previously. So here the material is represented as a collection of what we call as particles or material points. The kinematic, dynamic, and the material specific properties are stored at the material point level. We also need a background mesh. We call them as a background mesh or the background Eulerian mesh. So this mesh is used as a scratch pad for calculating the gradients, as well as for the time integration of the governing equations. So these features of material point method give certain advantages to this method. So as I told you, we don't require unstructured meshes or deforming grids. These methods can handle large deformations. And I told you that the material properties are stored at the material points. Hence, incorporation of multiple constitutive models is easy. Complex geometries can be modeled using this method, and this method is also amenable to large-scale computing. So coming to the governing equations, the mass, momentum, and energy equations are the governing equations that we use. But in this talk, I'm focusing on isothermal applications, so energy equations not shown here. The momentum equation is expressed in a Lagrangian form and is shown over here. The mass equation is not considered because it's implicitly satisfied at the material points. So sigma is a stress term, which is expressed as a function of the deformation gradient and material properties. So in this slide, I'll talk a bit about the various steps involved in a material point iteration. So to begin with, we initialize the simulation with material points, a collection of material points with specified locations, velocities, and stress tensors. Now we embed them onto a background grid, which is typically a Cartesian grid as shown in the figure here on the top left. In the first step, what we do is we project all these properties, namely mass, velocity, and the forces experienced by the material points onto the nodes. So that expression is shown over here in point 1. So here it's the mass matrix, and then we also see Ni, which is the shape function, and I'll talk about it in the coming slide. So having obtained the velocity at a particular node, in the next step, we obtain the velocity at the next time instant, which is Vi at t plus delta t, using a simple Euler time integration scheme. And once we obtain the updated velocity at a node, we go to step 3, which is where we update the particle velocities. So in the particle velocities step, there are 2 steps, namely a flip update as well as a pick update. So it is a blend of, in fact, both these schemes. In a pick update, the velocity update is performed basically as a function of Vi at t plus delta t alone and the shape functions. Whereas in a flip update, the update happens based on the incremental velocity, which is Vi at t plus delta t minus Vi at t. And in most of the NPM codes, we have a blending between these 2 update schemes. So alpha is a blending factor. which varies between 0 and 1. For 0, we get a purely pick update, whereas for alpha equal to 1, we get a purely flip update. Once we obtain the velocity at the material points, the fourth step is to time integrate these velocities using a simple Euler time integration scheme to obtain the particle positions, updated particle positions. And these steps continue for in the iteration of the MPM scheme. So talking about the shape functions, in most of the material MPM codes, we use three shape functions, namely the linear hat, the quadratic B-spline, and the cubic B-spline. As the name suggests, linear hat has a short stencil, and we assume a linear variation between the stencil, linear variation of the property between in a stencil. Whereas in a quadratic B-spline, it's a quadratic variation. In a cubic B-spline, it's a cubic variation. On the bottom of the slide, I'm showing the gradient, shape function gradient values in the stencil. One thing to be noted is that for a linear hat shape function, we have a discontinuity in the gradient value across the node. So if there is a material point which crosses across the node, it suffers a certain discontinuity in its gradients. This shows up in the strain rate values as well as in the stress values, and this could lead to errors. Whereas this problem is not present in quadratic as well as for cubic B-splines. It should also be noted that as we increase the order of the scheme, the computational cost also increases, and it can go up to like an order of magnitude difference between the cubic B-spline and the linear hat. A brief mention about our in-house solver. So we have the in-house solver, Hexagroup, which we developed at NREL. Hexagroup is developed based on the Amrex framework, and the particle class in Amrex is used to model the material points in the code and the related operations. The block structured grid framework in Amrex is also used to create the background grid in Hexagroup. We use level set methods to model complex geometries, and Hexagroup is capable with both CPU and GPU capabilities. Coming to the spectral stability analysis of MPM, which is the core topic of my presentation. So here we take a prototypical equation, which is shown on the top left. Here, V denotes the velocity, and Fi is the internal forces, Fe is the external forces. We assume the external force to be 0 for this analysis, and the internal force is simulated like a stress term in a Newtonian fluid. So we express this equation in a weak formulation, and making the assumption that the density is expressed as a direct delta function summed up over all the material points in the domain, we come to the MPM governing equations of the nodes, which is shown here. So the first term is basically the mass matrix. A is the acceleration at a node J, and here the second term is basically the internal forces acting at a particular node. To study the stability analysis, we take the one-dimensional domain shown on the right-hand side. So here all the plus signs denote the nodes, and the red circles denote the material points. For representative purpose, I've shown the material points to be located midway in the cell, but it may not be the case. We can vary these locations of the material point rather arbitrarily. The properties at a material point is denoted with a subscript P, and the subscript is used to denote time T. And similarly, the properties at node is denoted with a subscript I. There are a total of Ni number of nodes and Np number of material points. So the assumptions are like the domain is one-dimensional, it has got periodic boundary conditions, the external forces are assumed to be 0, and we induce another additional assumption, which is that all the material points have the same mass and it's a constant. We study the stability from a velocity perspective, and we assume that the material point locations are frozen while we carry out the analysis. So I come back to my previous slide. I'm showing 3 of the 4 steps involved in a material point update. So I mentioned before, the first step is the projection of the material point properties onto the node I. So we can mathematically express this through a transformation matrix T bar, which acts on the vector of the material point properties at time t. So this transformation matrix T bar is actually a function of the mass matrix and a coefficient matrix. Mass matrix is a square matrix of size Ni by Ni, and coefficient matrix of size Ni by Np. And these both matrices are basically functions of only the shape functions. Yeah, so coming to the next step, this involves velocity update at the node. So again, this can be expressed as a transformation matrix times a vector of the velocity at the nodes at time t. So the transformation matrix is given within the square brackets. This induces a non-dimensional number, which is the Fourier number expressed as nu times delta t by h squared. H is the grid spacing, delta t is the time step. And here we also see two additional matrices, the gradient matrices for the P to G and the G to P operations. These are again functions of the gradients of the shape functions. These terms arise because of the estimation of stress terms. Coming to the third step, so we can express the nodal quantities as a transformation matrix times the quantities at the material points. And we can club all these equations into the final equation for the velocity update here, which gives us, again, a transformation relation for the velocity at material point P at time t plus delta t as a matrix times the velocity at material point at time t. So here theta is the Fourier number times the product of the matrices here, and phi bar is identity times the theta matrix. Now, for an exact analysis, we can express the velocity as a Fourier transform and at time t. So if we want to calculate the velocity at time t plus delta t, we can express that as a theoretical amplification factor times the Fourier amplitude we had. So similarly, we can express the same thing for an MPM update too. So this is the expression that I've taken from the previous slide. So at any particular node, the velocity of a material point P at time t plus delta t can be expressed as this transformation matrix, which I call as A, times the vector of all the velocities at material point other material points. Doing some manipulations, we can arrive at the final relation where we can express the amplification matrix for a particular scheme as A bar times P, where P is a projection matrix. So this G is the amplification matrix, and this is a function of the non-dimensional wave number K times H. H is a grid spacing again, and the non-dimensional number, which is the Fourier number. So knowing the shape function evaluated at a specified material point locations, we can calculate the amplification factor. The amplification factor is basically a function of KH and FO, and it's a complex number. So we look at the magnitude of the amplification factor to see how much wave component amplifiers are diminished. So here I'm plotting the amplification factor contours as a function of KH and FO. And in this slide, I'm studying the effect of alpha. I mentioned before that alpha is a peak flip blending factor. So I'm studying here how alpha affects the solution properties. So I've taken linear hat as a shape function, and the material point location is fixed to be the middle of the cell. So on the left-hand side, I'm showing the amplification factor contours for alpha equal to 1. On the right-hand side, I'm showing for alpha equal to 0. And here we see that the yellow region is regions where the amplification factor is close to 1, which means it is stable and almost replicates the exact waveform solution. We see that for low values of Fourier number, which is low time steps, we can have a good computation performed for all the wave numbers, which is basically like high frequency components to low frequency components. Whereas if you want to increase the time step, which is basically increasing the Fourier number, we can do it only for a specified number of low frequency content. So that's for alpha 1. But for alpha equal to 0, we see that the properties are independent of KH, and it is a function of only the Fourier number. With increasing Fourier number, which is basically increasing time step, we see that the magnitude of the amplification factor reduces progressively. So we are expected to find higher and higher dissipation or higher damping in the solution for alpha equal to 0. On the next slide, here I'm studying the effect of shape functions. So I'm taking 3 shape functions, the linear hat, the quadratic B-spline, and the cubic B-spline. On the top, I'm showing the plots for alpha equal to 1, and on the bottom, I'm showing the plots for alpha equal to 0. So talking about alpha equal to 0, we see that all the shape functions perform pretty similar for alpha equal to 0. For alpha equal to 1, the linear and the quadratic B-splines perform almost similar, whereas for cubic B-spline, we find a larger domain for accurate computations. And this is for, again, material point location of mid-cell. The third slide, here I'm showing the effect of varying the material point location. We are assuming only a single material point inside a cell, and here I'm varying the material point locations with respect to the cell. So I'm comparing two shape functions, namely linear hat and cubic B-spline, and I fixed alpha equal to 1. So for when the material points are close to the nodes, we see that for linear hat shape functions, the amplification factor can be greater than 1. So that is in the zone. So which means that for higher and higher Fourier numbers or larger time steps, we can find numerical instabilities. And this is noted in the literature, and we call that as a grid crossing instability that I talked about before. And for linear hat, the properties vary considerably with the different locations of the material point within the cell. Whereas for the cubic B-spline, the variations of the amplification factor for different material point locations are very minimal. So it shows that the cubic spline properties are least sensitive to material point locations. So having talked about these properties, I want to demonstrate these properties using some test cases. So here I've taken a test case of of an elastic bar, which is fixed at one end and free end at the other. And this has a uniform cross section. And the bar is given an initial displacement of 0 with an initial velocity as a sine wave. And the rod is left to vibrate. So we have an exact solution for this case, and that is known to us. So similarly, we model this using NPM. And here is the domain that is used for modeling. Here you can see the background grid as well as the material points shown as circles. To compare between the theoretical and the NPM solutions, I use the center of mass velocities, which I'm sharing in the next slide here. So here I'm showing the effect of alpha, and I'm taking the shape function as linear hat. And here I'm taking 2 points, point A and point B, which are identically located in the KH F4 space. So here are the KH and F4 values. The scheme is also the same. The only thing that differs is alpha equal to the value of alpha. So for test A, we have alpha equal to 1. And for test B, we have alpha equal to 0. The predicted amplification factors are also noted here. And this is what we see when we perform the numerical test too. So here I'm plotting the velocity of the center of mass as a function of time. And the red curve shows the exact solution, whereas the NPM solution is shown as a blue curve. For the test A, we find very minimal damping numerically, whereas for test B, we see that the solution is damped considerably. So that shows the effect of alpha. And here in this slide, I'm showing the effect of grid resolution. So here I've taken the same scheme, which is a cubic B-spline, and I'm only varying the value of KH. So point C, we have a low KH value. Point D, we have a high KH value of 0.628. So the predicted value of G are shown here. For test C, we have a G value of 0.98, and test C, we have a G value of 0.90. And that is also evident from the numerical experiments. So test C shows very minimally damped solution, whereas test D shows damped solution because of the lower amplification factor. So the conclusion is that alpha equal to 1 does not necessarily give undamped solution. It also depends on the grid resolution. So that brings me to the conclusion slide. So I think I'll leave it at here and then take any questions.
Thank you very much. Interesting talk. I find NPM quite an interesting application, and it's nice to see a somewhat rigorous numerical derivation or exploration of parameters within the models itself. Mm-hmm. Can you, there we go, we have a question. Deepak?
Yep. So this is from Will. What causes the step change at time 0 on your last slide for G equal to 0.9?
Oh, this one?
For the G equal to 0.9, so test D?
Yeah, I see that, yeah. Okay, I think probably it's because of the boundary conditions effect, because this we are assuming periodic boundary conditions, but for this particular case, we have a slip wall. So we are thinking that might be the issue. It's not an apple-to-apple comparison, to be honest, but we are capturing most of the trends that the stability analysis predicts.
All right. With that, I'm going to ask you to keep all questions to the chat to keep us on time. We're at 10:20. So go ahead and move to the next presenter.
Okay, thanks.
Jim Parker coming up next to talk about empirical drag model based on foundational data sets and fluidization.
All right.
We hear you and we see your screen.
Fantastic. All right. Thank you. Yes, I'm James Parker with CPFD Software. We'll be talking about a product we've been working on for actually quite a while here. And the title of this talk is Revisiting When and You, an Empirical Drag Model Based on the Foundational Data Sets in Fluidization. Before I get into the drag models, a bit about CPFD software. We develop Barracuda Virtual Reactor. It's a multi-phase CFD code for simulating large-scale particle fluid systems like the FCC regenerator that's shown here. We have the particle fluid hydrodynamics being calculated along with reaction chemistry and heat transfer. Barracuda is used for a wide range of applications, though, and we commonly get questions about drag, like what drag model should I be using? For those with the capabilities, ask like what experiments or particle characterization should be performed, and if that experimental data is available for their particles. Question then is how can I improve the drag model or tune it based on this experimental data? And this is increasingly important as we look at some of the newer applications that are being modeled in fluidized beds. For example, or a nebulated bed in this case is the extradate catalyst in a nebulated bed hydrocracker, which is very non-spherical, this extradate. And we see this in a lot of more as emerging applications in fluidized beds where, of course, plastics are coming in various forms, biomass, of course, municipal solid waste, and then in cement applications, we see things like shredded tires and chipped wind turbine blades, all of which are highly non-spherical, non-uniform as well, and even within the set of particles that are there. And so this becomes the motivation for this work, is to try to understand how can we better model the drag for systems like this. So we're looking at just kind of background on drag models here. Typically for homogeneous drag models, the models will be correlated as a function of Reynolds number and of voidage, where at high voidages we have really single particle drag models, and at the low voidages you'll often see an ergon correlation that is used. And for kind of bridging the gap from across the range of voidages, models like When and You, Gittesbau, Defleece, Beatstra, various others that are commonly used in CFD to model this full range of Reynolds numbers and voidages that may be encountered in a fluidized bed system. Problem we run into, especially with these highly non-spherical, even sometimes the particles that are kind of look quite spherical, or closer to being spherical, is that the shape and the sphericity can have a significant effect. This is both for single particles where there are non-spherical drag models that exist, and then then at the other end, for fixed bed applications where we have the ergon correlation works quite well at correlating the shape and the functionality of the drag force, but it does have these two parameters, which I've noted here as A and B, And papers and literature have shown that there's a wide range of coefficients that can be used here in the ergon correlation, and and so then sometimes you'll see there's this modified equation where you have sphericity included in the equation as well. But that really brings up the question then: how do you measure the sphericity? If it's just a handful of particles, maybe it's looked at in a microscope, but a common approach is to measure the pressure drop across a set of particles and then back out the sphericity from the ergon equation. And so really, wherever that information is being stored, whether it's in these coefficients or in sphericity, the point is that there is variation as a function of particle shapes, and it can have quite an effect. So what we want to be able to do here is use that data to improve the drag. And so this is building upon some previous work where we're looking for a new homogeneous drag model here that has the following characteristics. It is matches the Schiller-Newman drag at voidage equal to 1, matches ergon at close pack, is continuous across the range of voidages, and can be improved by incorporating the experimental data. The approach here is to identify experimental data in literature where fixed bed pressure drop data and bed expansion data exists in the same set. For that fixed bed data, determine or fit ergon parameters for those particles, and then use this for creating a new model and then comparisons with other commonly used drag models. And this is basically the outline for the rest of this talk then. So in the previous work I talked about, this is actually as presented even at the 2016 Nettle Multiphase workshop. So this has been going on for quite a while. The various forms of the drag were studied, looking for what is the what's a good functional form, and it was found that what I call here a when-u form, where we have a drag force is equal to a single particle drag times voidage to some exponent, really fit the data being looked at that time quite well. But rather than that exponent being a constant, it was made a function of Reynolds number such that the ergon's drag force is maintained at close pack or at minimum fluidization. And so you see that here is this beta. This, with some simplifications, can be tidied up into the form shown below, where it's really like a logarithmic interpolation. And that, then the inclusion of this exponent n here is new in this work, and in the coming slides to show how this value is obtained. For the data sets, looked at the data sets that had originally used by Wen and Yu, and then added in the data of Jotron from 1952. So the full data sets that were used were all liquid solid data. So we're looking at particulate fluidization here, which included the data from Wen and Yu, Willem and Kwok, Richard and Zaki, Lewis, Julian and Bauer, and then the data of Jotron, which really provided some low Reynolds number liquid fluidized points. And so this was reassembled, a lot of like digitization of plots and transcribing some of the tabulated data. On the right, we see the original plot from Wen and Yu, and in the middle there, the reconstructed. We see here that the voidage error that was calculated for these sets is consistent with the plus or minus 10% that was reported by Wen and Yu. The actual drag force errors, though, are significantly higher, more like plus or minus, let's say 40%. And this makes sense given the exponent on voidage in the Wen and Yu equation. So from these data points, then, I said we carved out any data sets that had a fixed bed region. So in the upper right here, we see what I'm talking about, where this is a bed expansion experiment. We're looking at the pressure drop versus Reynolds number, and below minimum fluidization, we see the pressure drops increasing, and then above that point, then the bed starts to expand. So in those region below minimum fluidization, then we can fit ergon parameters to that. Some of the data just was bed expansion data alone, and that is just included what is called the full data set. So we've got the tuning data set, and which is a subset of the full set here. The ergon parameters that were fit for each of these, for each of the sets in the tuning set here, are presented in this table. See, the ranges of A and B are all kind of consistent within the range of those values that have been reported previously by McDonald for various materials. And it's taking this tuning set then was used to determine the value of n. So in some manipulation of the equations, we're able to get a very nice linear fit to determine n, which was found that around 0.7 is a very nice fit here. And so this value of 0.7 is used in the drag model going forward. Next up then is to see how it does for this set. And talking about here two versions of the model: the tuned, where the individual ergon parameters are used, and then an untuned version where just default values of A equal to 180 and B equal to 1.8 are used. For the tuning set, found that the tuned model did show improvement over the untuned version. And both of these models had lower average error and maximum error than the other drag models that were tested, including the Wen and Yu, which had an average error of 26.6% for the tuning set. Looking at the full data set, where tuning wasn't possible across all those, we're only looking at the untuned version then, and the untuned version as well, in this case, showed a lower average error and maximum error compared to the other drag models that were tested. For looking at the dependencies here on Reynolds number and voidage, for the tuned model here, we've got, really it's a smaller set, so we only got 2 orders of magnitude in Reynolds number, but we see for both Reynolds number and voidage in the tune set, lower errors and really no, say, kind of systematic dependency on Reynolds number or voidage. And same story on the untuned set, now with Reynolds number really spanning 6 orders of magnitude here. And voidage, again, the full range, very low error compared to Wen and Yu, and no really systematic dependencies that are shown. So with that, this brings me to my conclusions. A new drag model here has been fit to some of these foundational data sets and fluidization. The model is a very simple form. It matches the ergon drag model at close pack and the Schiller-Newman drag correlation for a single particle. Does without any tuning, has increased accuracy over commonly used drag models. when ergon coefficients of A of equal to 180 and B equal to 1.8 are used. And as shown, the model can be improved when improved values of the ergon coefficients can be obtained from experimental data. Again, the STRAG model is shown here at the bottom. And with that, happy to take any questions. Thank you.
Thank you for that presentation. Deepak, are there any questions in the chat?
No, I don't see any.
I guess I can lead off and ask, where do you see these types of empirical fits versus kind of the more the ones trained off data sets such as the machine learning or ML-based systems that you're seeing more and more common these days that are just consuming lots of data to spit out a trained model rather than something based on kind of these experimental observations?
That's a really great question. The motivation here is for being able to handle, particle sets that are coming in that are, say it's biomass, or it's just something where we want to have there's maybe some characterization that is available, and want to know how to, get a more accurate drag model for that particular set. I think it's really, this is, I think in a previous presentation said going old school. This is going really old school here. But it is, trying to use the information that we have for experimental. And I think the machine learning models, if we're talking about the subgrid characteristics here, then that's a whole different situation. What we've talked about, or the experimental data that was selected here is all liquid solid. So we're trying to pick data that is most likely to be homogeneously distributed within the system, and be able to exclude any of the subgrid characteristics that would appear and are the target of the subgrid models.
Thank you. I see a question in the chat, and I'll turn over to Deepak.
Yeah. So Will asks why your model is has 2/3 less average error compared to GIDASPO, since that should just be ergon equation for EPG greater than 0.4. Is that just coming from including the blend of Wen and U at EPG less than max pack?
Yeah. So if we look at, there are some structural differences here in the model. So the ergon equation really is only being calculated at the close pack voidage, right? We're not calculating ergon at higher voidages and applying that to that equation, right? So we see FMF there. That is not a function of voidage at anything higher than close pack, and then so really only the voidage dependency comes in that calculation of chi. And so I think that's, I don't know if that's answering the question, but it's really, we're not, ergon, or the GIDASPO, it's ergon up to a certain point, and then Wen and U, trying to have a continuous form that goes between the two, and let these foundational data sets drive what that form should be.
Thanks, James.
Sorry about that. I had to wait for there's a training exercise on site today, and I didn't want anyone to hear what was going on in the background and terrify anybody. It's all make believe, but necessary. I think with that, we'll go ahead and close this session out and let you all turn to your 10-minute breaks. That'll allow the next session to get ready and test their screens if they want. Thanks everyone for participating. If you haven't already done so, please remember to provide PDFs of your slide decks to the Multiphase Workshop email address so they can be archived for the talks. And with that, we will convene in 10 minutes at 10:50 for the next set of talks. While we wait, I see that Roberto, Sarah, and Austin, I believe, are in the presentation. Are Shoma or Andrew Myers around? No.
Sorry, Jordan?
No, I was just trying to see if the first two presenters in the next session are around, Shoma and Andrew. I saw that you were in the chat as well as Austin and Sarah.
Yeah, I don't think I see the first two speakers either in the panel list.
Great. It looks like we do have a full set, so we'll go ahead and get started. This session has been kind of pulled together. It was a bit of a hodgepodge of groups, just kind of seeing who's doing multi-phase fluid modeling on larger scale systems, or how they're using HPC to investigate multi-phase flows, or even in the case of this next talk, how we can use different techniques to kind of further our research in multi-phase flow via feature detection or in situ visualization. And with that, I'll go ahead and turn the floor over to our next presenter.
Okay, thanks, Jordan. So my slides are visible?
Yep, we can see your PowerPoint.
Okay, so now it's full screen, right?
Yep, now we're full screen.
Okay, all right, thanks. Okay, so thanks everyone for attending this talk. So the title of my talk is End-to-End Interactive Feature Analysis in Large-Scale Multi-Phase Flow Simulations Using In-Situ Feature Extraction and Post-Hoc Visual Analytics. So my name is Shoma Datta and I'm an assistant professor at the Indian Institute of Technology, Kanpur, in the Computer Science Department. So this work that I'm presenting here is a joint work with Terry Turton, David Rogers, James Adams from Los Alamos National Lab, Jordan from NETL, and Almgren from LBNL. So I was at Los Alamos National Lab before I joined in my new position, and this is the work that I was doing back there. So when you talk about in situ feature analysis, exploration at the exascale actually can be very challenging. So for the MFIC simulation, we know that the features of interest can be the bubbles or the void regions that are produced when we run the simulation. So on the right hand side, I'm showing one image. So the small cartoon image on the left essentially shows you part of the reactor where the simulation is happening, and then we are focusing on the fluidization bed region where these bubbles generally form. And then on the right hand side, I'm showing rendering of the particle field that it produces, and you can see that there are some low density particle region voids that can be categorized as bubbles, which are the feature of interest that we want to study and extract efficiently from the very large scale particle fields. So now the accurate extraction of these features at an exascale level can be very challenging. So there are two primary reasons. So one is that the complexity of the model physical phenomena essentially grows. And then the other problem is that this bubble features that we are interested in does not necessarily have a precise descriptor. So you cannot just segment or get the void region out from an unstructured particle data. So that makes it somewhat challenging to develop a robust algorithm. So in this particular research, we tried to use distribution-based representation of the particle data, and also tried to use distributions as a representation of a bubble. So we have developed an algorithm, and I'm going to show what we have achieved so far. So the idea is that we can use probability distribution as a feature descriptor. So we do not necessarily need any hard threshold value to define it if you can use a distribution. And then the other thing is that this, when you are trying to find out the region of interest, then we do not have to specify it. We can directly interact in the data and then try to highlight a region. So if this is the one of the time step from the MFIX simulation, then this box region, so this is a 3D data I'm showing the front view. So this is a 3D box that you can build a tool, and then you can make this box move within the data set, and then you place it inside a bubble, and then you specify that this is sort of the region that I'm interested in, because that region is inside the bubble region. So you are not specifying any specific value, you are just picking a region. And then the goal is that using whatever information that we can capture from this, we want to develop an algorithm that can extract this low particle density regions robustly in the in situ environment. So then what we did, we sort of created an intermediate representation from this particle raw particle field as a particle density field. So particle density field, essentially, I'm showing on the second image here. So this particle density field is a scalar field, which essentially says that at every location, roughly the density of the particles. And so you can render the field, and then you still see that particular region that was selected from the raw particle field. And you can collect all the points which fall inside this box. All the points will have some density value that you have computed, because this is a grid. And we take all those density values which are within this box, and then we just create a simple Gaussian representation, the Gaussian distribution. So now what we are trying to say, that this Gaussian is sort of like the template that captures statistically how a bubble can be described without any hard threshold sort of thing in the form of a distribution. So we want to find out regions in the data where distributions are very similar to this particular Gaussian distribution. And so this is the end-to-end pipeline that we have developed. So let's see step by step. So the first step is that assume that the simulation is running in an HPC cluster. So we will access the particle data. And then what we did, we created this density field in situ. And then from that density field, we applied some other steps, some other processing that I will describe. And eventually we sort of get a field like this, which is a new scalar field where the bubbles you can see are very nicely identified. And to capture the dynamics of the particles around every bubble, we also created another new field, a new scalar field, which sort of captures the velocity of the particles, primarily the rising velocity of the particles, in a very small compact format, in a scalar field representation. So this is the raw particle field, but then these two scalar fields are very small. They are just scalar fields, so we don't have to store millions of particles. And we can pick the resolution of these fields, and that sort of indicates how much storage we need. So we generate these two scalar fields in the in situ processing, and then we store them into the disk. That's the next step. So now the in situ processing has been performed, and then we have reduced the size of the data, and then we have only these two scalar fields. Now from that, we show that we can now build an offline interactive visual analytics system that allows you to study the behavior of this bubble, their interaction. You can track the bubble. You essentially can sort of do whatever you want with this bubble feature, so that you understand how the dynamics of the bubbles changes over time, and then how that can impact the actual accuracy of the simulation, and many other things. So let's see how we actually process the data in situ so that we detect such regions. So before we start, so the Gaussian distribution that we are trying to find has been identified in the offline. So you can assume that we have stored some time steps of the data, and then some expert has looked into the data, and then they have identified a region of interest, and we have computed the Gaussian distribution. So then the first step here is that we compute the particle density field that I have already mentioned. How we compute is essentially we create a three-dimensional spatial histogram using the location of the particles. So this process requires some computation and some communication over all the nodes, because the simulation is running in parallel, and you can create a histogram by creating partial histograms at every processor, and then you combine them together. So now you have a 3D histogram that has particle locations, and we essentially convert it into a regular grid data set. So the histogram bins, the bin frequencies now represent what is the density of the particle. So we interpret the bin frequencies, how many particles in a small cell, that essentially gives us the particle density. So the next step is that we create very small clusters, or we partition the data into very small subregions which are homogeneous. So here to do this, we are using an algorithm called simple linear iterative clustering algorithm. So this is essentially a clustering algorithm which is very similar to a k-means clustering, but you can think of this as a local k-means clustering. When it computes the distances, it sort of encompasses its computation only within its neighbors up to certain distance and not computing distance from all the points to all the other points. And that is where the time saving comes, and then this algorithm becomes very fast. So this essentially minimizes the variation of the density values inside every partition. That is the nature of the clustering algorithm. And the distance function that we use here, as shown here, you can see that it has two components, and gamma is the sort of weightage or mixing parameter. So we consider the location of the particles when we between of the cluster to the nearest particle. Then also Vx and density values. So we look at the distance in terms of their locations, and we also see how different the density values are, and then we use that combined using the gamma parameter as a distance function, and we iterate and minimize this distance function to sort of get our clustering. Now the next step is that once you have these clusters, every cluster has a set of points, right? So we collect all those points which are inside every cluster, and we represent that cluster using a Gaussian distribution. So all the points will have a density value. So we color points, we look up their density value, and then we create a Gaussian distribution out of it. So now we have translated this whole particle field into a distribution-based representation of small partitions which are all connected together. And you can see that the partitions are very nicely homogeneous, and then they sort of follow the similarity of the values, and then they kind of get twisted and bent so that you kind of get the boundary of the regions very nicely. So then the next step is that we create, so our goal is that we want to find the distribution that we have shown at the beginning, right? So that's the target distribution, the distribution that is very similar as a bubble region. So now you have a bunch of distributions within this set of clusters, and then you have a target distribution. So you essentially do a matching of the distribution with every cluster's distribution and see that which are the clusters that are very similar with the target distribution that we are trying to find out. And you can use Bhattacharya distance or KL divergence or any other sort of distribution comparison metric that gives you distance between two distributions or similarity between two distributions. And finally, using those distance values, we can normalize all the values, and then we can create a new scalar field where the locations indicate how similar they are with the target distribution that we are trying to find. And that essentially is the scalar field that I'm showing here. So this is one of the output that captures the bubbles. Then the next step is that we use we also compute the particle rise velocity. So in this particular simulation, the x direction is upward. So the bubbles are forming at the downward, and then they go up, and then they kind of, move, they mix with each other, smaller or larger, all those phenomena happens. So the similar idea we applied, we created a 3D histogram using the x velocity component of the particles. And then we converted that the same way we dealt with the density field into a histogram data, and then we convert it to a regular scalar grid. So that is what it looks like on the right. So from this raw particle field, you can see that it sort of captures the movement of the particles, where the high velocity particles are, where the low velocity particles are, from the color. Right. So then this is another scalar field that we also generate, and all of these are happening during the in situ run. And eventually we store this to scalar field. Now, if you think about the storage reduction, then what you see that if we assume 100 time steps for comparison, then if you store all the particle field with the velocity information only and their locations, then it roughly takes about 310 gigabytes. And this particular simulation actually had only a few million particles, not even at the large scale. But only storing the two scalar fields takes about 224 megabytes. So you can see the significant reduction is achieved still preserving the information about the bubbles. We have developed a VTK filter of this whole algorithm that can be deployed in situ using ParaView Catalyst. And we also have a GPU accelerated version using VTK-M library, which will be running on GPU and then primarily developed for the exascale machines that has come online very recently. So here is a very small video that I'll briefly show that, what sort of things that we can do offline. So now everything is happening offline. In situ has been done. We have stored the density field, the bubbles extracted feature field, and then the velocity field also. And now if you build an interactive tool like this, then you can segment the bubbles, you can find out their similarities, you actually can do tracking and a lot of stuff that can be done. So essentially what I'm trying to say that just by using this velocity field and the bubble similarity field that we extracted, you almost do all sorts of analysis, and the size of the data is very, very small. So you can achieve interactive rate when you're trying to explore the simulation that can have, thousands of time steps. So we also have developed some tracking algorithm. So you can see the results here. So essentially you can select a bubble of interest, and then you can, look at the whole 3D field directly, and then you can track that bubble and then understand how it is behaving. So you can just do interaction with the data, and then you sort of see what is going on. So then a little bit about the performance. So we have run one case that has 54 million particles. We have done it at a bigger scale, but then for the purpose of the paper, we only ran a 54 million particle use case. And then we ran it for 1,000 time steps, and then we performed in situ analysis at every 10th time step. So we sort of processed 100 time steps. And then we ran it on 2048 MPI processes. And I'm showing here, segment-wise timing for our in situ algorithm. So density creation, the slick clustering algorithm, and then computing the similarity. And so this is the total in situ computation time. And then this is the in situ IO time. So the total simulation time, you can see that quite high compared to our in situ processing, which is what we generally look for, so that we are not stalling the simulation, but only taking a small fraction of the simulation time. So this essentially shows that we are able to achieve that, but this is all CPU. In GPU, the performance will be even better. And the second table essentially shows that if you don't do in situ, you want to do that. Suppose you have the data stored somehow, but then you want to apply this algorithm offline using the data processed in a standard desktop. So that takes quite a significant amount of time, because you have to load all the particle field, you have to compute density, slick, and all those algorithms. So that roughly amounts to 12 hours that we had found. So all of these timings that's shown on this second table essentially happening in situ. So you can kindly totally get rid of this second table's time that I'm showing, and everything is done in situ. And then after it's done, then you directly can start visualizing and interacting with the data at an interactive rate. So with that, I acknowledge that this was done as part of the ECP project at Los Alamos National Lab, and we have used Oak Ridge's leadership computing facilities. We ran the simulation at Summit to collect all the in situ results. And then also we have used resources at Los Alamos National Lab for developing all the prototypes, the offline methods and everything. So here are some of the papers that we have written together out of this work. So if you are interested, then you can go and look into these two papers. And then if you are interested into looking into the software tool that I have shown, so you can go into this link. And then the code is open source, it's available, you can just download it, and then you can maybe use that for visualization of your own data. So that's all I have. Thanks a lot for listening, and then I can take questions now.
Thank you very much, Shoma. This is very interesting. I'm going to kind of table questions to the chat, so if you want to keep an eye on that, maybe answer some questions. It looks like one from Will just rolled in, and we'll go ahead and move on to our next presenter, Andrew, who will be talking about, let's see, exascale ready tools for particle methods. Thank you again, and we'll turn the floor over to Andrew.
All right, can everyone see my slides and hear me now?
Sure can.
All right, great. Well, yeah, thank you for giving me the opportunity to talk today. I'm going to talk about AMRX and some of the tools that exist in it for building particle simulations, including multi-phase flow simulations like an MFIX EXA. to mention that the PI of the AMRX project is John Bell at Lawrence Berkeley. And I also want to acknowledge up front that you know, a lot of people have contributed ideas and code to the particle tools in AMRX. So I'm giving this presentation, but I just want to acknowledge that a lot of people have contributed over the years. So I'll start by giving just a brief overview of the AMRX framework. So AMRX is a framework for building parallel block structured adaptive mesh refinement applications. It's been developed as part of the exascale computing project. One of the things that it does is it handles parallel communication, domain decomposition, and load balancing, so that application codes have less to deal with in terms of writing MPI code. It includes support for cell, node, face, and edge-centered mesh data, and also particle data, which is what this talk is going to be about. It also includes tools for doing multi-level operations, so flux registers, tagging, and regridding, and things like that. It includes support for embedded boundaries via a cut cell approach. And it also has some native geometric multi-grid solvers for elliptic and parabolic systems. I want to mention, so AMRX is open source and all the development takes place on our GitHub here, and also our documentation is all hosted online as well. This is an overview of some application codes that have been built using the AMRX framework. I don't want to go over all of this in detail, but the points are that it spans a wide range of different scientific domains. So we have cosmology, we have electrodynamics, we have multiphase flow. It also, so a lot of these codes are also part of the exascale computing project, but many of them are not. And the other thing I want to highlight is, so the codes that I've put on in blue there, these are codes that use particles in at least some capacity. So in some cases, these are just passive tracers of like a flow field, but in many cases, they're implementing more complex numerics as well. So this is an overview of the particle functionality in AMRX. So AMRX provides tools for storing and iterating over distributed particle data, so on different MPI ranks, that's associated with an adaptive mesh refinement hierarchy, like the one that I've shown here on the left. There's a flexible data layout that allows users to choose between an array of structs and a struct of array style format, or some combination of the two at compile time. AMRX provides MPI communication routines for common patterns that come up in particle methods, especially particle redistribution and halo exchange. Tools for building and iterating over neighbor lists, tools for particle mesh deposition and interpolation operations, functions for binning, sorting, or partitioning particles, and also parallel reductions and stream compaction operations. I'll go into more detail on all these in a bit. The point I want to highlight here, I guess, is that all this functionality works on NVIDIA, AMD, and Intel GPUs, and also supports OpenMP for CPU-only execution. So the idea is that applications can just have one source without a bunch of if-defs in it or anything like that, and it can be compiled to target all of these different backends in AMRX. And finally, particle methods implemented with AMRX have been scaled up to the full sizes of some of the biggest supercomputers in the world. So Summit, Frontier, Fugaku, and Perlmutter, and I'll share some scaling results in a bit. So this is just going into more detail on all of those points. So the data layout, so there's an AMR hierarchy like this. The particles on each rank are split up by AMR level and then also by the grid that they're on, with an optional tiling level as well. So on a single grid, you can have multiple different particle tiles. On a single one of those tiles, the data is stored as a user-defined mix of array of structs and struct of arrays. So, you know, an array of structs, you'd have like particle XYZ, the XYZ of particle 1, the XYZ of particle 2, etc. Or struct of array is like you would have the X of particle 1, the X of particle 2, the Y of particle 1, the Y of particle 2, and so on. Previously in AMRX, there was a limitation that said the particle positions had to be stored in this array of struct format, but that limitations in recent versions of AMRX has been removed. So now users can just do pure SOA data if they want, which is usually what you want to do for performance on GPU and really on modern CPU architectures like the ARM64 as well. We provide a bunch of tools for doing particle mesh interaction. So if you're doing a simple type of interpolation kernel, like if you just want to do nearest grid point or cloud and cell interpolation, you can just call functions that are already in AMRX without having to write any of that yourself. If you have your own kind of interpolation operation that you'd like to implement, we have a Lambda function interface for handling user-provided interpolation kernels. So if you want to do Gaussian interpolation or implement higher order particle shapes, you can do that, but still use our kind of high-level methods. The necessary parallel communication to do this, so if you have a particle that's kind of at some grid boundaries and it deposits some of its charge onto other grids that might be on other MPI ranks, that stuff is all handled kind of under the hood when you use these routines. We also have support for what we call dual grid. So this is, you have a totally different grid structure for your particles and for like your mesh or fluid data in the simulation, and you can copy back and forth between those two using AMRX communication routines. In terms of the algorithms under the hood, so we use a data duplication strategy for CPU threading, whereas on GPUs, we go back to doing atomics on a global atomics on a per particle basis. So modern GPUs like A100s or the MI200s have very good hardware support for single and double precision floating point atomics. So that turns out to do pretty well. And we also have implementations for GPU that use shared memory versions of this, which can be a win for some, but not all kernels. We also have tools for doing particle-particle interactions. So AMRX includes tools for building and iterating over neighbor lists, for doing DEM style particle-particle interactions like those in MFIX EXA. Essentially, this is where you pre-compute a list of potential interaction partners that can be reused for multiple time steps. And under the hood, this uses the cell list data structure to avoid a direct search over all possible pairs. Again, there's a Lambda function interface where users can sort of specify whether particle 2 belongs in particle 1's neighbor list based on some custom operation. There's support for both half and full neighbor lists, and this is a trade-off that's based on the amount of contention that you get. If you're using a half neighbor list, the whole data structure is smaller, and you don't have to process each pair twice, but you have to use atomics when it comes to updates to force. So there's kind of like a trade-off there. Roberto Porco, who I think we'll be hearing from in a bit, implemented this in MFIX EXA and found that the half list usually performs best on the cases he was looking at and on the hardware he was looking at. In terms of the parallel communication algorithms, so one of the big patterns that comes up with particle methods is redistribution. So this is when you have particles that were on the right MPI rank and place in the AMR hierarchy, and then they move, and now you have to put them back on the right place. So essentially, we have pure GPU implementations of this that can do the whole operation, including taking advantage of GPU-aware MPI implementations on the device. This comes in both local and global flavors, where by local we mean the particles are only moving to neighboring grids, and global means a particle can jump to any other grid in the domain. But both of those versions are in AMRX. And we also have tools for handling subcycling in time, which is something that comes up with adaptive mesh refinement codes. The other big communication pattern that comes up is halo exchange. And this is often needed for particle-particle work. So this is where we have a particle that's on one grid, and there's a nearby particle that's not on the same grid and could be on a different MPI rank. So what we need to do is create ghosted versions of those particles for each one of these grids, and then provide tools for copying data back and forth between the ghosts and the corresponding valid particles. So AMRX also provides that. This also runs fully on the device if you're targeting GPU execution. And there's also a recent optimization involving culling particles that are in the neighborhood of a grid, but don't actually contribute to a particle's neighbor list. So Kinji Wang recently implemented that optimization in InfixX as well. So these are some scaling results. So on the left here, this is from Summit, but this is a particle redistribution benchmark that we have. So this is basically just, we make up some particles and we move them around randomly so that they're changing cells a lot. And then we call the operation that puts them back on the right MPI rank after they move. So this is showing scaling for both single level in blue and with mesh refinement in red, going up to kind of the dotted red line here is the full size of Summit. So we get pretty decent weak scaling going up to the full machine on Summit on this benchmark. And then on the right, what I'm showing is this is actually from an AMRX based application code WarpX. This is another particle using code, but this basically stresses the particle mesh functionality in AMRX, and then also the particle redistribution as well. But they're able to take, they're saying they're able to compile their code and run it on basically the full machines of Frontier, Fugaku, Summit, and Perlmutter. And they see pretty decent weak scaling in all those cases. I think about 80-something% at the full size of Frontier. So we also include tools for binning, sorting, and partitioning particles. By binning, I mean computing a permutation array that would put the particles in some order. And then by sorting, I mean taking that permutation array and then actually reordering the particle data in memory based on it. And then partition is weaker than sort. It's just sort of splitting the particles into two groups. So all of this is implemented in terms of a counting sort, which in turn depends on having a good implementation of a prefix scan. So we use the vendor implementations whenever possible and kind of fall back onto the AMRX native implementation when we have to. So these tools are used internally all the time, so as part of particle redistribution and neighbor list construction. Or they're also used to implement application-specific physics modules like binary collisions or algorithmic options, so gather and deposit buffers for mesh refinement. If you want particles that are near a coarse-fine boundary to do something different than those that are not, then that partition capability is pretty useful. And again, these can be used to sort particles in kind of arbitrary ways. So you can sort by cell, you can sort by groups of multiple cells, you can sort by slices, or you can pass in a custom function that'll do pretty much whatever you want. So as an example of when that's useful, so one place we do that internally in AMRX is to improve particle mesh performance. So this is taking a particle mesh benchmark where we give the particles a large velocity so that they're frequently changing cells. And what happens after a while is the particles get very out of order in memory. And then resorting them and putting them back in that cell order can make a huge difference in the time it takes to do particle mesh deposition. So here, the difference between sorting by cell every time step versus never resorting the particles is about a factor of 8 in this benchmark that we looked at. And if you do a roofline analysis, you can see that the reason for that is basically that when you resort the particles frequently, you're basically getting a lot of reuse in the L2 cache that you're not getting when it's just disordered. And another thing I want to highlight here is like if you have a lot of particles per cell, you don't want to put all the particles in the same cell next to each other in memory. What you want to do is say there's 2 particles per cell. You want to take 1 from each cell, put all those next to each other, and then take the next one from each cell and put all those next to each other. And that way you're still getting good data locality, but you're also reducing the amount of contention in the atomics because adjacent threads aren't trying to write to exactly the same cells for a set of particles. I'll move over these next couple slides quickly because I think I'm at my 15 minutes, but we have tools for doing reductions over particle data as well that work both on GPU and CPU. So if you want to compute, you know, the maximum particle energy over the whole domain, you can do that in a performance portable way. And we also have stream compaction, like filter, transform operations that you can call on a particle data. And one thing this is useful for is to implement processes where one particle conditionally creates one or more other particles, possibly of a different type. So this can be used to implement ionization. It can be used to implement particle splitting. So sometimes when a particle goes from a coarse to a fine level, you want to create 4 other particles or something like that on the fine level. It can be used to implement QED processes like pair production and quantum synchrotron radiation. And these things can be triggered, say, in regions where the electromagnetic fields are high, or they can be triggered when a particle interacts with one of the embedded boundary walls, for example. So yeah, that's an overview of the tools that are available in AMRX for doing particle simulations. Yeah, thank you again for giving me the opportunity to speak, and I'd be happy to answer any questions at this time.
Thanks, Andrew. This work is fantastic for anybody who's ever had to write or maintain this stuff just to do the physics that they want to do, to have someone, or I guess the team of people that you all at AMRX do to manage some of this stuff is fantastic, because it lets us focus on more of that sciencey side of things, or physics side of things, I should say. I do have a question about, you said it has the internal capability to do its interpolation or deposition. Does that take into account the embedded boundary, or is that on kind of what we'll call a clean grid that's fully regular?
So for the canned routines that exist in AMRX, you wouldn't be able to. You would have to write that. So you wouldn't be able to use the canned routines in AMRX if you have the embedded boundary geometries, unfortunately.
Okay, I think that answers Roberto's nice question. We both thought, it'd be nice to offload that to you all, but we have a lot of custom routines to work around those embedded boundaries for geometries. So.
I would say that in practice, so most of the ECP projects have found it useful to implement their own version of, looping over the grids and depositing the particles in their own way rather than using these built-in routines. Mm-hmm. But yeah, an example of a code that uses the built-in routines is this, this neutrino transport code EMU uses those, and they were able to get that up and going relatively quickly. And then it ended up, the deposition time wasn't the bottleneck for them, so it wasn't worth it for them to re-implement those loops themselves. Mm-hmm. Yeah.
Perfect. All right. Well, if you'd like to keep an eye on the chat to see if any additional questions come through, we'll go ahead and get Roberto queued up here. I believe he's next.
Okay.
Thank you very much. So this is our second Roberto of the day. He's going to talk about some of the MFIX-EXA CFD DEM simulations, or some of the work that's been done recently in the development of MFIX-EXA. Roberto, you've got 20 minutes. I'll keep an eye on the clock for you, and I'll poke you if you get too close to the time limit. We're on a tight schedule today, so I'll turn the floor over to you.
Thank you, Jordan, and thank you everyone for the opportunity of presenting today. I'm Roberto Porcu. I'm a data scientist at Battelle and an NETL support contractor for the MFIX-EXA project. Today I will present our work titled MFIX-EXA CFD DEM Simulations of Thermodynamics and Chemical Reactions in Multiphase Flows. This is a disclaimer. It's mandatory to put in our presentations, and I would also like to thank and acknowledge the MFIX-EXA team, our members at NETL, Drs. Jordan Moser, William Fulmer, and Deepak Rangarajan, And our collaborators at Lawrence Berkeley National Lab, Doctors Anne Almgren, John Bell, Aaron Latanzi, Andrew Myers, Andy Nonaka, and Wei-Chan Zhang. So the problem that we want to address with MFIX-AXA project is to help the research and development of the design of industrial scale CLRs, the chemical looping reactors. As you can see on the left, a chemical looping reactor is a reactor. This one on the left is the one we have at NETL in Morgantown. It's a 50 kilowatt hot flow chemical looping reactor. The chemical looping reactor is a reactor to produce energy from fossil fuels combustion. But unlike standard power plants, in a CLR, the CO2 is mixed only with water vapor. This makes it easier to capture and sequestrate CO2 before it is emitted in the atmosphere. And as you can see on the right, the simplified structure of a chemical looping reactor. Inside, we have a mixture of gas and solids. Solids are metal beds that transport oxygen in the loop. So in general, this is a multi-phase problem. The problem is that in general, scaling up these systems to industrial scale proved to be not as efficient as we would like them to be. So this motivated the need for simulations and to understand what is going on and how we could improve the efficiency of chemical looping reactors. So back in 2016, the US Department of Energy created the Exascale Computing Project, which was a project to usher the nation to the next generation exascale computing hardware. Luckily, a team led by NETL and the Lawrence Berkeley National Lab was selected to develop exascale capable software for CFD-DM applications, and that's how MFIX-AXA project was born. Back in 2017, we were able to simulate a cold flow chemical looping reactor with a few million particles, but the code was taking quite a good amount of time to get to the solution. We arrived at today with our code able to simulate the NETL 50 kilowatt chemical looping reactor in counting more or less 5 billion particles in a much shorter time to the solution. So as you can imagine, simulating this problem is computationally expensive. And as I said, this was allowed by the fact that MFIX-AXA is capable of running on the next generation high performance computing supercomputers. We have developed our code on pre-exascale supercomputers such as Summit, Perlmutter, and Polaris. And nowadays we are able to run, we were given access to the exascale supercomputers, in particular Sunspot and Crusher, which had the same architecture as the Aurora and Frontier, that are actually the exascale supercomputers. They are just smaller. And we are also actually able to build and run on Frontier. And so MFIX-AXA in the main, let's say, in few main characteristics is a high-performance computing multi-phase flow solver, is written in C++, implements a hybrid parallelism, and is empowered by MREX, which is a high-performance computing library developed at the Lawrence Berkeley National Lab. When I say hybrid parallelism, I mean that we combine a multitasking and a multi-threading parallelism. And the multi-threading parallelism in general is represented by the fact that we offload the work to, whenever it's possible, we offload the work to GPUs, and either NVIDIA, AMD, or Intel architecture are supported by MFIX-AXA. So going into the specifics of the characteristics of our fluid phase solver, our computational domain is characterized by a multi-level, multi-grade approach. So we have several levels of refinement, and on each level we have several grids each grid can be given to a different MPI task to parallelize the work. And the complex geometries in MFIX-Hexa are modeled through an embedded boundaries approach. And we also support grid pruning, so we can remove all the grids that where there is no flow to reduce the computational cost and the memory required for the simulation. And the complex geometries are generated from a user-provided constructive solid geometry file that can be generated by the user through any common CAD software, for example, OpenSCAD. So it's pretty easy to generate complex geometry to give to the simulation. And as our fluid solver characteristics, the main ones are that we use a particles unresolved approach. So we first advance the fluid, keeping the particles unchanged, and then after one step for the fluid phase update, we solve particles through substepping. We implement a modern low Mach number approximate projection method with a Godunov time advancing scheme. So we have a second order approximation both in space and time, and we have all the fluid variables are self-centered, but only the nodal is also only the pressure is nodal. We can solve enthalpy, species equations, and heterogeneous chemical reactions that can be switched on and off more or less independently from each other. And we give the opportunity to use either an incompressible fluid constraint or an ideal gas equation of state constraint. And for the linear problems to be solved, for the linear algebra problems, we can use AMOREX internal solvers or Hyper solvers. For what concerns the solid phase instead, we can either solve DM particles or peak parcels. In either cases, the solid phase data is stored in a struct of arrays layout because we observed that this improves the coalescence of the accesses to the GPU global memory, which means also improved performance. So we have an Eulerian approach for the fluid phase and a Lagrangian approach for the particles. So to couple the two phases, we implemented depositions and interpolation kernels. When a particle is in a regular stencil, our kernels are linear. But when the particle is in an irregular stencil, which means that the stencil contains embedded boundaries, then we have nonlinear kernels. So particle quantities are deposited to the fluid mesh, and the fluid quantities are interpolated to the particle Lagrangian positions. For what concerns short-range forces acting on particles instead, so we have for particle wall collisions, these collisions are computed by representing the boundaries through a level set function. For DM particle-particle collisions, we use a soft sphere spring dashboard model, which means that for each particle we check collisions only with the other particles that are within a neighborhood to reduce, of course, the computational cost. And for the peak model, we use an iterative solid stress model to minimize the overpacking. And so instead, for what concerns the initial conditions, we have developed a bootstrapping initial condition approach, meaning that we are a peak to DM conversion method. Because what we saw is that when you set the initial condition, read the code, there is an initial transient regime which can be very long, so time consuming and energy consuming. So we came up with an algorithm to convert an initial peak run into a DM run that can be after the transient is finished. So the algorithms more or less works like this. We first run a peak simulation until the transient regime is over. When this is over, we save the current status in a checkpoint file and stop the simulation. Then this checkpoint file is converted in a full CFD-DM checkpoint data. In our case, for example, we were able to get 800 million active control volumes for the fluid phase and more than 5 billion particles. And all of this stored in a checkpoint file that is then used to restart a full CFD-DM run. And finally, after when we reach the several seconds of simulations, we visualized the results. MFIX-Hexa provides the data reduction methods in the form of user monitors and also supports in situ visualization with Ascent. So now we present some results that we have obtained for verification and validation of MFIX-Hexa. First, this is so we first benchmarked the code against analytical solution that was first published by Schumann back in 1929. So what he did was to get a monodimensional transient heat conduction packet beds problem, and he was able to provide an analytical solution. And later, more recently, Salehi extended this work by using Laplace transform, and he was able to include in this analytical solution also a uniform volumetric heat sources for the particle phase. And so he was able to provide an analytical solution for these type of problems. We benchmarked our code against this problem. Our code, of course, is three-dimensional. In our case, it was a three-dimensional code, three-dimensional simulations. We used three different configurations for the uniform volumetric heat source. We considered a strong source, a strong sink, and a weak sink. In all of the cases, the particles are held fixed in the domain. We have walls on two directions, and in the other direction, we have a mass inflow and pressure outflow boundary conditions. At the beginning, particles and fluid inside the domain have the same temperature, that is 300 Kelvin, and at the mass inflow, there is a flow of gas at 330 Kelvin. So as the gas enters the domain, as the gas enters the domain, we have a thermal step that propagates throughout the domain. So in all the three different simulations, we saw a very good agreement between our code and the analytical solution. And then we also, as a verification test, we tried the wet bulb problem. In this case, a water droplet is suspended in a humidified airstream. The droplet is modeled as a particle and is held fixed in the center of the domain. And at the beginning, both the particle and the airstream have the same temperature. And we considered two cases, at evaporation and a condensation test. In the evaporation, mass is transferred from the droplet to the airstream, while in the condensation, mass transferred from the airstream to through the droplet. For the evaporation case, we didn't have any experimental data, but we confronted the results to the work done by Jordan in his paper in 2015, and we got very good agreement. For the condensation test, there are some experimental data. You can see that the profile of the temperature of the droplet over the time is in quite good agreement with the experimental data. And the results in this case are also in agreement with what Jordan observed in his previous work, I think using MFIX. So for what concerns instead validation tests, we considered a bench scale fluid acid bed In this bench case, the problem is stuck in this way. So we have glass beds that are heated in an oven, and then they are discharged in a bed, and they're immediately fluidized by nitrogen gas. That is, so the particles are heated to 363 Kelvin, while the jet of nitrogen gas is at 293 Kelvin. So as the bed fluidizes, the particles cool down, and you can see that in dots are the experimental results obtained by infrared imaging, while and the temperature is the average temperature in the whole domain of the particles. Instead, the solid lines are our numerical results. Also, in our case, we are averaging the particles temperature, and we are showing here two cases. One is a lighter bed mass of 75 grams, and the other one is a 125 grams bed mass. And in both cases, we have different velocities for the inlet of the gas. So each color represents a different velocity of the gas injected in the fluidized bed. And in all these situations, we also observed as well good agreement between the numerical results and the experimental data. And finally, I wanted to show some performance analysis. Here we performed some weak scaling analysis of our code. So in this case, we got a problem where we have periodic conditions in the two directions, and in the other direction, we have mass inflow and pressure outflow boundary conditions. So the computational domain is split into 8 grids, and each grid has 64 to the cube cells. In each cell, we have 8 particles, and we considered, for us, it's a complete physics simulation in the sense that we have chemical, we have 10 chemical species, 7 for the fluid and 3 for the solids. And we also have we are simulating 4 chemical reactions. And so as you can see, we are we go from we weekly scale the problem from 8 grids up to 1024. We have each grid is assigned to 1 MPI task, and for each MPI task, we have 1 GPU, and the tests were run on Summit and Crusher. On Summit, we have Intel Power 9 CPUs and NVIDIA P100 GPUs, while on Crusher, we have AMD EPYC CPUs and AMD MI250X GPUs. Each of them contains 2 graphic compute dies. So in both cases and in both architectures, we observed very good scaling results, which means that show that NFIX is able to maintain good performance scalability both on pre-exascale and exascale architectures. And so that finally, I would like to thank you everyone for giving me the possibility to present my work. And if there is any question, please, I'm available to answer.
Just under the wire, Roberto. Thank you. We're going to go ahead and table questions in the interest of time. Keep an eye on the chat there to see if anything comes through. And with that, we will go ahead and move on to our next presenter. We're turning back to the material point method, and this time we're going to look at it for manufacturing simulations. With that, I'll turn it over to Austin. Thank you. We see your screen.
All right, can you hear me, Jordan?
And I hear you.
All right, fantastic. So let's get right into it. So yeah, as Jordan had mentioned, today my talk is on Picasso MPM. So this is the code that myself, Sam Reeve, Kwee-Tae Chong, Lance Bullerwell, and Stuart Slattery have been developing for the last couple years as a material point method code specifically kind of written for performing additive manufacturing simulations. And I think kind of compared to the previous talks, from Andrew and Roberto on AMRX-based codes, hopefully this talk gives some of us kind of an alternative viewpoint of a parallel and similar software stack of kind of achieving the same kinds of scalable and performant codes for simulating these kinds of problems on similar hardware. So just a quick overview. I'm going to talk about EXA-AM and kind of where that positions our code Picasso NPM kind of in a broader workflow. And then I'll kind of briefly talk about the software stack on which Picasso NPM is built, which is, in our case, on top of a particle library we call Cabana, and also on which is it's also built on Cocos, which provides our performance portability across architectures. And then we have kind of an intermediate library that we call, Picasso, which kind of provides PIC-specific algorithms, but which are general enough for which we build an NPM code, but which it can be used for other applications. And then I'd like to dedicate some part of the talk on specific physics that we have implemented in Picasso NPM. So specifically for dealing with this additive manufacturing problem of laser powder bed fusion. So this is a coupled thermomechanics problem that deals with phase change, lots of different physics. And then I'm going to show some examples of Picasso NPM, kind of demonstrating more in a unit testing fashion each of the specific components of the physics that we've implemented thus far, some brief performance results and some strong and weak scalings, and then a summary and some future work. So as I've mentioned, Picasso NPM is this code that we've developed that's really targeting this so-called laser powder bed fusion process, and I'm sure some of you are familiar with this, but essentially, we have a powder layer of different metals. In this case, I think this video is from Badera and others in Acta Materialia for a stainless steel powder bed. And you have some laser that tracks back and forth, essentially. This is, I think, a 300-watt fiber laser that melts the powder, to produce a part. And during this process, there's lots of physics. There's phase change from the solid powder to liquid melt pools, along with metal vapor plumes from powder particles that may become entrained inside the vapor. There's surface tension effects for the melt pool flows, and so it's kind of a really complicated multi-phase flow problem for which NPM we think is a pretty well suited approach to being able to throw high enough resolution at this and at large enough scale to resolve the physics for the melt pool specifically. So, I've mentioned here that this is a kind of a coupled thermal mechanical problem, and we've taken this so-called enthalpy formulation to kind of naturally handle phase changes. But we're interested in using our Picasso NPM code to kind of probe and look at keyhole formation in particular, and this is essentially where the laser power is sufficiently high enough to where the melt pool throughout the track, it essentially forms these keyholes that can be detrimental, right, to the quality of the part that's produced. In our case, however, we don't explicitly consider vapor. Really, we're more interested in just doing a fully resolved powder bed simulation that, similar to some of the DEM talks, that we've seen, model individual powder particles with a size and shape dispersion, and then also throw laser ray tracing while we're at it, using our points infrastructure from Cabana. And so the next slide, I'm going to talk about then where this code Picasso NPM sits as part of the broader EXA-AM workflow. So I think here on the next slide, Picasso NPM is, we can start from the bottom left and kind of circle counterclockwise. So the idea is to have a workflow that can simulate a macro scale part. And for instance, looking at the Diablo FEM code, this is showing us an example part from NIST, which is kind of this challenge problem to show how a laser powder bed fusion part is created, but then kind of going down the scales in simulating certain aspects of this problem, moving over to OpenFOAM as a finite volume code for doing a continuum simulation of a smaller scale of just the melt pool, heat transport, and fluid dynamics. But then maybe going even further down and looking at the cellular automata with ExaCA for actually looking at the solidified grain structures as these as the melt pool resolidifies, and then looking at the micro scale, with crystal plasticity models of the mechanical properties, and then kind of iterating on that, feeding back into the large part scale, macro scale simulation with improved constitutive properties. So Picasso MPM is, we're trying to target kind of not as a replacement, but at least as an additional numerical tool for validating the high fidelity physics from the finite volume and potentially the CA parts of this workflow, such that we can simulate the melt pool heat transport, the fluid dynamics of the melt pool, including the surface deformation. And then, as I mentioned, actually having the scale to throw at this to do explicit powder modeling of the powder bed. And so I'll get into the software stack, and that's kind of, I think, what I only have time really to talk about. But versus AMRX, I think we'll see some parallels here. At least has been more illuminating for me. Is that we have a particle library of algorithms, data structures, motifs, essentially for dealing with common things that you do with particle codes, particle mesh codes, Cabana. And Cabana provides these flexible particle data layouts. But Cabana, of course, is built on top of Cocos, which provides on-node performance portable targeting of different systems, be it through OpenMP, CUDA, HIP, and SYCL. And in terms of doing particle searching and neighbor searching, we have other dependencies such as ArborX, and then if we're doing any types of linear solves, that we have Hyper also as a dependency. And so kind of the first stab that we took at this was a proxy app called ExaMPM, or Cabana MPM, if you want to call it that was built directly on Cabana. And this was kind of demonstrating, hey, this is an NPM code that we can use just using Cabana alone. This is kind of a proof of principle. But then later development focused on extracting some common features of pick codes into this Picasso library, so this performance portable pick algorithms, which kind of sits now between Cabana and finally the app that I'm talking about today, Picasso MPM. So let's see if I can move on here. So as I've mentioned, Cabana is our particle library, and there are many parallels, I believe, as we've seen Andrew discuss with AMRX, but essentially lots of proxy applications and application partners use and rely on Cabana. And Cabana is developed, as I should mention, under the so-called Co-Design Center for Particle Applications, so COPA. And so, besides MPM and PIC for short-range simulations, it provides features for doing long-range interactions, such as ExaSky for in-body gravitational, results, and also looking at self-consistent field solves for QMD, or maybe a hybrid of short and long-range interactions for for MD type simulations. And then kind of sitting kind of on the other end of the spectrum is pick methods for, say, fusion applications with Fusion WDM. But kind of honing in on what I'm talking about today is ExaAM being an additive manufacturing focused project that is using MPM, which is primarily consists of particle grid and short range particle interactions. And so this is kind of a brief overview of what Cabana can provide, but I'll just kind of go through this, just skip through this quickly, that we have both what we call a core library and a structured grid library, Kahita, and that's probably going to go away at some point namespace wise. But the relevant features of Cabana are that, yes, we need particle neighbor parallelism. We support things like particle migration across ranks. And then the grid components of MPM is that we need grid parallelism, Halo exchange for exchanging grid data, and then very importantly for MPM, particle grid interpolations, and then depositions, as I believe is what I've heard the feature called for AMRX. And so, other things including load balancing and sparse grids, but some of this is still work in progress. So I'll quickly now jump into Picasso as the PIC library, and then finally our MPM code, Picasso MPM. This is kind of like a $1 million rendering of a proxy example problem for a tracked powder bed laser ray tracing simulation. But very quickly, MPM, right, is involving material points that are kind of shown as these dark circles, and then we have a background Eulerian mesh, and you can actually view it as kind of like an updated Lagrangian algorithm where you do P to G interpolations from particle data to grid nodes to then essentially update the grid through a field solve on the grid. But then really the grid doesn't move, it snaps back in the form of a convective step, and then you want to reinterpolate or deposit information from the grid back to the particles in the form of a GDP. And so those are essentially, the ingredients of an NPM code. Picasso, as I've mentioned, is this interlayer, right? So it provides us the facilities to do interpolation with varying bases, linear hat functions, B-splines, as well as kind of abstractions for managing our fields on the grids and particles. And then we can also do batch linear algebra operations with higher order tensors for some of the solid mechanics. And that's been kind of recent work, as well as more advanced, more recent flavors of NPM, including affine pick and polypick methods, right, that are a little bit more involved, than just doing like flip interpolations of the velocity, right? And then, kind of importantly, that I want to show is we have this level set utility to generate free surfaces from our material point particles. And so, Picasso NPM, it's a couple thermal momentum surface, single velocity, explicit flow NPM solver, where we have a latent enthalpy model for phase change. And I'll kind of show really quickly some surface physics that we've incorporated to be able to do surface tension with some fluid flow problems. And then I've already really mentioned how these components use Cabana, so I don't think I need to spend too much more time on that. But here's the model equation system for NPM, just very briefly, in the interest of time. We're solving an energy equation. We have a volume fraction on material points, so alpha is what we're calling it here, but this is an enthalpy formulation. So based on the current energy on the particle determines its phase. And so, we can discretize this into a weak form and then perform NPM through the P to G interpolations to essentially get the enthalpies on particles as well as the momentum on particles. And so we'll have separate terms for internal forces on particles and body forces as well. And then kind of interestingly, that I wanted to point out is that we also have implemented some models for surface tension. And so these models were taken from David Hyde and others, Fanfu, for consistent angular momentum preserving formulations of surface tension. So, we have some surface tension energy potential, and then essentially similar to computing gradients, we can take tensor gradients on our material points to compute effective surface tension forces on material points. So combined with these two different types of physics, kind of the anatomy of a time step is that we have P to Gs that are called through Picasso to interpolate energy and velocity onto the background grid. Then we do updating temperatures and velocities on the grid, and then we compute gradients of those quantities on material points, and then we invoke the constitutive model. Constitutive models for stress or energy models on the particle. And then we do a update for energy and momentum, and then we apply boundary conditions both on the grid and on particles directly, as you'll see for surfaces. And then we do a final G to P after we've done this grid update. And under the hood, it's calling SIMD parallel fours and grid parallel fours that are, again, abstractions for doing these parallel loops. So this is kind of showing how we generate surface particles on our NPM points. We essentially use the level set facilities that I mentioned that we have in Picasso to create meshes using a marching cubes algorithm. And from the marching cubes mesh, we then seed that mesh with more material points. So we have material points on that mesh, and then we have kind of very simple problems here that show the surface mesh that is changing because we have surface tension working correctly, for instance, an oscillating cube. That kind of, is showing us that we have these additional terms ready to go from Marangoni convection. And so another problem that is kind of showing the effective phase change of boundary conditions is this melting cube, or, our variant of the dam break problem, kind of showing this viscoelastic liquid forming from the melting of this ice-like cube. And then something that's getting a little closer to the spot melt is then actually using liquid metal parameters for the so-called droplet solidifying on a chilled surface. And this is kind of showing us side-by-side views of starting off with a liquid droplet that's falling onto a chilled surface and then solidifying from the bottom, and then showing us kind of the interior particles, or rather the surface particles and the interior particles that we use for NPM. And then our current work is then applying all of that to a spot melt problem that's trying to look at the effects of laser power on keyhole formation and dynamics. And so this is from a little bit earlier this year. Unfortunately, I didn't have time to get this approved for the talk, but this is essentially showing us that we have the phase change effect of a laser boundary condition that's impinging on the top of a metal surface comprised of material points and inducing this phase change, and then kind of showing the side view of a formation of a keyhole with this efficient laser power. And so we're kind of happy with this preliminary result, but of course, getting closer to simulating the full problem of like a laser tracked, laser powder bed fusion process I showed on the first slide, we can implement moving boundary conditions to kind of get closer to that. And so just very quickly, as people have mentioned, we're still guided by performance, trying to ensure that we have as much performance on our existing machines here at Oak Ridge and on OLCF, so on Summit and Crusher, as well as Frontier. This is kind of showing a brief breakdown of the kernels that we use in the NPM code for the thermals and mechanical solves, as well as the surface solves. For, in this particular case, 9 million grid points and 250 million particles on a single node of Crusher. And so, it's kind of distributed everywhere here, but kind of showing that, the surface is essentially a big chunk of this because of the search that we use with ArborX to do ray tracing with particles and free surfaces. And then this is showing some typical size scalings for representative kernels. In our case, right, the P to Gs, the particle to grid for the divergence of the stress, and the grid to particles on the velocities for different grid sizes, and then particle per cell counts. So this is kind of showing, expected scalings for larger system sizes for P to G and G to P results. But kind of the major point here is that P to Gs really do account for a large portion of the timings in our simulation. And then finally, we did a very brief, strong, if you want to call it this, a strong and weak scaling result on Crusher with 1 in 10 nodes that's running this affine pick interpolation, so a little bit more computationally heavy, showing, desirable, strong scaling results for, I think, a 330 million particle system on 1 in 10 nodes, as well as weak scaling results from a 3 million particle system up to 300 million particles. And so in summary, this talk was just to kind of show that Picasso NPM is this other code that's a high fidelity multiphysics NPM application targeting AM processes, but kind of interestingly, I think, for this session, we're built on the Cabana library and Picasso and ArborX libraries. And so what we'd like to kind of wrap this work up is to have good and experimental comparisons with a team at UTK for comparing the melt pool dynamics and the keyhole formation, as well as some open foam finite volume simulations for doing DNS. And we're currently working on implementing implicit NPM, some additional optimizations using sparse grids, and then laser ray tracing for explicit laser tracking. So that's all I have, and I'll be happy to take questions.
Thank you very much. This is a very interesting talk. I'll pass off here to Deepak to let him read any questions that have accumulated in the chat. But point out for the audience who hasn't noticed that this is Cabana developed under Copa. So Copa Cabana with that one again. So with that, I'll pass off to Deepak.
I see one question from Andrew Myers. Hi, Austin. Thanks for a very interesting talk. I was wondering if Picasso NPM takes advantage of the ray of structive array feature in Cabana. If so, do you know how much better the best stride size performs over pure structive arrays?
Yeah, so that's a good question, Andrew. I do know that our particle lists that we have in our Picasso library as the interlayer, those are wrapping AOSOAs in Cabana. And the stride length, I think, I haven't actually looked in a while at what the default stride lengths are that Cabana uses, for each different backend. But kind of the assumption there is that it is optimized for each of the architectures. Now, that said, that is something that we ought to look at. On the other hand, just trying structive arrays, I can't speak really to that. I don't think that, at least myself, I'm not sure if anyone else on the team has, but I'm not sure if we've directly made the comparison between AOSOAs versus SOAs. using Cabana, right? For the NPM code, at least. But that is something that I think that we could be wise to look at. Yeah.
All right. Thank you again very much for the presentation. If you don't mind keeping an eye on the chat for any additional questions that might roll in. And with that, we're going to move on to our next presenter and the last for this session. Sarah, she's going to talk to us about compact closures for multi-phase RANs. And with that, we'll turn over to Sarah. Thank you.
All right. Can you guys all see my screen and hear me?
We see and hear you.
Okay, great. So thank you, first of all, for the invitation to come give this talk. Like Jordan mentioned, I'm going to be talking about some methods that I've been working on to identify essentially compact closures for multi-phase RANS equations, specifically for strongly coupled gas-solid flows. So as I'm sure this audience already very well knows, gas-solid flows are pretty much anywhere you look. But this work that we've done has really focused on the context of fluidized bed reactors, specifically in the riser portion of these systems. And so these systems are very challenging for a number of reasons, but a key reason is that the huge amount of length and timescales that are present, and the fact that what's happening at the micro scale actually will impact what's happening at macro scale behavior quantities that we care about for example, reactor type systems. So what I mean by this here is the physics at the particle, wakes past particles, particle collisions, surface reactions, phase change, heat transfer, all that good stuff. What's happening down at that scale is actually cascading up to the macro scale. So this makes it particularly challenging. And it's also a real big departure from kind of what we think of in terms of turbulence modeling from the classical single phase side of things, where the single phase representation is shown in the kind of grayscale here on this plot, where we traditionally understand that energy is produced at the large scale and cascades down to the micro scale where it's dissipated. As soon as we inject particles into a gaseous system, we see that we have actually production of energy at the micro scale that can flow upward to the macro scale. So this is one of the key reasons why a lot of the work that extends modeling strategies that we're used to using from the last 100 years based on single phase turbulence closures, those things really have a hard time extending to multi-phase flows. In addition, single phase turbulence generally is characterized by a relatively small parameter space. We have the Reynolds number, which we all know and love. But as soon as you shift into a particle-laden turbulence sort of framework, the parameter space becomes much larger, and I haven't even shown all of them here. This is just an example. So in addition to our fluids Reynolds number, we also have a particle Reynolds number, a Stokes number, density ratio, mass loading, volume fraction, ratio of length scales, and on and on. And so when we think about how we do computational simulations of these types of flows, there's different strategies across the different scales, right? So we have this wide range of time and length scales. And at the micro scale, we have particle resolved DNS. This fully resolves our hydrodynamics and heat transfer, which is great, but it's limited by the number of particles that we can simulate in these systems based on our current computational abilities. So it's not tractable, of course, to do a PRDNS simulation of an entire industrial scale reactor, but these simulations are really useful for informing models for how momentum and heat is transferred between the phases, kind of at the scale of the particle. And so when we use these models for momentum and heat transfer, we can kind of sort of like leapfrog up to the mesoscale and do simulations such as Euler-Lagrange simulations where we're resolving interparticle contact, but we use mass momentum in heat transfer models to represent what's happening essentially at the subgrid scale around individual particles. And this allows us to simulate configurations on the order of hundreds of millions of particles, probably more than that even now. But then the idea is just like we used our PRDNS data to inform models for mesoscale simulations. What I've been looking at is using mesoscale simulations to inform closures for the multiphase RANS equations. So for macro scale type equations that we would like to use. Okay, so if we want to simulate industrial scale systems, we of course need improved models. There's a much heavier reliance on models as you scale up these systems. And kind of the real prize that I've been chasing, and I think many of us have been too, is to develop closures that are accurate across different regimes and different scales for multi-phase systems. Okay, so the system that I studied in this particular example is a fairly simple configuration where essentially what I'm looking at is the fully developed interior region of a riser. So this is away from a transition region, and it's also away from near wall effects. So, and I'll talk about the configuration in a little bit more detail in a second. But this was chosen because it's very simple, but two-way coupling still drives the turbulence. And it is related to what we see in the inside of a circulating fluidized bed reactor in the riser. And the goal here is to determine if we can learn interpretable, accurate models for multi-phase flow conditions that are also robust to challenges from modeling, such as having sparse training data and that sort of thing. Okay, so in this configuration, it's a triply periodic domain. The initial conditions are that the gas is quiescent and particles are randomly distributed, as you can kind of see here with this staticky looking picture. And then the particles are allowed to fall under gravity. They spontaneously form clusters. And then the parameters of both the phases are shown here. We studied a density ratio of 1,000. Particle diameter is, the particles are spherical and have a uniform diameter of 90 micron. And then we adjusted the gravity in our simulations to target different particle Reynolds numbers, so ranging from 0.8 to 8. This should be meters per second squared. And then also we considered 3 different volume fractions. So this represents 9 simulations in total. So 3 different particle Reynolds numbers via gravity, and then 3 different volume fractions. And then as a consequence of that, 3 different mass loadings. We can calculate a characteristic cluster length based on a particle settling time derived from Stokes settling. And so we ensured that our domain was fully developed, or I'm sorry, our simulation was not domain dependent by setting the domain length to being 32 times the characteristic cluster length. And then, as I said before, gravity is changing our particle Reynolds number. So we have 3 particle Reynolds numbers represented here. And so these parameters were chosen with fluidized bed conditions in mind. And we solved these simulations using in-house code NGA, which is fully conservative, finite volume, DNS LES code. Semi-implicit Crank-Nicholson is used for time advancement. The particles are treated in a Lagrangian manner, so position and velocity is calculated with Newton's second law. We used a soft sphere collisional model with a coefficient of restitution of 0.85, and then advanced the particle ODs in time using a second order RK. And then the phases are coupled through an interface exchange term, which appears through drag and also the volume fraction. So the drag correlation that we used was the Tenetti drag law, which I believe was referenced in the previous session. So this drag law depends on both the particle Reynolds number and the local volume fraction. As I mentioned, periodic in all directions. And then we ensured that our densest domain was at least 32 characteristic cluster lengths in the gravity line direction. Then finally, since this flow is fully periodic, we forced our mean mass flow rate to 0. Okay, so we did these Euler-Lagrange simulations, and we wanted to use the results of those simulations to start to think of how we might inform closures for the multiphase RANS equations. So I'm going to show you those here. In these equations, I denote both time and spatial averages by the angled brackets. So since it's periodic in all 3 dimensions, and then eventually, once clusters form in this configuration, it becomes statistically stationary in time as well. So those angled brackets represent an average over both space and time. And then we also use a phase average. So this is analogous to a Favre average. So the subscript F will denote a phase average with respect to the fluid, and then P with the particle, where the epsilons are the volume fraction. And then one other note on notation. So fluctuations from mean quantities are denoted with primes. So a triple prime will denote a fluctuation with respect to the fluid phase average, and then a double prime with respect to the particle phase average. And these are the multiphase RANS equations in the fluid phase for this configuration, which I already mentioned is quite simple in the grand scheme of multiphase flows. So as soon as walls or other body forces are introduced to the system, you have more terms that appear in these equations, of course. So the term that I'd like to highlight here is the drag production, because it's the only source of TKE present. And also make the comment that, as I alluded to earlier in the talk, we can't just extend our models from single phase turbulence, and it's also really challenging to augment existing models from single phase turbulence. So the question kind of is, what's the best approach to model these systems? And so the approach that I've been taking for the last number of years has been to use a sparse regression-based approach that essentially postulates if we want to model a tensor D, we're going to say that that tensor can be reconstructed using a linear combination of coefficients beta and then a set of basis tensors T. And so in this linear combination of coefficients and basis tensors, the tensors themselves may be nonlinear, and but they're based on our knowledge of physics. And then the coefficients could be constant coefficients, and then they can also depend on the principal invariance of our minimal invariant basis T, and that dependency is free to be nonlinear as well. And so this is kind of an homage to sort of the idea of using invariant tensor basis for turbulence modeling in single phase flows. This was carried out in the 70s for a number of single phase turbulent flows. And so going from sort of this formulation to how this is going to look with our actual data, what we're going to do is we're going to take all of our data for this tensor D that we want to model, and essentially we're going to take every instance that we have from our trusted data and vertically concatenate it and string it together. So essentially we're taking our tensor and we're going to stretch it out into a tall vector, single column vector, and then put each instance that we have in our data, so different flow configurations, different time samples, that sort of thing, string those all together vertically. And then we're going to do the exact same thing with our minimal invariant basis T, where each column represents that same configuration as we had in D, but each column is a different basis tensor. And then the idea is that we want to find a vector of coefficients, these beta hat, where the idea is that we want that vector to be sparse. Ideally, we want as many as possible of those coefficients to be 0. So that will effectively do kind of like basis selection, as well as give us the coefficients to fit the data. And so how do we find beta hat then? And how do we ensure that it's sparse? And so we do that using the same procedure that's in Brunton's 2016 paper on Cindy. This is also called the lasso optimization. So the optimization that we do is we do an L2 norm regression, regressing our coefficients to the data. So this is essentially just ordinary least squares. And then we penalize the L1 norm of the coefficients and also include this tuning parameter lambda. So essentially, as lambda is larger, we end up with fewer terms in our model. And as you reduce it, more and more terms are included in the model. This is handy to formulate it this way because by doing so, we can ensure that our resulting model is form invariant. That's important. If we rotate our configuration, we still want the model to work, of course. So essentially, if we apply a rotation matrix Q to our data, since if you remember, our model is just a linear combinations of coefficients times our basis tensors, we can just bring that rotation matrix inside of that function. And then if you also recall, we formulated our tensor not as, as its traditional form, but in a tall and skinny orientation. So that means that beta is a single value and doesn't change based on orientation. Okay, so I'm not going to dwell on this a long time here, but we've shown using single phase turbulence that this approach works pretty well, even with flows that have a large degree of separation in them, which is traditionally challenging to model. It's also robust to noisy and sparse training data. So if we look at experimental data, which has error in it, as well as only available at a limited number of points compared to computations, it does pretty well for that as well. And then it also does well if we apply a learned model to a different flow configuration than what it was trained on. It does well there as well. Okay, so now we're going to extend that approach to our gravity-driven gas-solid flows. And if you recall, we have these 6 unclosed terms in each phase. And a key challenge here is that if you recall, we needed an invariant basis set in order to carry this out. But for multi-phase flows, generally these haven't been derived. So that is a key challenge. And then, of course, as I mentioned in the beginning as well, we have a much larger parameter space and kind of a wide range of length and time scales that we need to take into account. I also mentioned as we increase the complexity of our configuration, the number of unclosed terms is going to increase as well. Okay, so the first challenge is determining an invariant basis. And so what we can do here is identify tensors that are relevant to the flow physics. So for this case of flows, we have an anisotropic stress tensor that we can define in both the phases. So essentially, this is the particle phase Reynolds stress and the fluid phase Reynolds stress. We take out the TKE and then subtract off 1/3 from the diagonal and have an anisotropic stress tensor for each phase. And then we can also form this tensor based on the slip velocity. So essentially, we're just taking our slip velocity and then doing an outer product with it to form a tensor, and then using the anisotropic part of that as well. Finally, since all the terms that we seek to model are symmetric, the basis that we're going to form also requires that the tensors must be symmetric as well. So we can follow a procedure that was developed in the 50s that basically gives a recipe for taking a certain number of relevant tensors and formulating an invariant basis set. And what we find for the drag production is that when we do this procedure, as we decrease lambda, we increase terms in our model. And if you look at this red line here, this is model error. So once we get to 3 terms in our model, our error goes down quite a bit. And then as we add terms, we can kind of drill that down to 0, which is represented here. And then in this plot, I'm showing the 9 configurations. I'm sorry, no, this is just for G equals 0.8. So this is just a subset. This is just 3 configurations. The 3-term model is shown on the left and then the 6-term on the right. So you can kind of see the differences in including those additional terms. And then we've also assessed performance on temporally evolving flow. So we took those models that we learned from the stationary data. And then what we did was we started with that end condition and then flipped gravity around and let it evolve in time. And so the Euler-Lagrange result of doing that is in the dashed line here. And then our learned model is in red. So considering that the model was trained on just fully stationary data, it did pretty well to capture the evolving in time physics. And then I'm showing this for the particle phase velocity here as well. And I think I'm out of time, so I can stop here. But I will just say that we've started working on, or recently worked on using gene expression programming to kind of offload the work of determining what the coefficients should be if a constant coefficient isn't sufficient. And so, yeah, with that, I would be happy to answer any questions.
Thank you very much. We are at a break, so we can actually run a little bit long. I appreciate if people need to step out to grab lunch, but we have a minute or two if there's any questions for Sarah. Deepak, is there anything in the chat?
No, I don't see any in the chat.
I guess everyone wanted lunch. Up there we go.
Oh, so that's a good question. So wall-bounded flows, I don't know how this would do if you took these models and threw it into a simulation with walls around it. That's one of the things I'm working on right now is looking at modeling near wall kind of things that happen. I would imagine it would probably do, fine in the interior of the flow and then probably break down a bit at the walls. But I'm working on extending to that. It's a good question. Are there any resolution requirements for the RAND simulations? Do the RAND simulations need to be unsteady? That's a good question as well. I haven't given that one quite a lot of thought just yet. I don't believe they would need to be unsteady. And I'm trying to think of, I can't immediately think of what the resolution requirements might be, but that's a good question. I'll have to think about that a bit more. Excuse me.
All right, and with that, we will thank all the speakers for our session. It's very much appreciated. Again, anyone who's presented this morning, if you haven't already provided a PDF copy of your slides to the Multiphase Flow Workshop email address, please do so they can archive them on the website for anyone who wants to look back at them. And with that, we are going to break until 12:50, where we will pick back up with an afternoon session. Thanks, everyone.
Good afternoon, everyone. I hope you're ready to start the afternoon session of the Multiphase Flow meeting. First up this afternoon is Hari Sitaraman from the National Renewable Energy Laboratory.
Okay, thank you. My name is Hari Sitaraman, and I'm a scientist at the National Renewable Energy Lab. Today I'll be talking about some of our work on gas-liquid flow modeling for renewable fuels production. And when I say renewable fuels production, this is from biomass feedstocks and also includes some work on gas fermentation, which includes CO2 and syngas as the feedstock. So just to orient everyone, I just have this one slide to just show how important biomass is, because this is currently the only resource for carbon-based fuels and chemicals. While solar and wind are used for generating electricity, and fuels such as sustainable aviation fuels need sources that have carbon, such as biomass or CO2, for instance. So just to again orient everyone, the ways to convert biomass to fuels include two pathways, one which is the high temperature and the other is the low temperature pathway. The high temperature is using pyrolysis to convert to gaseous products and oils, while the low temperature involves biochemical conversion of the cell by making sugars out of the cellulose and then using microbial bioreaction to convert to liquid fuels. So today we'll be looking at the lower pathway and specifically looking at the bioreaction pathway where sugars are converted to products that finally gets upgraded to fuels that can be used as sustainable aviation or marine fuels and so on. So just to again give an introduction on what bioreactors do. Through microbial action, they enable conversion of feedstocks to useful molecules. It has been widely used in food and beverage industry and in pharmaceutical industry, and now it is being surmised as a way to provide a pathway for making biofuels such as ethanol, butanediol, which can be intermediates for sustainable aviation fuels. Gas fermentation is also an emerging field for CO2 capture and conversion that includes even syngas fermentation. And in these cases, the fermentation is a large cost contributor, and improved bioreactor designs at scale are necessary. And at this point, it becomes more of an engineering problem than biology. And the dominant physics, of course, is gas-liquid flows, which plays along well with the multiphase flow workshop here. So this work is regarding numerical modeling of gas-liquid flows. And the challenging questions that arise during modeling are how bubble dynamics, how do you treat gas mixtures, and how they impact bubble size distributions and mass transfer. And the second big interesting part of this modeling is how do you implement component-wise microbial uptake as a reaction term, and how does that influence species distribution and hydrodynamics. And both of these challenges, of course, play into how we design large-scale reactors for improved mixing and energy requirements. So again, jumping directly into how we model these systems, I just want to briefly talk about the equations and the methods that we use. We use a two-fluid approximation. We assume that the gas and liquid phase are interpenetrating phases. The gas bubbles are small enough in scaled-up reactors that a continuum assumption is reasonable. We solve compressible low-Mach-Ranz equations, volume fraction constraint, mass momentum equation with appropriate drag terms for bubbles in liquids, and the species transport equation as shown here, which has an important term, which is the interface mass transfer that shows up as a source term on the right-hand side. And again, the species are solved within both the gas and the liquid phase with the interface mass transfer. We also account for bubble size distributions through the population balance-based model, where classes of bubbles with volumes are associated with a transport equation with source terms for coalescence between bubbles that can create bubbles and that can destroy a certain bubble, breakup of certain bubbles into daughter distributions, and also a drift and nucleation term. We also account for the drag using the Grace drag model, which is used for spherical bubbles, non-spherical bubbles, which depends on the Reynolds and the air force and the gas fraction. The mass transfer is accounted through the Higby penetration model, where the KLA, which is the mass transfer coefficient, is obtained using a Sherwood correlation through the Higby penetration theory. And we finally also account for microbial uptake through what's called a monode model, which depends on the local concentration of oxygen in this case. But for gas mixtures, it would include a multiplication of these monode-like terms over different species of gases. Moving to the next slide, our model is implemented in OpenFOAM. We have added in some custom implementations for the mass transfer and Grace drag models, and we use fermentation broth properties that are similar to water, a turbulence model for at-scale simulations, and population balance is, for some of the cases we do, are using 10 classes. With greater number of classes, the cost increases, but we have noticed that around 10 we get grid converged results. And more details of our work are in some of these papers, which I'm happy to refer to you at the end of the talk. This slide shows the validation of our model for bubble columns. The top two panels show validation for air, where we show gas holdup as a function of superficial gas velocity. The gas holdup is a measure of how much gas is present in the liquid at steady state, and this can be a measure of how tall the column rises once you sparge in gas. We also looked at mass transfer coefficient validation with some of the established correlations in literature. We also recently looked at a validation study for CO2 in a co-flowing bubble column, and that is sort of shown here, where we look at two cases with varying superficial velocity, look at CO2 mole fraction in the gas phase as a function of height of the bubble column. And we are able to see that we are able to capture the trends in the experiments as well as other low-dimensional models present in literature. This slide shows some of our recent studies on large-scale bubble columns. These are about 500 meter cube in liquid volume, 40 meter high, 5 meter diameter columns. And we are looking at different designs that include the traditional bubble column design that's on the left, which shows the transience of gas fraction and how oxygen in the gas phase dissolves into the liquid phase. And what is shown in the middle panel is the airlift reactor, where there is an internal draft tube that enables recirculation. And also in the last panel, I'm showing a movie of the stir tank reactor, both gas fraction and oxygen concentrations. In all these cases, you can see that there is a large heterogeneity in the concentration of oxygen, and this is mainly because of the large pressure gradient that you see in tall reactors, where the hydrostatic pressure is much higher at the bottom compared to the top, thus increasing the solubility of the gas. We looked at how oxygen uptake from the microbes affect the steady-state oxygen concentration. We see that without microbial uptake, you see the same concentration there for all the reactor designs, and this is again because you would achieve the saturated concentration of oxygen in the reactor. But with uptake rates, there is a difference that we see. There is higher oxygen concentration for the stir tank, and also you see that the rate at which the oxygen concentration reaches steady state is faster, thus indicating higher mass transfer in stir tank-based reactors. So moving to the next slide, I want to show two case studies where we have used this for a design of industrial scale reactors. One is for the production of 2,3-butanediol from sugars. And this is an interesting problem because there we need coupling of microbial bioreactions and hydrodynamics, which happen at very different time scales. And there is an interesting effect where controlled amount of oxygen is required to achieve the product that we need. So in this case, a simplified chemical reaction scheme obtained from a complex metabolic pathway looks something like this, where sugars can be directly converted to BDO or butanediol, or it can follow a path through a side product called acetone. And this pathway is triggered only in low oxygen environments, while high oxygen environments only trigger the pathway on the right to BDO. And so at higher oxygen conditions, you actually lose a lot of sugars to acetone as a side product. And this is an interesting aspect to study, to see how we can design the reactor in such a way that we get more BDO production as opposed to the side product. And in this case, as I said, there is a large disparity in timescales. The reactions are typically of several hours, while the fluid dynamics happen over hundreds of seconds. So we implemented this time-step subcycling scheme where we solve the transport equations to steady state, use the steady state species distribution, do a bioreaction update, and then update the uptake rates in the multiphase solve. And so with this coupled model, we see that, like the slide I showed earlier, the hydrostatic pressure has an impact on heterogeneity of oxygen concentration in the reactor. It tends to increase the concentration of oxygen towards the bottom of the reactor, and therefore this can adversely affect the BDO production. So this bar plot kind of shows how we optimize the reactor geometry from a 35 by 5 meter reactor with superficial velocity of 6 centimeters per second to something more of a non-traditional bubble column that has more of a a lower aspect ratio and lower superficial gas velocity that resulted in about 25% improvement in butanediol production and reduced side product production. Moving to the next case study that I wanted to show is on CO2 syngas conversion to fuels. In this case, our aim was to look at how mixture of gases affect mass transfer and bubble dynamics in bubble columns. So we looked at a 2-meter size column, but varied the hydrogen and CO2 mass fractions, and the CO mass fraction, of course, is 1 minus all of these numbers. So we looked at 20 different cases, and within these cases, we wanted to see how the hydrogen concentration impact mass transfer and bubble dynamics. And this is an example case of how gas fraction, CO2 concentration, and liquid velocity streamlines vary over time and during a simulation. And you can see that there is higher CO2 concentration towards the inlet sparger, again because of higher slip velocities between the gas and the liquid. And the gas and the liquid flow, you can see there is a recirculation region formed towards the bottom of the reactor. So this might be an important slide to show how hydrogen impacts bubble size distributions. What I'm showing here is one case where we have less H2 and the other case where we have higher H2 concentration, higher H2 mass fraction, 7% and 18%. And what I'm going to show here is the bubble size distribution at different heights along the bubble column at 0.1, 0.5, and 1.2 meters. And one can see that initially there is a large population of small bubbles around 1 millimeter size. And as you go up in height, coalescence effects start playing a role. And you can see that you start seeing larger bubbles towards the top. And this effect is more pronounced when you have more H2 in the system. And this is again because of the higher buoyancy and higher superficial velocity that you would see with more hydrogen in the gas mix. This is one of the last slides. Again, I wanted to show the effect of scaling the bubble column height. This is the small scale 2-meter reactor that I showed earlier. And this is scaled up 10-meter reactor. Again, in the 10-meter reactor, you see a high heterogeneity in hydrogen concentration. And this can be also seen as the variation of H2 and CO with height. You can see that there is a high hydrogen concentration at near the sparger inlet, and it starts reducing towards the top, again, because of the impact of the reduction in pressure as the height goes up. A similar effect is seen in gas fraction as well. There is large mass transfer towards the bottom of the reactor, and then it reduces towards the top. So in conclusion, we have developed a computational model using OpenFOAM that can be used to study gas-liquid flows for microbial conversion of sugars to sustainable aviation fuel, intermediates, or CO2 conversion to fuels. And we also showed some results on how we validated our small-scale column and comparison between different designs, and also 2 case studies on how we use this model to improve design of a butanediol reactor and study the impact of hydrogen on CO2 syngas reactors. And in future, we are planning to try the LES capability in OpenFOAM and with larger, finer grain classes for bubble size distributions and novel reactor designs. Thank you, and I acknowledge my the funding sources, Bioenergy Technology Office, and also the HPC capabilities at Envelope. Thank you.
Thanks very much for the talk. Does anybody have any questions, either in the chat or by phone or over the WebEx? I don't see any questions. I'll quickly ask a question.
Sure.
For your species equations in particular, do you have one for all the gas phase, or do you also include each of the bubble classes has their own species concentration?
Right now, yeah, there is no separate species for each bubble class. It's just one.
Thank you.
Okay, any other questions, or I can stop?
Yeah, if anybody has any other questions, please put them in the chat, and or if you raise your hand or something. But if not, we can get started with the next talk from Gautam Krishnamurthy from University of North Dakota.
Hi, everybody. I'm here to present on radiative heat transfer effects in gasifiers for clean hydrogen production. So this is a nice transition from the previous presentation which was concerned with low temperature syngas production, and here we are moving on to higher temperature syngas production. So specifically, I'm going to be talking on oxy-steam gasification, and basically what this involves is when a fuel feedstock is partially oxidized and reacted with steam, then we get a syngas that is dominant in carbon monoxide and hydrogen. And tailoring this composition is very important to target specific products that we want to manufacture from the syngas. Now, when this partial gasification is carried out using coal waste, biomass, municipal waste, etc., then the syngas and eventually the hydrogen that is produced can be treated as carbon neutral or even carbon negative. Now, typical operating conditions in these gasifiers are in the range, depending on the system, are typically in the range 600 to 1000 Celsius. They're carefully monitored and controlled. So the syngas that is exiting the gasifier is typically about 1000 Celsius. And the syngases are cooled and then sampled eventually down in the downstream. So, but what happens is as the syngas is cooled, the hydrogen production, carbon monoxide, methane concentration, any ash that is present in your fuel feedstock that is vaporized, tar formation, all vary quite sharply within this temperature range and during the cooling process, and it can cause operational challenges. Now, in yesterday's presentation, it was highlighted that the very pyrolysis and devolatilization process of these really complex feedstock involve hundreds of reactions. Now, it's very apparent that reaction rates are a strong function of temperature. So an ability to predict the temperature is very crucial. Most of the heat transfer within these gasifiers are assumed to be dominated by convective heat transfer, and the effects of radiation is typically ignored in most of the simulations of gasifiers. And there's a valid reason for this, because in contrast with pulverized fuel systems, the temperatures are much lower in gasifiers. Most of these gasifiers have very large aspect ratios, and consequently they have small optical path lengths. Therefore, the effects of radiation can be ignored, or some crude approximations can be made. But today's presentation, I'm going to highlight that due to the high concentrations of radiatively participating gases that are going to be present in the syngas, predicting radiation can be very important. While my results are mainly concerned with atmospheric pressure systems, we can readily see that most gasifiers that operate at higher pressures, the syngas is going to come out at higher pressures. The partial pressures of these infrared active gases are going to be even higher, and therefore the effects of radiation can be magnified. So again, the cooling of the syngas, I'm going to focus only on this cooling process associated with syngas and how it can potentially impact the location of tar and ash condensation along the sampling train. So here's our fluidized bed gasification system at the University of North Dakota. So this is the cylindrical tube here shows our fluidized bed gasifier, where lignite coal is being gasified, oxy-steam gasification is carried out, and sand is being used as a fluidized medium. And the simulations, as I mentioned, most often stop here of this gasifier. So the syngas composition and temperature at the exit of the gasifier is predicted in CFD simulations, and we don't generally track what happens to the syngas as it travels down and is cooled via the cyclones, condensers, and eventually it gets sampled in this location here. So there's a significant cooling of the syngas occurs where it is cooled down to nearly room temperature before it is being sampled. The experimental conditions investigated in this study where the coal and steam flow rates were maintained constant here in order to investigate the effect of oxygen to carbon ratios on the syngas composition. So I'm going to present here three typical oxygen to carbon ratios, 0.8 through 1.6, which was achieved simply by cranking up the oxygen flow rate. So it's oxy-steam gasification where there's no nitrogen present in the system. So the oxygen flow rates are increased to maintain these oxygen to carbon ratios highlighted here. So in the gasifier, we used ANSYS Fluent, typical Euler two-fluid model, and here are some of the various other modeling options that were explored. Lignite is a very porous coal with very open structure, so there were no diffusion limitations assumed with the devolatilization or the heterogeneous combustion process. So we just used a finite rate chemistry to predict the composition and temperature of the syngas as it was exiting the gasifier. Now, after the syngas exited the gasifier, we modeled the cooling process rigorously by taking into account the effects of radiative heat transfer. Now, the syngas consists of CO, CO2, and water vapor. All three are radiatively participating. They have a lot of overlapping bands, so getting a good radiation model for syngas mixtures is quite challenging. So again, here's a quick overview of the various processes that were, various reactions that were considered. Again, pyrolysis and devolatilization is extremely challenging, but we used a simple empirical based devolatilization model based on the proximate analysis of the fuel material, and we modeled the volatiles in this manner. The two main reactions that is of interest in this presentation is highlighted here. The water gas forward reaction, water gas shift forward reaction, which is exothermic, and water gas shift reverse reaction, which is endothermic. So these are to be kept in mind as we discuss the results. So what the measurement showed was that as the oxygen to carbon ratio increased, the hydrogen production in the syngas started to decrease. So the primary questions that we were interested in answering is, can CFD replicate these trends? And can we, from understanding the gasification characteristics within the gasifier, can we uncover why low oxygen to carbon ratios favor hydrogen production? So the figure on the left shows the gas volume fractions associated with these three oxygen to carbon ratios. So the main takeaway here is that as the flow rate of oxygen increases from moving from left to right, there's more fluidization that is occurring, gas velocities are higher. So the bed, the sand and lignite fuel bed is kind of approaching this slugging regime from a bubbling regime. On the right, we see that as more and more oxygen is being supplied into the system, there's more oxidation that occurs, oxidation of the fuel that occurs. Oxidation is exothermic. So the temperature inside the gasifier is increasing as well as we go from left to right, as oxygen to carbon ratio increases. Also highlighted here is, since these fuel investigated in this study is lignite coal with considerable ash content, we were approaching this temperature of 1100 Kelvin, which can potentially lead to ash agglomeration problems and loss of fluidization, essentially. The figure on the left here shows the rates of reactions associated specifically with the water gas shift reverse reaction. And the figure on the right shows the sum of all oxidation reactions. So there's a whole bunch of oxidation reactions that are occurring at different oxygen to carbon ratios. Now, what's readily apparent is the more oxygen that you supply, then the rate of oxidation reactions are going to go up. On the left, we see that the reverse water gas shift reaction, the rate of the reverse, since water gas shift is an exothermic reaction and reverse water gas shift is an endothermic reaction, and increase in temperature should start favoring the reverse reaction, water gas shift reaction. And that's exactly what is happening here, where the rate of reaction for the water gas shift reverse increases with increased oxygen to carbon ratio. So these two were the primary reasons why the hydrogen production starts to go down with increase in oxygen to carbon ratios. So here is a comparison of the measurements versus predictions. So hydrogen production, as indicated by the black histograms here, are going down, which were reasonably well replicated by the simulations. And the production and the compositions of CO and CO2 are a little bit more complicated because CO and CO2 are reactants and products in multiple reactions, as I showed previously. So they are oxidation products, devolatilization products. They participate in water gas shift and the reverse water gas shift as well. So while the production of the composition of hydrogen was reasonably well predicted, there were some challenges in accurately predicting CO and CO2 compositions as well. Now, again, as highlighted, these CFT predictions correspond to CO2 compositions at the exit of the gasifier, whereas the sampling was done way downstream after the syngas had been cooled. So we started exploring if there is a need for identifying and incorporating good gas radiation models in the systems. So the first thing towards identifying good radiation model is to investigate what are the water to CO2 ratios in these systems. Now, most models for gas radiation properties have been developed for simple hydrocarbons, coal and natural gas, where the water to CO2 ratios typically range between 0.5 to 2.5. Whereas what we see here is within a gasifier, where partial oxidation is taking place, there can be significant variation in the water to CO2 ratios for which accurate gas radiation models may not be currently available in the literature. And the second point to note from the figure on the right is that the carbon monoxide mole fraction can be very high in these syngas systems and these gasifier systems. Now, carbon monoxide, again, radiative properties of carbon monoxide are not that accurately developed, or the role of CO radiation has been traditionally been ignored because in pulverized fuel systems, CO concentrations are low and CO radiation is going to reduce at high temperatures. However, we see that in these gasifiers, CO concentration can be quite significant, often approaching up to 50%. So then we started tracking the composition variations as the syngas that was exiting the gasifier was cooled all the way to room temperature conditions. So the figure on the top shows at oxygen to carbon ratio of 0.8, when gas radiation was not accounted for, again, the water gas shift is CO plus H2O gives CO2 plus H2. It's an exothermic reaction. So as the gas is cooled, the forward reaction is being favored from Le Chatelier's principle. So there should be more hydrogen and CO2 production. Consequently, the equilibrium constant for water gas shift should increase as the gas is cooled. And that's exactly what is observed along axially and along the axial direction as the gas is cooled. The red line representative of the equilibrium constant does increase, and hydrogen production is increasing as well. Hydrogen is the dark black line here. However, if you account for radiation in the cooling pipeline in the cooling channel, we see a much more drastic increase in the equilibrium constant. And so equilibrium conditions are very quickly attained. And hydrogen concentration also increases and then starts to stay constant. So this is with the oxygen to carbon ratio of 0.8. And we see similar trends with at oxygen to carbon ratio of 1.2. Again, a more gradual increase in equilibrium constant at without radiation, but with radiation, the process is hastened and the hydrogen composition results can reach its steady state value fairly quickly. So the temperature profiles along the cooling path is quite different depending on whether you account for radiative losses or not. So again, same trend with 1.6. Radiation really hastens the attainment of equilibrium compositions. Now this has very severe consequences, especially when we are dealing with the issue of tar condensation and ash vapor condensation processes. So we want to tailor these operations such that we want the tar and ash to condense only in specific locations along the cooling path. Not accounting for radiative heat losses properly can result in us not identifying the exact region along the cooling channel where the tar and ash condensation is going to take place. So again, if you look at the gas temperatures along the sampling train for the 3 oxygen to carbon ratios, we see that without radiative heat transfer, the gas continues to remain hot, whereas these are highly emitting gases that are coming out of the gasifier. If you account for radiative heat transfer, even though this is a small aspect ratio, large aspect ratio, small path length cooling pipe, the effects of radiative heat transfer could be significant, and the gas, which results in the gas cooling down fairly quickly to attain room temperature conditions. So, and this again, this effect is going to be exacerbated when we are dealing with high pressure systems. So there is a critical need to start accounting for the impact of radiative heat transfer, not only along the sampling train, but within these gasifying systems themselves. And so the main conclusions from this is that we examined the variations in hydrogen concentrations. The high hydrogen production was favored at low oxygen to carbon ratios. There were significant variations in water to CO2 ratios within the gasifier. CO mole fractions were high. So there is an increasing need for developing and validating customized model for gas radiative properties that can be employed in these scenarios. And they need to be validated against accurate line-by-line benchmarks. Water gas shift reactions continue to occur. So it's not important to just truncate your CFD simulations to the exit of the gasifier. As the syngas is getting cooled along the sampling train, these homogeneous reactions, lots of homogeneous reactions, although I've emphasized just the water gas shift and reverse water gas shift, there are a lot of tar condensation complex reactions that will continue to occur along the sampling trains. And the impact of radiation, in addition to convective losses along this sampling train, could be quite significant because they can potentially help identify operational challenges in these systems. So that's all I had. I thank you for your attention, and I welcome any questions that you may have.
Thank you for an excellent presentation. Are there any questions from anyone?
Yes, hi, Gautam Merdad here. You're clearly showing that radiation has an effect, in the cooling system and for the water gas shift. What do you think about the effect inside the bed itself, where the presence of particles or bed material can attenuate, the radiation? Do you think it's as crucial?
It could be because it is challenging because different reactors have different volume fractions of solids, right? So if you have a circulating fluidized bed, yes, the volume fraction of the solids is going to be lower. But on the other hand, a circulating fluidized bed is thinner also, right? It's very long, lot of aspect ratios. Whereas if you have a packed bed, then volume fraction is very large of the solids. But so yes, I think there will be some impact, and but yeah, we need to temperature and the bed volume fraction are both going to determine how much of a large impact is going to be.
Yeah. Okay, great. Thank you, guys.
And as you know, CFD simulations of multi-phase reactors are challenging in itself. And if you start throwing in radiation with wavelength and directional dependencies, then
exactly.
Yeah.
Yep. Absolutely, I hear you. Thank you.
Yeah, thanks.
Does anyone else have any questions? Well, if not, thanks again, Gautam, and then we'll move on to our next presentation. Yidong Z from the Idaho National Laboratory.
Thank you very much for your introduction, and let me just quickly pop up my presentation slides. Here we go. Good morning at my time, and good afternoon, everyone. So my name is Yidong Shah, a computational scientist from Idaho National Laboratory. Today, I'm gonna give an overview of our experiment-informed computational models for granular feedstock preprocessing and handling unit operations. Most of the model, the SAS I present in this one, come from the research from Idaho, but at the same time, we collaborated closely with Unreal. So we do have some of the newer models also from the contributors, collaborators from Unreal, just like Harry, who just presented earlier. So I think in the future edition of our presentation, we also would like to include those model progress from Unreal. But for this one, this primarily focused on those outcomes from Idaho National Laboratory. And this piece of work has been primarily sponsored by the DOE Bioenergy Technology Office's the Feedstock Conversion Interface and Consortium project. And the motivation for our idea of developing those models is actually derived from those process upsets that we have observed for many years in the pre-processing and the material handling aspect in the biorefinery and research community. So if those materials are not well pre-processed, they certainly cause the flow issues in those handling equipment, and that will put the system to the downtime and an overhaul, and that would significantly impact the proficiency of the biorefinery system at all. So using modeling as an alternative to test and suggest the improvement for those pre-processing and handling would be possible options for now and the near future. And we tightly follow the concept of the so-called quality by design to develop and implement those particle flow and the fractionation models. And we do want to capture the key features of the physics of the particle and the unit operations in those processes. So here is a very brief example of what we can do with a very powerful model to predict some kind of the processes in the size reduction operation in a hammer mill and also the screw conveyor. But overall, we will just tell you and trying to understand and make those models predictive, we do need to understand of those materials from multiple scales, from the micro scale to the bench scale, and eventually to the pilot scale in our like biomass feedstock national user facility, which is the largest scale that we can possibly deploy in an easy manner within our research capacity. And for the much larger scale, I think we do need to collaborate with the industry partners in order to test our model's predictability at a so-called industry scale. From the very beginning of our research, a key question is how to model the biomass particles. That has been an effort of about 2 years, because like the traditional like hard solids people use to model, they do not have much flexibility or the bulk compressibility. But what is different for biomass is usually they are very compressible in the bulk sense, and those models developed for the pharmaceutical and the rock mechanics may not be directly applicable in our case. So we really reviewed all of the possible options before we started researching our own approaches, trying to set the pros and the cons in the previous review articles. And in the same sense, I think in order to model the large scale, the industry scale, the traditional continuum mechanics-based models, such as finite volume and finite element methods, they cannot be directly used for biomass because of the large compressibility of the material in the continuum sense, and they are changing compressibility depending on the different stretch conditions. And we also reviewed the possible options to start with a few years ago as serving as a guidance for the future research. And our approach overall within the project is really to observe the phenomenon in the real experiment and try to come up with ideas to use experimental data to inform how we should develop those models and use these models to predict their the flow behaviors of individual unit operations in pre-processing and the material handling, and using our experience obtained from simulations to either indicate the upstream or the downstream operations, such as pre-treatment or the conversion. And the outcome of such an exercise is always trying to provide the industry with something that they can refer to. So, for example, by using both experimental data and also the extended simulations based on the good validation of our models, we can come up with the so-called design charts for flow unit design, such as a hopper in our case. And we try to really put together a table that connects the material attributes, the geometry design of a hopper, and their performance, like is either funnel flow or mass flow, and what their critical arching distance would be. Such information would help industrial partners to consider certain materials for the certain operations, so they can potentially avoid any disaster situation, just like a backflow or the clogging in their operations. So that's the meaning of such activity for modeling and simulation. And to start with, we used a discrete element particle models for flow modeling, and there are the different approaches to really assemble the realistic particle shapes of those biomass particles. Here are just examples of where we use the rigid multi-sphere model or the flexible bonding sphere model in order to model the screw conveyor situation or the hopper discharge. And they haven't been proved to be very effective for certain operations, but there are also the limitations because the limited capability to resemble the particle shapes for those different types, such as Constover or the pine wood shapes. So, in a very exploratory nature, we tried to use really X-ray CT to analyze the particle shapes of the realistic biomass, such as pine chips, and try to come up with high resolution models for those the particles. And certainly we know those high resolution particle model cannot be used for bulk solids flow simulations because this is computationally unaffordable. So we needed to do certain cost greening in order to come up with affordable particle shape resolutions in order to put them into the bench scale flow test, such as those tribometer tests, for which the experiment was conducted in Oregon National Lab. But they do provide the experiment data, so we can use them to really to calibrate and validate our particle scale models. those particle models really have a good resemblance of the particle shapes of the real biomass. However, due to the good resolution, they're relatively expensive in general, and you do need to use a lot of computational cost. Although national labs have access to the large scale high performance computings, and we always need them to carry out some highly important research. But an important consideration we have is they cannot be easily accessible by industry partners, especially small and medium scale businesses. So, and our focus later on and moved on to how really we can do the good market outreach to support those industry partners to use our model. Then we come up with the cost-grained DM model, which essentially reduces the cost of computing, but also perhaps will enable people to deal with to model the pilot or even the industry scale bulk solid simulations using these DM models. And here is an example of the Hopper discharge for a beam that has a height of 5 meters using our cost-grained models. And all those are open source codes and hosted on our GitHub site. But again, there is some limitations with the particle resolved models. No matter how powerful or how cost-grained they are anyway computationally costly and cannot come up with the speed of the continuum mechanics models, which, like for example, the finite element. Just simply by comparing those CPU hours we use, and you can certainly know the good approach to further move on for the large-scale computer might be using the bulk scale models based on finite element or finite volume. But however, there had been the historical issues with those so-called constitutive models for finite volume or finite element. So that has been a recent breakthrough in our research to come up with the right description of the constitutive models for those bulk solids that can accurately represent their bulk natures in a highly consolidated status. So those models are so accurate in order for us to model those Hopper flow and also the school conveyor simulations. And those are recent, from my perspective, state of the art progress in the continuum mechanics for the bulk solids. And you can find the references in our published articles. And after I introduced the bulk flow, I also would like to talk about the size reduction operations or the fractional mechanics of the biomass. This has been a topic I think has been previously explored at the much lower scale at NREL. NREL had done a lot of good work at the molecular scale, but on the higher scale, it would be also challenging because the knowledge we could obtain from the molecular scale is not so easy really to translate to the higher scale. And so we explored the options for the experimental scale. For example, the wood blocks, how we can really model the wood block fracture, and these are very complex behaviors in general in biomechanics. So we tentatively used still using the DM model, but trying to come up with the custom contact models and the bond stiffening model in order to capture those nonlinear and hysteretic fracture behaviors of the woody biomass. I think that serves as the very first step for us to understand the possible approaches to further the knowledge of these simulations. And in order to further understand the biomechanics at the lower scale, for example, at the micrometer scale, but much above the nanometer scale, we explored and developed those, I would say, those micro scale DM model in order to model the possible fracture mechanics at the scales. We try to understand those mechanics so that might be helping us to upscale our model parameters at the macro scale. And that is a very meaningful exploration in the recent past. And here is a demonstration of a simulation when we do have the actual loading test for the microstructures of those woody biomass, and you can see the deformation and the collapse of those biomass structures. And we do have the later version of this, which is under the current development. So We also studied those like herbaceous, herbaceous and biomass, for example, the corn stovers, the stock. In order really to understand their mechanical behavior, what we do first is actually not model development, but we conducted the controlled experiment to understanding the bending behaviors. And this like kind of a test can apply not only to biomass but also to a lot of the different agricultural products. And like the importance of it so is to get the like experiment data and the biomechanic data in the first hand and apply them to our like DEM model. For example, if we want to model such a kind of a knife milling of the corn stalks, we want to really provide the right parameters to their bending stiffness and also their yielding stress. So those experiments I mentioned in the previous slide will help us to set the right parameters. So we will be able to model the realistic behaviors of such an sophisticated engineering environment. Yes. So I think that's a very important aspect we want to continue with. So here comes another pre-processing unit, which is called air classification or air fractionation. And this literally really is like the gravity-based, using like the blowing air to separate the fine tissues and also the the larger density particles. This is really to separate different anatomical fractions in either the corn stover or the forest residues. So the produced the feedstocks can be highly enriched to certain anatomic fractions, because we understand that the different anatomic fractions have different flowability and the conversion thermal chemical properties, and using the fully mixtured biomass feedstocks may not be the best options for the certain needs of the downstream biofuel production. And by using the coupled CFD and the DEM simulation, we are able to simulate such a process and indicate, for example, what's the optimal blower power rate and what's the best and combinations of those flow tubes and our input feeding rate to indicate the optimization of the real experiment. So here is some like extensive work when we are considering the possibility of modeling MSW. So of course, and when we are dealing with the MSW, those materials, for example, the plastics, they are very different from biomass. So before we really studied anything regarding flow of MSW, we tentatively started trying to, if we just model some like original source of MSW, like the cardboard or the plastic bottles, can we even use a model to like predict their mechanical behavior? And so here is a very just a simple but interesting example for the actual loading of the waste plastic bottles, trying to understand their elastoplasticities. Yeah, and I think we have not done more of this work, but we just wanted to verify the like feasibility of doing so. Yeah, I think that's an interesting topic to further consider. And to conclude from this one, I would say that the research to understand the mechanical behavior of the materials, either biomass or the MSW, requires the knowledge from the multiple scales, from the micro scale to the bench scale and to the pilot scale. Each scale can help us to design the better model strategies for the other scales, and this is ongoing effort. I presented this content maybe like 6 months ago, but in the recent past 6 months, we do have a lot of new updates on those modeling activities, and I think it will be my interest to continue to share with you our latest progress in the future interactions. So that's all of my presentation today, and feel free to ask questions if I can answer. Thank you very much.
Thank you for a very informative presentation. Are there any questions from anyone?
Very interesting presentation, Yidong. Question: have you made any comparison between your when you're actually modeling the real shape of the biomass itself versus the bounded sphere, since compressibility is such a big issue for feeding system? Have you compared the two?
Yes, we started with the easiest one. For example, is like a non-flexible. Yes. So later we found that the compressibility is kind of the bottleneck. If because we do like the actual compression test in order to model the bulk solids the compressibility, we found and by using those non-flexible particles, it's just relatively hard. And also the contact model is a non-factor. If we are using some like linear bilinear elastoplastic model that also has some limitations to capture those very unique stress strain curves. But using the bounded spheres, which provides the flexibility of the particles, it certainly helps us to capture a lot of the behaviors when they're being compressed. But the downside of this is without using the specialized contact models, they are still not able to capture the kinds of like the recovery stage of this bulk materials. And I think I can use this one slide to show you like um, it's important to capture both the loading and unloading procedures for those material because in a complex material handling environment, and sometimes materials are regionally compressed and sometimes they are just regionally depressed. Only if we are able to like capture both the loading and unloading of the bulk materials in a meaningful way, then we can consider these models are accurate for representing the bulk materials of a biomass.
Okay, so when the material, when biomass goes through the feeding system,
right.
When it comes out basically into the reactor, now potentially the internal structures have changed, right?
Yes. And I can
is
tell.
There, yeah, so I was gonna say, is there any plan to kind of formalize it, how that has changed in terms of, because ultimately from a reactor scale modeling, what comes out of the feeding system is what goes into the model, right? So
you are right.
Is there any plan to kind of bridge what you're doing and what actually comes into the reactor scale modeling in terms of porosity models, for instance, that could be a function of what happens during in the feeding system, for instance?
Yes, we do have a plan, and we do have the current ongoing research work where we are simulating a compressible screw feeder, which like the role of the compressible screw feeder is directly to feed into the reactor. And I can tell you, this is much more challenging than I previously thought because when we have a compressible screw feeding scenario where the density is continuously increased through the pathway, and I think a lot of technical challenges occur. And our model, which was validated in the gravity-driven hopper and using the constant diameter and screw conveyor, I mean, although they can render a good prediction for those scenarios, but for the it occurs to us in our development team when we are dealing with some compressible screw feeder, for example, the new challenge come because like we do need to really capture the right stress increase with the experiment. So yeah, I cannot share much detail because I also need to fully digest what's going on with our current progress. But I can tell you it's not so straightforward. Yeah, but we do have a plan.
All right,
to bridge the gap.
Yeah, thank you.
Yeah, thank you very much.
I have a quick question since we have a little bit of extra time.
Okay.
On your last slide for your air classification model.
Okay.
So what do you use for the drag for the different materials?
Okay, let me quickly pop up again. So, in a nutshell, to answer the question, so this is a two-way coupling between the CFD model and also the DM model. For the drag, we do choose from available drag like a solid and air in, like fluid solid in interactions, but for the different materials, it's possible for us to fine tune the different dragging models or the coefficient within the models, and this is so far for the air classification that has been kind of exploratory work, so we haven't dig into too much into the technical, and I'm afraid to say in order to accurately capture the individual particle interaction with the air, it's not easy for me to imagine how to design a controlled experiment to do that. I believe we can do it, but what like that like equipment we have in our side or they're at the pilot scale, so I would say it's possible and it will be interesting, but in the current one, the air classification belongs to so-called anatomical fractionation process. So this is essentially not within the scope of our current project or in the near future. But if the individual project in our lab would require us further extend those capabilities and make it more accurate, then we certainly would really dig into the details, the fine details of things. Yeah.
Thank you very much.
Yeah.
Are there any other questions out there? And ask in the chat if you would like. It doesn't look like it, so we'll move on to the last presentation of the session from Alan Runstetler from CanMet Energy Canada.
Can you hear me?
Yes, I can.
Okay, great.
Thank you.
And you should be able to see my screen now. Okay, let me know if you can't see anything, but I'll get started. So I'm going to talk about a fluidized bed approach for hydrogen production from natural gas using hot slag from steel plants. So if you're not that familiar with iron and steel production, I'll just give you a little backgrounder here. So here's a particular iron and steel making process. It's not that important, the particulars of the process, but note that it's a pyrometallurgical process, so it operates at high temperature.
Excuse me,
and produces a
I can't see your slides. Can anyone else see slides?
Oh, you can't see them?
I don't think they're. No, I cannot.
Oh, I forgot to hit share.
There you go. Now it's coming
Sorry about that.
Thank you.
Okay, so yeah, here's a particular iron and steel making process. It's not that important what the exact process does and looks like, but
we might be looking at one of your other screens.
Oh, sorry about that. Did I get out of share here?
You can hit share again, and there you go.
Okay. Oh, there we go. Okay.
There you go. You're good now.
Okay. All right. Sorry about that. So it's a pyrometallurgical process, meaning it operates at high temperature and ultimately produces a liquid iron product. And in addition to iron oxide, iron ore contains a lot of minerals, and they also are in liquid form in the end, and they float to the top. And the quantity of slag is comparable to the quantity of iron. So that's kind of well depicted in this picture here with this sort of ratio of the hatched slag to the purple iron. But essentially what we're talking about is this very high temperature byproduct of iron and steel making. And what happens to this slag byproduct? Well, in many cases, it's simply poured into pits. And in other cases, it's granulated using water to use the material for cement production or construction aggregate. But in very few and approaching no cases is that very high quality heat actually recovered. So there are some studies out there and technology developments. Recently, the intention has been to capture the slag energy as a high temperature air for use within a plant. Now there's a lot of interest in low carbon fuels currently, and hydrogen is a carbon-free fuel, but it needs to be produced from something, usually natural gas or water. And a production pathway that has gained attention recently is to decompose natural gas, which consists mostly of methane, into a gaseous hydrogen or hydrogen-rich gas and a solid carbon or carbon-rich byproduct. So essentially what we're talking about is the form of pyrolysis. The advantages of going this route, it's potentially easier to store or utilize carbon compared to CO2. It essentially introduces some other options that become available instead of going straight to CO2. And as I'll show, it's possibly more suitable for smaller scale production than steam methane reforming. Disadvantage compared to steam methane reforming, it produces half the hydrogen per unit of methane. So about 60% of the chemical energy of the methane is retained after decarbonization. So the proposition here is to dry granulate the slag and use its heat to drive the endothermic methane decomposition reaction, using a fluidized bed to provide the contact between the slag and the natural gas. So you could think of it essentially as a waste heat to hydrogen process. So this is what the process looks like. So the slag pours down into a rotary cup atomizer, and that produces the slag granules. The fluidized bed and the rotary cup are more integrated than it shows here schematically, and I'll show that in a moment. But the slag particles end up in the fluidized bed where they provide heat. The methane is what's doing the fluidizing, and then the decomposition occurs. The solid slag and some carbon come out of the bed, and then there's a gas stream coming out the top with hydrogen, most likely some unconverted methane, carbon, and some errant slag as well. So that gas stream then goes through a heat exchanger to preheat the incoming methane. And then there are a couple of operations that are associated with removing solids from the gas stream. And then if you want a high purity hydrogen, then you need to do a gas separation here. And then any of the unconverted methane is returned through the heat exchanger back to the fluidized bed. So this was analyzed using process analysis, and it appears that in terms of the quantity of hydrogen it could produce, it's equivalent to about 20% of the reductant from the steel processes itself. That's intended as a measure of how much hydrogen could be produced. There are limitations to how much hydrogen can go back directly into an existing process, but it's intended as sort of a measure of how much hydrogen can be produced. And then the slag flow in most of these iron producing operations is not continuous, so the slag transfer to this proposed process would need to have a buffer capacity for it to operate continuously. But from what we've seen of slag handling in steel plants, that is possible because they transferred around in pots, and sometimes it sits for a while in these pots before being disposed. So we aligned our operating conditions with a Canadian steel plant. There's nothing overly interesting in this table here, other than to point out that we assumed we could get the slag particles into the fluidized bed at 1300 degrees Celsius. They're sitting at about 1500 degrees Celsius at the tap hole. So that we thought is a reasonable assumption. Okay, so the first thing people ask when you propose a process is how much is it going to cost. So it's a good exercise to try to figure out where such a process would fit in the real world. And in the interest of time, I'm not going to go through the details of how we did this insofar as it's straightforward to figure out what anything's going to cost. Most of this is pretty straightforward. There's only the 2 points at the bottom that I want to point out. And one is that we didn't assume we were going to get a lot of money for the carbon byproduct. So we didn't want to be overly optimistic about that. And we also added a 50% contingency to the numbers that came out of our cost calculation, just because this is a pretty new idea and there are a lot of uncertainties. So there are a couple things I want to point out from this cost analysis. One interesting thing is to look at the sensitivity of the net hydrogen production cost to the natural gas price. And as you might expect, it tracks pretty strongly with the natural gas price. But we seem to get hydrogen costs that are pretty reasonable. So that looked good. And then the other interesting thing we looked at is its sensitivity to the carbon black sale price. Everything else kept constant, and it's a little bit less sensitive to the carbon black sale price. We even looked at the possibility where we'd get nothing for the carbon, and we still have pretty reasonable hydrogen production costs. Another important comparison to make is what is the cost of hydrogen production relative to other ways you could get hydrogen, and what do you get for going to the trouble of trying to capture the waste heat from the slag. So we ended up finding that the proposed process is competitive with large-scale steam methane reforming with integrated carbon capture, and much less costly than small-scale steam methane reforming, making it suitable for on-site hydrogen production and use at the plant. And then using the hot slag to drive the methane decomposition reduces hydrogen production cost by 25% compared to combusting a portion of the natural gas itself to get the heat. Okay, so another thing we looked at was the methane decomposition reactor itself. So this is a little bit more detailed schematic where you see the liquid slag coming in and the rotary cup atomizer, and it's more integrated with the fluidized bed, which is sitting below with the methane coming in from beneath to do the fluidization. We studied this using CFD, but we had to scale it down to a pilot scale size just because of the computational intensity of these kinds of calculations. So this is the bed we were using. The slag injection pipe, admittedly, it doesn't look like the diagram on the left. We wanted to put the slag in near the bottom. Since we weren't sure how well this is going to work, we wanted to give it the best chance of working. So that's why the slag is coming in fairly low in the bed. And the slag discharge pipe we did end up using for reasons I will talk about in a moment. So the operating conditions were a scaled down version of the large scale And they're oh yes, and I guess the bed temperature we were aiming for was 1,083 degrees Celsius. So that would be a good temperature to for the decomposition reaction to happen at. Okay, so this is a brief description of the CFD calculation. We have the decomposition reaction going on where methane is decomposing into carbon and gaseous hydrogen. We seeded the flow with these nucleation particles of carbon black because we needed something for the carbon to essentially accumulate on as the reaction progressed. We used the dense discrete phase model in ANSYS Fluent, particle-particle interactions using the kinetic theory of granular flow. And then we had three discrete phases. So slag particles initially in the bed, injected slag particles, and the carbon particles. We played around with the slag particle sizes to see what the bed was, happy operating at. So we came up with a series of particle sizes that would essentially put some constraints on the rotary atomizer in terms of what it has to deliver to the bed. And we had some measurements of the expected particle sizes of carbon black from our own lab here. So we had some idea of what to expect these carbon particles to look like. And then we sort of made some guesses about how many nucleation particles we had to put in, and then some of those guesses were a little bit off, but not too badly. We ended up with carbon particles that were a bit too dense in the end, but not terribly off. So we used the P1 radiation model and weighted sum of gray gases model for the gases, and the particles participated in heat transfer by convection, radiation, and in the case of the carbon particles, an endothermic methane decomposition surface reaction. So I've put some of the particle heat transfer parameters here. There's nothing too interesting there. Maybe the split of the reaction heat in terms of whether it comes from the particle or the gas phase. This is something we grappled with for many years in the coal combustion days, and I think we settled around 0.3. Okay, so the CFD model, we simulated 16 seconds of operation, and this was enough to achieve steady state with respect to fluidization and the methane decomposition. But that's a relatively short operation time, and because of that, we can't achieve steady state with respect to the solids inventory in the bed. So we decided to not allow solids to exit the reactor during that 16 seconds. So we had hot slag particles entering through the injection to compensate for the heat consumed by the methane decarbonization, but no particles were allowed to leave. So as a result, the bed solids inventory increased by 2% during those 16 seconds. So here's an example of the results. So I'm not sure if this is broadcasting all that well, but that's the sort of the bubbling bed operation there. And then on the right, we have the hydrogen mole fraction in the gases and the gas temperature. So you can see that the hydrogen mole fraction gets up to about, in this case, around 0.7, 0.75, and then it seems to stall. And that's related to the temperature distribution over here. So the gases pick up energy in the fluidized bed, or they pick up heat in the fluidized bed, and the reaction continues up to a point where the temperature gets a bit too low for the decomposition reaction occur, and then it just sort of stalls out. So the reaction finishes about midway up this reactor. So the reactor is probably a little bit too tall, but we get a decent amount of methane conversion. So just to summarize the technical results, the average steady state bed temperature remained between 1020 and 1060 degrees Celsius, so fairly close to what we were aiming for. The average temperature of the gases exiting the reactor was 850 Celsius. That's probably because the decomposition reaction stalls around that temperature. So in terms of the decomposition reaction kinetics, we had to go to the literature, and there are some experiments documented there. So there was one set of experiments where they were using carbon particles as the fluid bed material, and we were able to derive kinetics from that. And there was another one that was using molten slag. So we were, and that actually provided kinetics. So using one set of kinetics, we had a mole fraction of 0.7. This implies a 53.8% conversion of methane to hydrogen. Using another set of kinetics, the hydrogen mole fraction reached 0.9. This implies an 82% methane conversion. So it seems as though this fluidized bed approach would work. But if you wanted to really pin down its exact performance, there would be some experiments required. The variation of reaction kinetics in the literature is not unexpected, given that the decomposition of methane is influenced by catalytic effects that depend on the composition of the material in contact with it, particularly when the material contains metal compounds. So, in conclusion, it is expected that about 20% of the reductant could be replaced by the produced hydrogen from this particular process. And we found that it would be economically competitive with large-scale steam methane reforming with integrated CCS, except at a smaller scale. So it could be suitable for on-site hydrogen production and use at the plant. And for going to the trouble of trying to use the slag, you get a 25% reduction in the cost of hydrogen production from methane decomposition. The CFD analysis suggested that the fluidized bed approach will work, and further work would be required to optimize the design and operation, control the solids inventory in the fluidized bed, and probably a lot of experimental work would be required to reduce the uncertainty of the chemical kinetic rate for methane decomposition, determine the fate of the produced carbon, whether it leaves with the slag, or what proportion it leaves with the slag as compared to the leaving with the gas flow, and addressing the challenge of the molten slag dry granulation. So with that, I'll stop and be happy to take any questions.
Thanks for excellent presentation. You answered my question with your last statement. I wanted to ask where the carbon went, and you answered that. So
yeah, so I kind of went over that quickly there. See, in a lot of steel plants, they send the slag to cement plants to be used in the cement process, and that's true also of fly ash from coal-fired boilers. But there's a limitation on how much carbon can go with it. So we assumed that we were going to pollute the carbon too much. We didn't want to be too optimistic. So yeah, we assumed there'd be a fair amount of carbon contamination on the slag.
thanks. Does anyone have any questions? If no one else has, I have a follow-up kind on that. Would you envision some sort of kind of cleaning process? Let's say after you do the experiments, there's like no way you're not going to have a certain fraction of carbon on the slag, that you use steam or something to kind of clean off, or some other oxidizer to clean the slag so that you could sell it for for some other purpose.
Yeah. We've thought about that, and I think that would be possible, and that would come down to the economics.
Okay, thank you.
Yeah, thanks.
I mean, you almost have to do something, right? Because if you don't separate them, then what are you going to do with slag, and how are you going to get, I mean, you can't sequester that carbon, right? If it's contaminated.
You're talking about this?
The carbon black and slag. Would you separate the two in this process?
I guess we're kind of assuming that you could still use it as a construction material, like for roads. But that so I kind of skipped over this on the slide because for time, but we were told that if you could sell it to the cement plant, you get $25 a ton, and if it's only good for aggregate, you get $5 a ton. So, if you could clean the carbon off and it made environmental and economic sense, then maybe you could get your $25 a ton. So there's a few possibilities.
Sure, that 5 to 25, that could make a huge difference at the industrial scale.
Yeah, and then maybe it's worth using the steam to try to clean it. Yeah.
Sure. Yeah. Thank you.
Thanks.
Does anyone else have any other questions? It is. So for any of the speakers, please, if anybody has any questions, please put them in the chat. And I'd like to thank everybody for the last 4 presentations. It was very informative. Thank you very much. I think we have a break until 2:40, and Mehrdad will chair that session that starts at 2:40. Thanks very much. Bye, everyone.
All right, it's almost 2:40. Welcome back, everyone. This is going to be our last session. Our next speaker is Ali Reza Behzadi from Siemens Digital Industries Software. Ali Reza, please take it away.
Yeah, thank you. Hello, and thank you for attending this presentation. I'm going actually to talk about the Eulerian simulation of an 8-inch circular fluidized bed unit at PSRI using a novel EMMS drag model. And we are using basically the StarCCM Plus for that. In fact, we've been working with PSRI for a long time during even the past time that CD Adapco was taken over by Siemens, and in close collaboration, we thought that let's actually present something in that regard and use the rather new EMMS model that we have been playing with. This is the outline of my talk. First, I briefly go to the motivation behind the work, a bit about this EMMS drag model and the fluidized bed regimes, which this model covers. Then a bit about basically this circulating fluidized bed from the PSRI, the test case that we are using, showing some results and comparing with the experimental data, and then conclusion. In fact, one of the paramount importance in the fluidized bed related flow is capturing the heterogeneity. And by that, I mean the mesoscale structures that appear in the gas-solid flow domain. What you can see here, I go into detail of the test case. What I wanted to show here is if we go for the homogeneous drag model, which is GIDASPO in this case, we will see that we have the entrainment of solid particles, which is not what experiment will show us. So there is definitely a need to an alternative, basically drag model to the traditional homogeneous one. And one of the way would be this energy minimization multi-scale, in which the interchange between gas and solid particles are minimized. So that is the thing that we are going to use for this EMMS modeling. And to be basically more detailed, we aim to calculate the drag exerted on a heterogeneous suspension of particles. And basically the subgrid heterogeneous structures make a significant drag modification. And along that line, we are using this EMMS model, which is in line with the classical EMMS model, which was proposed firstly by Lee and Kovac in 1994. In this model, basically, the mesoscale flow structures are decomposed into dense and dilute phases. And usually what is happening is optimization of a stability condition under some basically force and mass balance equations is taking place. So these EMMS drag models can be basically extended by using these subgrid level models, and they should cover the different regimes of the fluidized bed as far as these mesoscale structures of bubbles or clusters are concerned. There are various works during many years that cover this subject, and I've put some of the references here, basically. So the model that we are using in this work is basically shown here. This is the drag coefficient, and the important point about that is basically this HD, which is heterogeneity index. And this is a measure of discrepancy between the homogeneous and EMMS drag. This CD0 is basically drag coefficient for an individual particle, which I'm sure you are aware of it. Basically, subscript S and G stands for solid and gas. Epsilon is the volume fraction, and rho is the density. We have the relative velocity here, and this basically formulation happens here. The main thing is just this HD, which is a function of volume fraction, solid volume fraction. Now this EMMS model should cover different regimes of the fluidized bed, from the bubbly to the pneumatic one, as well as the particle type, which we are considering for this one, and it is mainly dealing with the Geldart A and B particles. What is usually happening for the fluidized bed regimes is people are using some dimensionless flow regime, using some dimensionless coefficients in order to find out which regime of the fluidized bed we are dealing with, like conventional fluidized bed, circulating fluidized bed, or in different basically particle groups like group A or B. What we have done for this work is we are also using some dimensionless parameters, as you can see here, Reynolds C here for the turbulent fluidized bed, and also Reynolds SE for the fast fluidization. So what we are going to do is we calculate this value of the UC using all these parameters that we have. And if it happens that in any part of the flow domain, the velocity reaches this point or exceed that one, we are going to use the turbulent fluidized bed regime. And the same happens for the fast fluidization. If in any part of the flow domain we will reach this value of the velocity, we are going to use the fast fluidization. This is actually quite a simple way, but as you will see later on in the results, it will give quite reasonable results. And another thing is it will save a large amount of time from the computation. So this is the geometry we have considered, and we were mainly concentrating on trying all the simulation on this one. Then we actually changed the geometry to the one that you can see on the left in order to see what will happen, mainly to save some computational time. And also we did more investigation to see if there would be any compromises in the flow and basically the regime that we are going to consider, which was not the case. So we concentrated on actually using this geometry. What you can see here is the properties that we use for the particle and gas. The initial bed height is 2 feet. Maximum packing limit is 0.624. And we've tried this case for a number of superficial velocity from 0.229 to the maximum value of the 0.615. What we found with the analysis that I showed just now was for this lower value of the velocity, we are mainly in the turbulent regime. And for the maximum value, we are in the fast fluidization. And this one is kind of the intermediate one. And this actually was proven by the experiments that we compare the results with and that you will see in a minute. The important thing was in the experiment, we don't see any entrainment. So that was actually a good measure to see if we are producing reasonable results or not. These are actually more information about the simulation that we've done. We've used star CCM plus Eulerian modeling for the granular flow. Granular pressure is used, and we are solving for the granular temperature. We first started with the Hidaspo drag model, as you saw some of the results for that, but then concentrated on the EMMS drag correlation, mainly for the turbulent and fast fluidization. For the frictional model, we use the modified Johnson, and for the viscosity and granular diffusion model, Hidaspo was used. Radial distribution function was modeled by Ding and Hidaspo, and we tried to use the pressure gradient force as well as the segregated solver for the basically the phase couple segregated for the solver. And these are some information for the boundary condition for the gas and solid, as well as the time step used, maximum iteration per time step, restitution coefficient, and the simulation time, which was 25 seconds, and we tried to get the average for the last 20 seconds of the simulation run. And all these runs were done by 160 processors, basically. This is just one of the typical example that you can see for the evolution of volume fraction. And this is just concentrating on the fluidized region. And as you can see, the volume fraction reaches the maximum packing value. We started with, as I said, with this 0.229 and for the velocity, for superficial velocity at the inlet, and tried to compare first with this fast and turbulent to get some idea what is actually happening in these regimes. And as you can see, they are comparable. What you can easily see that basically the fluidization region for the fast fluidized bed is lower than what we get for the turbulent. We could get more information regarding, for example, the Eulerian drag in Z direction for the fast and turbulent. And also the same thing happened for the velocity 0.318 meter per second fast and turbulent, in which you can clearly see more differences happening here. And here, basically, we are in the range of between turbulent and fast fluidized bed. And the same thing goes for the drag, basically, which we could look at it and see what is happening for drag in the Z direction. For the maximum velocity, also, these things actually were compared. And as I actually mentioned earlier, we are mainly dealing with the fast fluidized bed. So we expect these results to be closer to what we are getting by comparison with the experiment that I'll show you in a minute, basically. And this is actually the same thing for the Eulerian drag in Z direction. One of the important things that we were looking at it was pressure distribution for basically these regimes of the fluidized bed. First, for the turbulent fluidized bed, for these different superficial velocities, and the same thing for the fast fluidized bed. And as you can see, compared to the basically turbulent fluidized bed, here we are actually looking at the wider range for the fluidized regime, especially for the higher value of the velocity. And for the fast fluidized bed, this regime becomes actually much lower. When we are looking at this pressure distribution and comparing it with the experimental data for these values of different superficial velocity, you can see that compared to the experiment, for this lower value, we are getting more or less good results for the pressure distribution. This is height, by the way, and this one is the pressure. And as this velocity is increasing, we see that we are getting actually more close to the fast fluidized regime. And as you can see, the fast fluidized is compared with the experiment much better compared to what you can see from the turbulent fluidized bed, which doesn't actually give reasonable results, as you can see here. We also actually looked at the axial pressure gradient, as you can see on the basically vertical axis, and on the horizontal, this is the height. And for different values of the superficial velocity, it can actually generate reasonable results, and with the simple assumption that we are actually using just one basically correlation for all the domain, it's actually generating quite good results. And this is actually what we can see for velocity, which is higher. And again, the results are comparable with the experiment. It's giving actually reasonable results. And this is for the maximum value of the velocity, which actually, again, noting that we are actually used a very simple approach to use these correlations, it's actually quite reasonable. So this brings me to the conclusion that it emphasizes the requirement for the drag correlation to capture these mesoscale effects. And definitely the way to go for us is just to use this heterogeneous drag formulation and this EMMS model that we are using compared to other homogeneous drag models like DDASPO that cannot actually predict what is expected from these simulations. And Eulerian multiphase granular flow produces reasonable results, as one can see for this pressure drop gradient and bed expansion. And these results can be generated in kind of less than 2 days. What we are now looking at it is we try to bring the same experience for them and do all the actually other things that we have done for the Eulerian multiphase and compare all the results for the DEM to see what will happen in that area, basically. Yeah, I thank you for your attention, and I will be happy to answer any questions that you may have.
Right, great, thank you, Ali Reza. Any question for Ali Reza? Don't see any in the chat. We have time perhaps for one question. Let me ask something quickly. I think you mentioned that the EMS model can handle transition between the different groups. So if I have, let's say I'm looking at a biomass that goes through, a reaction as size and density changes, it will go from group B to group A, let's say. This drag model should be able to handle that, right?
Yeah. I mean, these actually, there are a number of, I didn't try to go into the correlations because these things are quite complicated and the function of, usually these things are just a function of volume fraction, the latest version that we are using. But the formulation is quite cumbersome. But you can actually cover all these regions from the bubbly to pneumatic one using this EMMS, and it can generate very good results. I mean, I tried here to just actually looked at just pressure drop and also a bit showing some of these things. But what you can see is for the gas holdup or solid volume fraction, I mean, this is actually black and white. You can get much better results compared to the homogeneous drag formulations.
Okay, great. Well, thank you, Ali Reza. If you have any question for him, please use the chat. Let's move on to our next presenter. He's Amir Masood Anvari, and from Clarkson University. And please go ahead.
Hello, can you hear me?
I can hear you.
Okay, thank you.
Sure. But okay, please share your presentation. All right, great.
Hello, everyone. Thank you for having me today. And my name is Amir Masood Anvari, and I'm going to present my research on predicting particle dispersion through the application of the transition, KKL omega, turbulence model, and Lagrangian method. Firstly, I will provide an introduction to my work. Following the introduction, I will delve into the various applications of my research. Next, I will discuss the methodology, including the geometry and the equations involved in the process. Subsequently, I will present the results, and lastly, I will draw conclusions and future work. Respiratory viruses, including COVID-19, can spread through airborne droplets generated by various activities such as sneezing, coughing, and even simple breathing. These tiny droplets actually act as carriers of viruses and play a significant role in the the transmission of infectious diseases. given the implications of airborne transmission, the design of ventilating systems becomes crucial for maintaining indoor air quality. Proper ventilation, can, for example, help reduce the concentration of, for example, respiratory droplets and contaminants in spaces for minimizing the risk of viral spread. Also, understanding the transport of airborne particles is really essential, and the movement of these particles in indoor environments, especially into the in the breathing zone of, for example, the receptors and the emitters, has a direct impact on the risk of infection. And at last, the choice of turbulence model, significantly affects the reliability and accuracy of our predictions. In this slide, I'm going through the application. The first is to develop effective strategies to minimize exposure to respiratory droplets, and since the virus can be transmitted through airborne particles, improving indoor quality, for example, air circulation, filtration, and ventilation can help reduce the concentration of particles. And for the methodology, we used ANSYS Split code and discrete random walk model, DRW, for the simulation, and also we used KK omega turbulence model for our research, and also we used different sizes of particles and also different ventilation rates, ACH, and also different size of partitions, the partition here. In this geometry, we have two mannequins and a partition between them, and also we have two inlets, supply diffusers and an outlet, return grill. And for the ventilation system, for achieving acceptable indoor air quality, we use the ASHRAE, American Society of Heating, Refrigerating, and Air Conditioning Engineer standards. As I said, we used KK omega turbulence model. It's a three-equation transition eddy viscosity model, and here we have three transport equations for turbulent kinetic energy, K sub T, and laminar kinetic energy, K sub L, and also omega. For the Lagrangian method, from here, Lagrangian method considers particles as a discrete phase and tracks the pathway of each particle. Lagrangian tracking method, calculates individual particle trajectory, by solving particle motion or momentum equation. Here in this equation, the left-hand side represents the inertial force, and the right-hand side we have, in the first term, we have the drag force, and the second term we have the gravity. Here we have the Reynolds number and also the relaxation time, tau, and here C sub C is the Cunningham correction factor. The aerosol concentration here in this research evaluated using a diffusion model approach, accounting for turbulent dispersion and gravitational sedimentation. Here C is the concentration, and also the V sub T here is the terminal velocity of the particles, and D is the Brownian diffusivity, and SC is the Schmidt number here. And the aerosol transport is simulated by developing a user-defined function for solving the equation. And also here we have another equation for normalized plane average concentration. We defined some planes, some sampling planes in the breathing zone of the receptor and also the emitter. And when particles pass through these planes, their information like the diameter, position, and temperature, velocity, and also the time at which they passed through these planes were recorded, and also the results exported to a file. Then we used a MATLAB code to generate information regarding the normalized plane average concentration. Here we have N here, and the N is the number of injected particles. A here is the area of the plane. A sub in is the area of the mouth, and V sub I here is the velocity that each particle at that velocity passed through the plane, and V sub in is the velocity that particles are injecting. Here I'm going through the results, and it shows the average airflow velocity, magnitude contours. At a section crosses the two mannequins, and we have here the ACH 1.9 with two different partition height. I should say that the ACH here means the air change rate. I mean that it's almost 2. It means that in an hour, the air in the room will be changed 2 times. And although the maximum velocity in this room is higher than 1 meter per second, the velocity contours in these figures are cut at 0.2 meter per second. So because of that, the detail of the airflow can be better observed. And by increasing the ACH, as we can see here, the ACH, the velocity magnitude from the superdiffuser is increasing, and also it's resulting in different airflow patterns inside the room. However, as we can see here, by increasing the partition height from 1.3 to 1.6, it doesn't result in significant changes in the airflow pattern. Here we have the concentration contour that are the fractional concentration of the emitter mannequin. I mean that these concentrations are normalized by the exhaled concentration, and as you can see here, the concentration in the room generally decreases with the distance from the emitter. It is for 10 micron particle size, and the ACH 3.95 with 2 different partition height. Here we have a plane, a sample plane that we define in the breathing zone of the emitter and receptor. The diameter of the plane is 1 meter, and the concentration for this partition height is almost 0.0022 for this ACH, and the concentration for this partition height, I mean this ACH 3.95 and 1.6 is almost 0.0021, and it says that we have less concentration near the breathing zone of the receptor, but not too much. It doesn't have, for example, significant changes in the breathing zone of the receptor. In this slide, I'm going through the results for particle tracking on Lagrangian method. As you can see here, these are the dispersion of the particles after 25 seconds, 50 seconds, and 150 seconds after emission from the emitter mannequin at this ACH, and we can see how the particle disperse and distribute in the room. Here we have the concentrations, normalized plane average concentrations for different planes. We have here the vertical, in the right hand side we have the vertical plane, on the left hand side we have the we have an horizontal, and we have different number of concentrations because we have different velocities in different directions. For example, in the right hand side, we have a direction in Z, and we have the velocity in y direction in the left hand side. Here we have a complete plane that at the previous slide we have half of this plane, and we have two other concentration, and the green one plane is the same plane that we use for diffusion model, and the concentration for this one is 0.0043 in the greasing loom. And here we compared the three different number of injected particles. For example, for 10,000 injected particles, we have 0.0041. For the order of 20,000 injected particles, we have 0.0043, and 7,000 particles, we have 0.0044, a normalized plane average concentration. And we increase the number of injected particles 2 times and 3 times, but we can see that the number of the concentration increased, but not 2 times or 3 times. At the end, we saw that presence of the partition significantly impacted airflow pattern and the particle distribution. However, by increasing the partition height, we had a negligible effect on the droplet dispersion and concentration, and also by increasing the air change rate, I mean the ACH, we had a less concentration near the breathing zone of the receptor, and for future studies we can have, for example, the thermal plume and heat transfer on the distribution and dispersion of particles. And thank you so much.
All right, great. Thank you very much, Amir Masood. Any question? I don't see anything in the chat right now. Just a quick question. In your future work that you listed,
Sure.
do you have any plan to also look at the effect that a mask may have in terms of aerosol penetration and distribution?
Well, actually, I saw some research about using some masks and on the face. But first, I want to see, for example, the rotation of the head in distribution in the breathing zone, or the thermal plume, and the heat transfer from the mouth, the temperature from the emitter and the receptor. It will be my future work.
Okay. Okay. Good. Good. Yeah, that should make some effect, hopefully. All right. Well, I don't see anything in chat. Well, if there is any question, please put it in the chat for Amir Masood. Thank you very much.
You're welcome. Thank you. Thank you.
Sure. And let's move on to our next presenter, Mohsen Amin. I'm sorry, from Argonne National Lab. Mohsen, floor is all yours.
Can you hear me?
I can hear you, and I see your presentation. Yes.
All right. So you're seeing the full screen, right?
I am seeing the full screen. Yes, sir.
All right.
Go ahead.
All right. Good afternoon, everyone, and thank you, Mardad. So my name is Mohsen Amin. I'm a senior research scientist in the Transportation and Power Systems Division at Argonne National Lab. Today, I would like to talk briefly about our work on large eddy simulations of particle-laden flows using the spectral element method called NEC 5000. So before getting into the work, I would like to acknowledge Juan Diego, who was a former postdoc in my group who did most of this work. He's currently at General Atomics. I would also like to acknowledge our collaborators from Argonne, Sikong Wu, and Samuddin. So here's a quick outline of the talk. I'll give a brief introduction about the background and motivation for this study. And I'll talk a little bit about the numerical method that we use called spectral element method and its implementation in the code NEC 5000. We'll talk more specifically about the fluid particle coupling using this particle in cell approach for coupling the fluid phase and the particle phase. Then we'll talk a little bit about the computational setup for this particle-laden turbulent jet flow and the experimental data set that we are using for the validation. The remainder of the presentation will then focus on the single-phase jet as well as the particle layer and jet simulations, and looking at the effect of several of the simulation parameters. And specifically, I'll be looking at the effect of particle collisions, effect of injection parameters, and effect of hydrodynamic forces on the solution accuracy. And then I'll conclude with some suggestions for future work. So again, it's for this audience, I don't need any further motivation, but turbulent particle layer and jets have found its application in several fields, including fluidized beds, flame spray pyrolysis, gas turbine engines, among others. In our group, in Transportation and Power Systems Division, we focus mostly on propulsion applications. We're looking at modeling fuel spray and spray flames. Spray impingement on hot or cold walls are of key interest. And if you have attended the talks in the morning, Roberto Torelli from my group had a talk where his focus was on multi-hole spray injection. Here, I'll be talking mostly about particulate and jet flows, but we basically use the same approach for also modeling fuel sprays as well. So a schematic is shown on the right, looking at both these phases: the carrier phase, which could be a gas phase generally, and the suspended phase, which could be either particles or liquid droplets. To model this, there are several approaches. Generally, you can divide it into Eulerian, where we solve everything in the Eulerian phase. For example, the cases that Roberto showed in the morning, where he was simulating the flow inside the nozzle. These are cases where Eulerian can be necessary. The other more commonly used approach for modeling these kinds of flows is to use this Eulerian-Lagrangian approach, where the full Navier-Stokes is solved only for this carrier phase, which does not really see the entire suspended phase. And the effect of the suspended phase is brought in through source terms in the continuity, momentum, energy equations. And the second approach is more popular and is also feasible. It's the more feasible approach when you have a lot of particles. In terms of fidelity, we also have our Reynolds average Navier-Stokes, larger simulations, direct numerical simulations, and whatnot. Again, in this presentation, I'll be focusing on the high fidelity LES of turbulent particle layer jet flows using spectral element methods in an Eulerian-Lagrange framework. So the method we're using is spectral element method. I'll give a quick intro about it. So this is based on a weak formulation. We're just using continuous Galerkin approach. So the idea is you discretize your spatial domain into several spectral elements, and the solution is represented as nth order tensor product polynomials within each of these elements. And in 2D case, you could look at it this way: if it's the 10th order tensor product polynomial representation of the solution, this is how one of these trial functions would look like. And you will have n of these, and you take a linear combination of that to represent the solution within each spectral element. The advantage of spectral element methods is that it combines the fidelity of being able to represent complex geometries, but you also get exponential convergence because of the spectral element representation or spectral representation within each element. Additionally, we're using characteristic-based time steppers, which allows us to use sufficiently large CFL numbers here, 2 or 2 to 3. For the particle solver, we use the library developed from Professor Paula's group, specifically by David Zweig, called PPICLF or particle PICLF. I forget the exact the full form of this. But in this approach, we are solving the particle equations using RK3 SSV approach, and to get the gas phase solution, we're using spectral interpolation from the gas phase to the particle locations to, for example, get the gas phase velocity, gas phase temperature, and so forth. And to move from the particle representation to the gas phase, we're using a Gaussian projection filter to, for example, get the track force term or the source terms for the momentum and energy on the gas phase from the particle phase. I won't go through these equations in much detail, but just for completeness, I'm showing the equation solved in the gas phase on the left and the particle phase on the right. The only thing to note is that we have this new quantity that's typically not seen in multi or single phase flows called theta g, which is kind of the void fraction, or which is 1 minus the volume fraction of the particle phase, and that represents kind of the volume that the gas phase sees. And we use spectral interpolation to get the velocities, temperatures, and so forth from the gas phase to the particle phase. And we use projection to kind of go back from the particle phase into the gas phase. So moving on to the model validation. So we are looking at a turbulent particle-laden jet, which was experimentally studied by this group in 1989. It consists of a turbulent jet of air, which contains glass spherical particles with a constant diameter. Some of the details are shown here. The density of the particles is also shown here. They had experimental data available for 2 different mass loading ratios. So here mass loading ratio is defined as the ratio of the mass flow rate of the particle phase to the mass flow rate of this gas jet. And for this specific, one of the reasons we chose this experiment was that the experimental data available for validation was pretty comprehensive. They had measurements available for both gas phase and the particle phase. They had mean RMS velocities and even some Reynolds stresses available as well for the gas phase. The computational domain is shown on the right. This is the cylindrical domain. We have 2 parts of the case, where one is your turbulent pipe flow, which leads into the cylindrical domain as a jet. So one key part of setting up this case is how do we introduce the particles to the gas phase. It's a 2-step process. So the first step is to use what we call a recycling boundary condition to establish a turbulent jet. So basically, you start with a laminar flow, you introduce some perturbations, and have the flow recycle back in. So basically, whatever exits out of this red line is fed back into this inflow, and you repeat this for some time, and the flow develops or transitions from laminar to turbulent. And then the second phase is to introduce a particle. There was some uncertainty from the experimental setup. They did not really give us too much detail, so we had to play around with this location. So here it's the location of injection, which is represented as V0. For the outflow, we are using a standard Dong outflow, which is a stable turbulent outflow. Going directly to the validation cases, starting with single phase. So they also had data for single phase. So there's no particles, it's just turbulent round jet. So here I'm showing validations for the mean velocity, the RMS velocity, Reynolds stress here in ZR space, as well as the centerline velocity as well. So overall, we see excellent agreement for both the means and the RMSs. So this kind of tells us that this recycling boundary condition we used actually worked, especially since we're getting pretty good agreement for the RMS and the Reynolds stress terms. Additionally, we repeated these cases with 3 different grid sizes. Here, what we call as P convergence. So we're not changing the spectral element representation itself, but within each spectral element, we are changing the polynomial order from 5 to 7 to 9. Overall, we see that between 7 and 9, the results are matches for both means and RMSs. So moving forward, I'll just be showing results with the 7th order polynomial, even for the particle-laden jets. All right, so the next 3 to 4 slides, I'll go over a couple of key parameters that we varied and how that affected the results. Starting with the effect of particle collisions. So we have 4 cases here represented as C1, C2, C3, and C4. In C1 and C2, the injection location, like I showed in the computational setup slide, was selected to be -5, which is basically 5 diameters upstream of the jet exit, of the pipe exit. And C3 and C4 is closer to the pipe exit, which is at -2. Here, 2-way and 4-way refers to no collision and collision. So this is just a nomenclature that is used by this PPI-CLF library. So 2-way would mean that there is only 2-way interaction. So basically the fluid phase interact or affects the particle phase, and the particle phase affects the fluid phase. In 4-way, we are also accounting for the particle-to-particle collision. So just a simple way to think of it is cases 1 and 3 has no collisions. 2 and 4, they do have collisions. So the simulation results are shown here for the centerline gas phase velocity, centerline particle phase velocity, and also the number density distributions along different axial locations. So overall, the simulations with the collisions tend to produce lower gas phase velocities as well as lower particle velocities for both of these injection locations. Overall, it does seem to agree better with experiments when we have collisions on, although the effects are not very significant. This can also be explained by looking at the particle distributions, which are shown on the right as well. So even with with collisions, the particle distribution seems to tend closer to the experiments, especially when you look at the radial distributions of the particle number density across different axial locations. Having collisions leads to a more spread out jet, and the distributions agree better with the experiments. We do see that the number density at the center line, which is shown in this fourth plot, is not that great. But we'll go into more details in a later slide. Additionally, looking at the injection locations, it's seen that if you have injection at -5, the gas phase agrees better. But if you need better agreement for the particle phase, you need to inject at -2. Again, we'll try to resolve this in a later slide. Now we're looking at the injection parameters itself. So looking at two different things. So one is injection location and the other one is the injection velocity. Again, one of the reasons why we had to play around with these parameters was that experimentally the details of how the particles were introduced into the jet were not very clearly mentioned. So we did have to take that as kind of a modeling or a tuning constant to really get to match the experimental conditions better. So here we're looking at 4 different cases. So case 2, 4, and 5 are looking at the same injection velocity, but injection locations of -5. Or far upstream, -2, far downstream, and -3.7, which is kind of an intermediate location. And case 6 is the same as case 2, but now instead of injecting at 0.7 times the gas velocity, now we're injecting at 0.5 times the gas velocity. So overall, when looking at the gas phase statistics, the case with injection location further upstream, or case 2, seems to have better agreement compared better agreement for the mean velocities near the pipe exit, while cases with injection locations further downstream have better predictions for the particle case. Overall, changing the velocity had the effect of reducing the overall gas phase velocity. And again, I'm not showing the Reynolds stresses here, but we found that all cases yielded similar results for the Reynolds stresses. Overall, based on looking at both gas phase and particle phase in general, we find that using an intermediate injection location of -3.7 yielded overall better predictions across. But again, there are still some places where things can be improved. This slide, I'm looking at the effect of hydrodynamic forces. So we accounted for 4 different forces that are due to the particle fluid interaction. The first one is, of course, the major one, which is the drag force. Additionally, there are 3 other forces we looked into: the pressure gradient force, added mass force, and shear-induced lift force. Again, like I said, typically only drag forces are accounted for. We just want to make sure, even for these cases, that is indeed the case. So here, case 7 and case 9, 7 has only drag accounted for, and case 9 had all 4 hydrodynamic forces accounted for. Overall, we see that the impact is negligible. So as you can see, for the gas phase velocity as well as particle phase velocity, the lines are all pretty much on top of each other. And looking at the centerline gas phase and centerline particle velocities as well, the red and blue are pretty much on top of each other. There were some minor differences in the Reynolds stresses. Again, not really shown here, but overall, not too much of a difference. Finally, we also had an additional case looking at the injection distribution. So for all these cases, we had an injection location based on the axial distance, but radially it was distributed non-uniformly based on experimentally measured number distance distribution. But when we use a uniform distribution, we did see a pretty non-negligible impact. So it is important to have, even if the axial location there's some uncertainty, we do need to have a non-uniform distribution of the particles across cross section of the injection location. All right, so this is a final slide. All the previous results were. force. Sorry. All the previous results were with a constant mass loading of 1, but we also ran cases with a mass loading of 0.2. So here, the 2 lines corresponds to a mass loading of 1, which is in this black line, as well as these filled symbols. And the red is the lower mass loading of 0.2. So overall, at lower loadings, what we're seeing is that the particles and gas phases tend to decelerate more in the downstream locations. And we're seeing that the current method can capture this difference in momentum transfer for cases with different mass loading ratios. And numerical results are showing the same trend as in the experiment. And again, our hypothesis is that as we increase the loading ratio, the particles will carry more inertia, which accelerates the gas phase due to the momentum transfer, and then this gas with a higher momentum will reduce the average drag force acting on the particles downstream, which results in faster moving particles. So that's kind of what we think is happening. So we did some further analysis as well. So some of these results were presented at the AIAA SciTech Forum, which is not shown in this presentation. We looked at particle subcycling. So this is just a way to improve the integration of the particle solver. We did not see significant effect on the flow statistics. We also looked at grid sensitivity. I only showed the grid sensitivity for the single phase jet, but we also did it for the particle laden jet as well. We did not see any further refinement. So n equal to 7, 7th order with the current grid was good enough. And initial particle distribution, I showed it slightly, again, assuming uniformly distributed particles only affected the near field, whereas in the far field, it does not really impact the velocity distributions. So overall, just to conclude, we showed that simulation results for the single phase jet were in excellent agreement, which showed that the way we are introducing the turbulent inflow is a valid way of introducing the turbulent inflow using this recycling boundary conditions. And we used a grid sensitivity analysis to show that a 7th order polynomial was able to give grid convergent results. For the particle laden jet, we looked at different things that could impact. Overall, it was found that for the conditions relevant to this study, including particle collisions, did play an important role in improving the distributions of the particle velocity as well as the particle number density, which also improved the predicted gas phase velocity as well. The other things we looked into were more to do with the fact that we did not really have the full quantification of the experimental conditions. There was some uncertainty in the way the gas phase or in the way the particles are introduced into the gas stream. So it was found that we did need more information about how much further upstream the particles are being introduced, and are they being introduced at a higher speed than the gas phase, at a lower speed, and whatnot. So these are important to get accurate predictions. So we are still, there is still a scope for improvement, and further, a few other things that might be missing would be also to see whether there was a swirl in the jet. Again, details were not available. And there are some other missing forces in the model, including history forces, some tangential components of collision forces, and also to have more realistic collisions as well. So with that, I will conclude this presentation. I'll be happy to take any questions.
All right. Thank you very much, Mohsen. Any question? There's actually a question in the chat. It says, were experiments replicated multiple times so you could establish error bars to correlate with numerical results?
Sorry, can you repeat that? I missed the first.
Sure. The question is, were experiments replicated multiple times so you could establish error bars to correlate with numerical results?
Yeah, that is a good point. I'll have to go back and check. Just one thing I want to mention is that this study was from slightly more than a couple of years ago. So still need to go back and check, but I don't think they reported the error bars. They did have the means and RMSs as well as Reynolds stresses reported. So we just used, so the way we did this was we're basically looking at the statistically steady part of the jet. So we established the statistically steady part, and then we did the time averaging to extract the means and RMSs. Yeah, so we didn't really look at the error bar. We were just kind of looking at the mean and RMS. So, but it is a good point. That's always going to be a case.
Yes, Marianne says fair enough. Thanks. All right. Any other question for Mohsen?
I have a question.
Please go ahead.
So is this an implicit LES model, or do you have a Smagorinsky-like model also?
Yeah, that's a good question. So we use something called it's called a high pass filter relaxation term. So there is a subgrid term, but it's not exactly a Smagorinsky term itself. So you're adding a high pass filter relaxation term as a subgrid model.
So that is the filtering, you mean?
Yes.
Okay. But you're not modeling the small scales then.
So the modeling is done through a high pass filter relaxation term. So you're not so there are two ways that we typically do it in Next. So one is kind of just doing explicit filtering. That's probably what you're referring to. So you run one time step, you then filter the solution at the end of the time step. That is one approach. The other one is to use a subgrid term, but that subgrid term is not exactly a Smagorinsky term. We call it a high pass filter relaxation term. So you are still adding that to the right-hand side of your equation. And again, I'll be happy to share, like this AWA paper has some details, and there are a couple of other papers which will give a little bit more.
Okay, great. I also have.
Feel free to just send a message. This is my email. Just send me a message. I'll be happy to share additional papers.
Is there time for one more question,
Yes, we have a few more minutes. Go ahead, Harry.
Okay, so in NEC 5000, you have the two pressure formulations, right? The PN and PN and the PN minus.
Yeah, yeah.
So are you doing the PN minus 2 here? Because...
No, this is all PN. These days, pretty much everyone uses PN. But yeah, this is all using PN.
Okay, thank you.
Yeah, the reason was also like eventually we kind of moved on from this to move on to sprays, like evaporating sprays and reacting sprays and whatnot. So for that, we had to use the low mark formulation within NEC, and low mark is only within this PN. So we pretty much are using PN.
Okay, thank you.
Okay, great. Thank you, Mohsen. If there are any further questions, please use the chat. Our next presenter is Ethan Young from NREL. Ethan, floor is yours.
Okay, new computer. I forgot I had to re-enable everything. Thank you for your patience, everybody. My name is Ethan. I work at the National Renewable Energy Lab, and I'm going to talk to you today about a brand new project. We're trying to develop a lattice Boltzmann solver that's going to let us simulate gas bubble transport through something called a porous transport layer, which turns out to be pretty important for electrolysis. So just a little bit of background, you probably already know this, but electrolysis is when you split water into oxygen and hydrogen. And it turns out it's a pretty sustainable and kind of promising way to produce hydrogen for energy. It's sustainable, especially if you use a green power source for the electricity to do the water cracking. I want to talk about one specific flavor of how you could do this. That's polymer electrolyte membrane, or PEM water electrolysis. And that's the picture that I'm showing on the right here, a really exaggerated cartoon. But basically what's happening is on the left-hand side, you have a flow of water past this really idealized looking porous transport layer, or PTL. There's an anode side and a cathode. So the water is brought through that PTL. It comes into contact with the anode catalyst, and that breaks the water into oxygen and hydrogen. The hydrogen kind of moves through that polymer electrolyte and it exits the other side. And in this, I mean, that's the product. In a sense, that's the exciting part. But the side that we're really going to focus on today is the left-hand side, or what's going on at the anode. So what happens at the anode is the water comes in, it contacts that catalyst layer, it starts nucleating and growing these oxygen bubbles, which then sort of move through the porous transport layer due to, you know, a combination of buoyancy and capillary effects and surface tension and so on. They grow to a big size on the exterior of that PTL, and then they kind of advect with the flow and are carried away. The oxygen is the waste product here. So, you know, I mean, it can be used for other things, maybe even like a biomass reactor or something like that. But in a sense, we don't care. We're just trying to get rid of it. And you can kind of imagine why that's the case, is because the longer the O2 bubbles stay on the catalyst, the less area you have available to perform this reaction. So it's really up to the PTL to facilitate the nucleation and the removal of that gas to keep kind of the maximal area of the catalyst open for business. And the PTL does other things. It has, you know, certain electrical properties and even some mechanical properties. But for our purposes, we're really just going to focus on this blockage idea that, you know, depending on how that PTL is designed, its porosity, the shape, things like the tortuosity, you can make it easier or harder for gas and water to move through that. And if you could improve this, then you could maximize the efficacy of the process overall, basically by maximizing the area of the catalyst that is available to do this reaction. So that's just kind of the background. That's what we want to tackle. And the way that we're doing it is with a lattice-Boltzmann approach, specifically a two-dimensional 9-streaming direction, or D2Q9 lattice-Boltzmann method. And actually, you know, this lattice-Boltzmann method is based on sort of mesoscale principles. So it's nice for this. It uses this idea of fictitious particles. I think not truly a particle method the way you usually think about them, but the idea that each one of these cell-centered quantities is a discretized Boltzmann distribution. Discretized in the sense that there are only sort of certain velocities along which we have a probability of traveling. And it turns out with this simple description, you can capture all kinds of cool behaviors. You can capture complex boundaries without doing any complicated meshing or grid adaptation, just by doing what's called a bounce back. So if a discrete velocity points into a solid, you simply reflect off of it, like what would happen, you know, at the molecular level with surface roughness. It's also pretty easy to capture multiphase interactions. The way that these interfaces establish and persist over time is all driven through a pretty simple to define set of interparticle forces. And that lets you capture even high density ratio systems, interactions between gas and liquid, liquid and solid, solid and gas. So it's pretty flexible. And finally, it's good at small Reynolds number, which is definitely not a deal breaker for us. That PTL that we looked at is on the order of maybe 100 microns thick. The velocity is quite small, the way things percolate through there. And so the fact that LBM is well suited for small Reynolds number systems is just fine by us. This isn't really a primer on LBM, but you know, just the bare bones description in terms of the math, you'll always see LBM with the BGK collision term written like this. It's kind of broken down into two components. There's the streaming aspect, which is sort of what we discussed, how those microdistributions, which you can think about like a histogram, the probability of moving along this certain direction, how they move from the current location, which is x comma t, and advect into the next cell at x plus e delta t, where e is a direction along this grid. So moving up or moving to the right or moving down and so on. On the right-hand side, you have what's called the collision term. So after the streaming step, and you have all of these microdistributions moved into their new location, all of the fluid cells look around them. They see all of the 9 quantities that they need to determine their macroscopic quantities. You know, what is my density and what is my velocity as a function of all of these microdistributions. And once you have that, those new distributions that exist in this new location do what's called the collision step, which is to sort of move toward their equilibrium distribution with some characteristic time tau, where tau is related to the viscosity. So how quickly or slowly you move toward that equilibrium is dictated by the viscosity of the system. And you can figure out what the system wants to be at, that equilibrium distribution, just based on the macro velocities here, or excuse me, the macroscale variables, density and velocity. At the bottom here, again, not exactly a crash course, but I'm showing what is meant by this idea of streaming. So these color-coded arrows are pointing along the discrete lattice directions. Before streaming, they all exist, sort of, you have the full histogram at each location. After streaming those cells, you can see where each one ends up, and the effective bounce back as well. So this is a handy picture. I reference it quite a bit. Multiphase we haven't really talked about yet. The approach that we take is called single component multiphase, which means that you sort of have less freedom to dictate the individual components of two different phases. So they share certain properties, but you can establish very strong density ratios using this approach. So an example of a single component multiphase system would be water and water vapor. So the single thing water, but split into two phases. And the way that we do this, or the catch, or the way that you inject these forces is, if you noticed on the previous slide, the calculation of the equilibrium distributions looked a little bit different than a standard LBM formulation. Instead of using the velocity, we use what's called the shifted velocity, which takes into account the velocity, but also adds onto it the total force. And you are free to kind of load that total force up with any effects that you want to try to capture. The two kind of critical ones are particle-particle cohesion, so the tendency of these high-density clumps to stick together, I guess, and adhesion, which describes a different force that is only active between solid particles and fluid particles. And you could add lots of other things. We added gravity, but there's surface tension forces and modifications to, interparticle forces that are between disparate phases or disparate fluids and so on. And I've broken down the two most important ones, the cohesion and adhesion forces. The first one is between fluid particles and the second one is between fluid and solid. And just to kind of give you a sense of how this works, if you look at the summation, again, you're looping over things that are neighbors to where you're currently located. So I loop over all of the neighboring entries of psi, where psi is an effective density or effective mass that we'll see on the next slide. But I loop over all of those and sort of sum up, weighting them by the streaming directions on the lattice. And just, again, to give a kind of sense of what that actually means, if you look at the picture on the right, trying to give some intuition, imagine you're standing at that high density pink node and you're trying to figure out what is the cohesion effect that I feel. Well, I loop through all of my 9 lattice neighbors. I notice, that up and to the right of me is a low density fluid, and so that gets weighted smaller in terms of the force that is applied. Down and to the left of me is a much higher density fluid, so that receives a higher weighting. And you can see when I sum those all up, the net effect in black there is this strong cohesive force that you can see tends to like corral a droplet and maintain that high density, low density interface across the edge. And there's a couple knobs you can control to control the strength of this. G cohesion and G adhesion are kind of scalars that determine how strong or weak those effects are relative to one another. Lastly, on the last slide, we talked about psi, the idea that we're trying to come up with something that describes the effective mass of this system. You can actually just use the density straight away, but then you're limited to very small density ratios. What is commonly done, or what we found out is commonly done, is to set it according to an equation of state. So you can come up with a definition of psi that depends on pressure, density, temperature, and so on. And there's all different flavors. To go probably way too quickly over this, suffice it to say we're using Carnahan-Starling, which we found can achieve a really high density ratio. And it's a function of, like I said, temperature and density. And you pick the constants. Frequently, the ones used on the right are employed, and so that's what we've done here as well. And that lets us get to a really high density ratio system of like up to 1,000 between liquid and gas, versus if we were just using density, you're limited to almost a density ratio of around 1. All right, so lattice Boltzmann was all new to us. Definitely multiphase was new to us. We wanted to kind of put the code through its paces. And so we started off doing some really simple benchmarks. In this case, we're doing a high density drop falling onto a surface. So it's going to be a high density liquid that is accelerated downward toward a solid wall due to gravity. And it's going to come to rest on that wall, and it'll form some contact angle. And we can control what that contact angle ends up being. If you remember back to the adhesive force, we have this scalar G adhesion, which controls the strength. So there's a cohesive force that tends to keep the drop together, and then there's an adhesive force that tends to pull the drop toward the wall. And we set this up, and we found out it's important to initialize this system correctly. I think that's true. We found other instances of the initial condition being quite important for a high density ratio system like this in the literature. And so what we ended up doing is, just to give you an idea, if I wanted to initialize a system like the one below, where that's a heat map of the density, a cross section, if you plotted the density along that orange line, you'd see that I have kind of a sigmoid function that is a function of radius. There's a high density in the middle where the drop is located, and there's a lower density at the edges where the gas exists. And I was finding it kind of numerically easier to initialize something that is close or a nearby solution, not exactly what it wants to do, but is close enough and kind of has a softened edge, and then let the system kind of lock itself in, versus us trying to start from that sharp initial jump across high to low density, which was leading to all kinds of numerical issues. Just if anybody else is having this problem, I found that to be a useful trick. So we start these all in the same way. Again, the thing that's varying here is the adhesive parameter. And sure enough, we get the expected behavior with G adhesion. All of these maintain a really sharp interface. The density ratio here is, if you remember that plot, around 1,000. So this is an indication that we have, the knobs are moving things in the right way, and also that, Carnahan-Starling is giving us this high density ratio, and it's stable even with big displacements and sort of motion and forces acting on that interface. The porous transport layer is all about bubbles, so then we did the same thing but kind of inverted it. So now we want to just look at what's going to happen if we sort of do this in reverse. Instead of starting with a droplet, we're going to start with a bubble, and I'm going to blow the bubble in the middle of a grid of kind of idealized PTL fibers. So again, this is really just like a cartoon, but we want to see what the effect is, the differences between how much the fluid wants to adhere to the solid versus the gas. What is the structure that you end up with, and how is that a function of the hydrophilicity or hydrophobicity of the surface? And we do a similar kind of soft start for the initial condition, and then we lock into a density ratio a little under 1,000. Actually, it's high, but it's under 1,000. And I'm also going to use this opportunity, to overload you with yellow and purple images to also show that we've done a little bit of, in a very qualitative sense, some mesh refinement studies to try and get a sense for, what are the rules of thumb for how refined these grids need to be. The top row shows our most hydrophobic example. So if you remember, G adhesion was -1, and as we move toward the right, we increase the resolution of the grid. You can see there's a sort of a qualitative change in the shape around 128 to 192, but then between 192 and 256, it looks like we've converged onto a final orientation. The more hydrophilic case on the bottom row locks into a converged shape pretty quickly. And so we kind of use these rules of thumb for how many nodes to place across cylinders and how many nodes need to be in between the fibers of our PTO. And I think this picture kind of shows why that is important. The resolution is important. This idea that you have kind of this sharp interface between a density of 1,000 and a density of 1, and you are better off if you can sort of resolve that smoothly. And so yeah, we were happy to sort of see that we do get some type of convergence. We're still working on this. Finally, I want to just show some initial progress on PTL. This only does kind of a fraction of what we need it to do, but we are able to demonstrate, that we can get buoyancy-driven bubbles moving through the water and interacting with the PTL. This is sort of the first slide where I've showed dimensions, because now it's important that we tackle this the right way. So, like I said, the thickness of this PTL is 250 microns here. It establishes a really small Reynolds number, and we're just going to look at a subsection of this. We're not going to try to tackle the nucleation at the surface, which it turns out is hard, nor are we going to deal with how the background flow looks. We just want to see for the moment if we can get buoyancy-driven flow through here. And again, because we're not dealing with nucleation at the surface, in order to have a bubble to look at, we sort of cheat and use a periodic boundary that as it leaves the top, we will release a new bubble from the catalyst at the bottom there. And you can see At this high density ratio, we're getting a really strong surface tension effect here. This bubble is very easy to get it stuck, even with something that is relatively porous. So as I move to the right here, all I'm doing is increasing the radius of those fibers. And you can see pretty quickly it gets stuck because it wants to adhere to those. So in other words, the buoyancy effect here is not enough to overcome sort of the capillary pressures that the water is exerting and the related thing of surface tension at the interface. And that's essentially what happens in the real PTL as well, except that at the catalyst, you're injecting and displacing more liquid as you produce more of the gas phase. And we're not able to do that here. And so we're sort of stuck until we can come up with a better boundary condition that simulates the nucleation and growth and sort of injection of oxygen into this system. But this was still kind of an interesting thing to see. If we wanted to have more control over the individual phases, so remember I said that we were using a SCMP for single component. There's also MCMP flavors where you actually treat both fluids separately. You can see how that would be initialized on the bottom left. So both fluids actually exist everywhere in the domain. It's just that one takes a strong precedence over the other. So previously we just had a single blue line. It was either high or low density. Now we have two. And the blue, where it takes precedence, would be representing the air here. And the orange line, where it takes the precedence, represents... I'm sorry, I got that backwards. The blue line would be the water, and the orange line would be the air here. I think my graph may be backwards. But when we do this, then we can sort of come up with... we can control the forces arbitrarily. So we can, for instance, set the air to not interact very much with the solids, and for a very low density ratio, at least this little toy example here, we can get lots of sort of interesting flow effects. But again, this is, I would not put a whole lot of stock in this result because the density ratio is quite low. Really just a toy example to show off, that you can tune these things individually with MCMP. So this is my last slide. It's short on conclusions, a fairly new project we're working on, and long on future work. So even though we kind of are just getting the pieces in place and just now starting to get our first kind of cut of interesting results, we think we kind of have the fundamental pieces in place to solve this PTL problem. The future work is really just boundaries, boundaries, boundaries. I mean, we need a way to sort of grow oxygen bubbles at the surface, a way to kind of naturally inject them and have sort of propagation through the PTL, and then a natural kind of growth and eventually detachment and release at the exterior side. So far, we've only been doing synthetic boundaries, but the sky's the limit, as far as taking an image, thresholding it, and using that as our interface. And finally, we're going to move this to capture 3D physics into a D3Q27 code. So with that, I'd be happy to take any questions. Thank you very much.
All right, we're great, Ethan. Thank you very much. Very interesting work. We are right at 4 o'clock, so in the interest of time, I'll encourage you and others that have any questions, please use chat and communicate with Ethan. So that will bring us to our last presenter, Felipe Marcial. I apologize if I mispronounce your last name. And Felipe is from Louisiana State University. Felipe, please go right ahead.
Okay, so my name is Felipe Maciel, so I'm a research associate here at Louisiana State University. And I'm glad to share some of the developments of this project. So just acknowledging some of the people involved. I have Dr. Waltrich, also from Louisiana State University, Janine, Carney, Brian Toss, Brian Fronk, and Fuad. So it's everyone involved in this project. Okay, so my title here is Computational Model of Acoustic Solid Interaction for Early Kick Detection Wellbore using log wire drilling tools. And so this come up with a quick methodology here, a quick motivation here. So as we may know, like the unexpected gas invasion or kick is still like a common and persistent threat for drilling operations, and this brings up the risk of loss of well control and blowouts, such as happened of the well-known Macondo disaster with loss of life and also loss of like enormous environmental disaster. So this brought up the idea that came up with one of the Kelly Rose publication here of the suggested early kick detection method. Seems like the common ways of detecting kick or gas influx, it's really significant lagging in terms of time and in terms of missed or false detection. And the idea of using well-known tools that's being already implemented in the wellbore, such as the log while drilling sensors that are there during the drilling operations, came up to mind. But one of the issues on developing this is the lack of data and the hard time of obtaining this field data from oil companies and from lab operations, because it's a very complicated scenario to test and to obtain information. And we've been working on this synthetic data development. So we are using both computational methods and also experimental methods to come up with synthetic data and to try to fill this knowledge gap in terms of information so we can use to develop this idea. It's basically producing this synthetic data and creating some sort of database that can be used to create and test a machine learning algorithm that can be provided and used for detection and real-time analysis of the information that comes from these LWD tools, and using those information to serve as a warning for drilling personnel. If we have a gas influx in a well, for instance. Okay, so here just an overview of what we are trying to see or trying to model here. And we are looking specifically at the acoustics signal, at the logging, the sonic logging, which is also implementing in most of the BHAs that's already in this log while drilling approach. And we are looking at that since we have from the literature that the sonic signal, they are very sensitive to change in the fluid properties that we have there. So as you can see here, the speed of sound, the speed of the propagation of sound waves in a fluid medium is very sensitive to change of density and the void fracture, the book modulus of that fluid itself. So if you have a gas in a fluid, we're going to have a different speed of sound. And it brings up the potential to use this sonic tool as a method to detect as a potential method for early kick detection. And we are working on modeling this propagation behavior. Just very quick here, just an overview. There we have we're gonna have here the sonic tool, just an example of that, and the propagation that goes from the transmitter to a set of receivers here. And the propagations go through the fluid and then through the rock, and then as it goes forward, it goes back to the fluid and to the receivers as well. And part of the arrivals is going to have here the mud arrivals is going to go straight through the fluid up to the receivers. So this set of information can be used as data, so we can use to calculate the speed of sounds and see whether we would have a kick or gas influx in this fluid medium. And in terms of modeling this, so here's the general scalar wave equation, and it's very much describes acoustic perturbations, very small acoustic perturbations, and it's especially dependent on the density and the speed of sound of that material that the fluid or that sound wave is propagating to. And this equation is implemented in COMSOL, so that's the main solver that we are using for this project. And it allows for also different types of source, so like monopole and dipole source, and also for solid fluid interactions incorporations, since you have also a solid component with the rock component in a wellbore scenario, for instance. And in terms of two-phase flow model, and we are looking at two main approaches that we're trying to do in order to model the speed of sound or the acoustic propagation in a fluid, in a two-phase fluid. So here we have the homogenizing model, which is pretty much it's a homogeneous model with an approximation for the properties of a multiphase fluid. We use the Woods equation, so we can get a mixture speed of sound based on the liquid and gas fractions, and also the speed of sound of liquid and gas and density of liquid and gas for that material. And it's going to give us a mixture speed of sound that we can use to model a very specific void fraction or a specific amount of gas in that fluid domain. Similarly, here we have a discrete bubble approach that we actually model the bubbles itself. We're going to have a set of bubbles dispersed in this domain here, and the volume of the bubbles related to the total volume would also give us a certain void fraction that we're using to model this multiphase, this two-phase fluid model here. Of course, this is computationally more expensive than this, but it allows for extra complexity that we can observe in terms of, for instance, sound scattering in the bubbles itself that we cannot observe in a homogeneous model like this. Okay, so just a few examples of what we can get in terms of results, of simulation results that we've been getting from this. I have here a simple model of a column with a homogeneous section and a bubbly section, and have a source at the bottom and a few probes, a few receivers sparse up to the end of the domain here. And we can get information such as the ones showing here, which is very much similar to what we would expect to get in a, let's say, LWD scenario. Have like a source and a few receivers and get some information in terms of pressure perturbation of this propagation here. And we can use this information the similar way that they use in the analysis for the speed of sound, and we can obtain based on the distance between the probes and the time of arrivals in that probes for the same wave peak that we're looking at. We can get that information and obtain the speed of sound for that material here. So here you can see we are setting this lower part as water. So we're going to have on here 1480 meters per second. So we are getting around 1500 meters per second on the analysis here. And in the bubbly domain here, this bubbly domain has a 2% void fraction. And based on the Woods equation, only with 2% void fraction would lead to a speed of sound of 85.6% meters per second in that section. And that's pretty much what we're getting here as well, just setting air bubbles in the middle of a water domain with this void fraction. And we get relatively good results compared to what we said, what we expect in there. And bring it a little bit more closer to a wellbore scenario. Here, let's say, still notice that we're using that approximation for pressure acoustics. So this will have a solid-like domain. It's not an actual solid because I'm not using any properties of the solid material here, such as solid mechanical properties. Just approximating with the speed of sound for that solid material and the density. And have a fluid model, a fluid domain, or a wellbore fluid domain here with a certain already speed of sound and density and source and a set of receivers. And we can get something like this. So this is pretty much what we expect, to have a source, and as the propagation of the wave goes and reaches the solid material, it reflects back and have like a reflector wave, a transmitter wave, and creates this compressional head wave. And as if you have like the solid mechanical properties, we've also created this shear head wave, which is we are not seeing here because we're not modeling that yet. So, but still, only using this approach, we in terms of speed of sound, we can already spot the fluid wave, which is what I expect in terms of it comes directly from the source, and also the compressional head waves. And we can use the same analysis in terms of probe arrivals to capture the speed of sound of these two waves, and it matches really well from what we're expecting in terms of velocity for those two materials. Okay, so now we're looking at a little bit more realistic scenario, and then we're implementing actually the solid mechanics properties in that rock material here. So we're not doing that before, but now we can see that the speed of sound and the speed of sound of the compressional and the shear wave, they're dependent on the elastic properties of that solid material, such as Young models, Poisson ratio, I have here shear models, bulk models, and density of that material. So this would give us the CP and CS, which is like the propagation of the P wave and the propagation of the C wave velocity. And so those two equations, they are also implementing the solid mechanics models in the solver that they use, COMSOL. And we can combine these two approaches in a more realistic approach with multiphysics, with pressure acoustics and solid mechanics interaction. And here we have a similar domain as I showed before. I have like a fluid domain, a solid domain, and this is just absorbing layers, so we don't have a lot of reflections coming back to the domain. And we have a similar set of propagation signals coming as the transient evolution goes by. And at this point, we are able to see the direct wave propagation and the compressional wave propagation. At this point, we also see the shear wave propagation. I just zoom in a little bit here to see a little bit better. We have the compressional head wave, the shear head wave, and the fluid wave propagation. So this fluid wave, in terms of the problem that we're looking at, it's like the most important in terms of identifying if you have a different void fraction in the fluid. But we can validate like this compressional head wave and shear wave, and to see if our model is working as we expect, using this using the critical angles of reflection that we have, which depends very much on the speed of sound of the compressional head wave and speed of sound of the shear wave. So these are the calculated critical angles. It's very much the angle that would still see any reflection if we have a wave propagated from one medium to the other. And we are able to match those angles really well in our simulations as well. So this some sort of validation against analytical calculations of this critical angle. And this tells us that the model is doing at least what we're expecting in terms of capturing the shear wave and the compressional head wave. So when you look at a more similar approach on what we think in a probe, transient probes or transient receivers spaced around like this line here, we'll see something like this. We will expect to see like the pressure wave and the shear wave right after that, and then the mud arrivals and the stone wave. So this would be especially the ones that would be mostly affected by changes in speed of sound due to gas influx in a case of a kick, for instance. But here these are analytical calculations of the head wave, the compressional and shear head wave, and the direct arrivals in terms of time of arrivals. And this is what COMSOL is capturing for this specific position, for these two probes. And you can clearly see the compressional head wave and the shear head wave, and here the fluid arrivals. So we're still working to try to identify better which one is which in terms of mud arrivals and Stonley wave arrivals here. So those are the ones that are mostly related, as I mentioned, to the gas influx in the case of a gas kick, for instance. Okay, so now we have like this type of information, which is similar to what we were expecting in a log while drilling scenario. We have like those several probes spaced out, and have like this a lot of data coming like in terms of arrivals on these probes. This is the transient propagation for this specific simulation. And using this, using all this information, we are trying to translate this in a like more analytical approach to see if we can capture that if we can capture those information that we want to see here. So this is like a semblance plot. This is like a conventional method used already in analysis of acoustic signals. So this can tell us, based like an information like this, what's the speed of sound and what's the time of arrival for each specific component of that signal here. So here it captures the direct wave arrival and the shear wave, the shear head wave, and the compressional head wave, which matches with what we expect from this domain here. I have like here, compressional head wave would be around 1880 meters per second. Shear head wave and the fluid head wave. So now this fluid head wave here, so as you can see, it's very distinct here. So let's say we have a fluid. So this already has a certain void fraction, and we have a fluid with a gas influx. We'd like to see something like this in this plot. So it tells us that in that specific scenario, we would having gas, not only liquid, but also gas in the wellbore. It's very well characterized by the direct fluid wave here. Okay, so this is always, most of this is still ongoing work, but I already have some of the final remarks here and some of the next steps that we're still working on. And especially in terms of what we saw so far, we are able to confidently able to predict the main modes of propagation that we see in a LWD scenario. And we saw that you can see the shear wave and the P and S wave propagation velocity, and also the fluid head wave, the fluid arrivals. That's like most important for this kick detection approach. But we are continuing to explore these fronts here. So we're continuing to explore like the solid fluid interaction component. So we still try to identify a little better what like this fluid arrivals here, and trying to identify which one is which in terms of mud arrival and in terms of Stonley wave, and also whether we can use actually these components to identify changes in void fraction in a wellbore. We saw that we can see that in a simple model. We can see that it can set at different void fractions and it can capture that, but can you use that to actually identify changes in void fraction in a like more realistic scenario? And also, we're continuing investigating this discrete bubble approach. We have done some work on this already, but we're going to investigate more how does this bubble mixture as opposed to homogeneous mixture impacts the wave train, and we'll see some differences in terms of, especially in terms of amplitude that returns from the propagation of the waves in a bubbly scenario and the propagation of the wave in a homogeneous medium here. And forward, especially in the data analysis and machine learning development, So we saw that we can use the signal analysis and the machine learning techniques to identify the direct arrivals, the shear wave, and the head wave. But we are working towards seeing if we can actually use that as a measure, as a way to identify a kick, or using those types of wave trains. So this is like a ongoing and future steps that we are taking for this project, for this approach. And this is pretty much what I had for this quick presentation. So this is just acknowledging LSU, Oregon State University, and NTL is all involved on this front. And if you have any questions, left my email here, and we can also, I don't know if we still have time for that, given the.
Well, we are well over time. Is there any question? Let me see. I don't see anything in the chat. But in the interest of time, let's wrap it up here. If there are any questions, please reach out directly to Felipe. And this should conclude our two-day workshop. I'd like to thank everybody for participating. And thank you, Brian. Thank you, Karen, for all the behind-the-scene work to make this two-day a success. As I was saying earlier, with the pandemic behind us now, we will have our next year workshop in person. So hopefully we'll see you all in Morgantown next year. Thank you all for participating. Have a great rest of the day. Bye-bye.